Good afternoon to Vanda. Good afternoon. So you please kindly confirm audio video on screen once. Please kindly confirm audio video on screen. Clear? We will wait for 2 or 3 minutes. Okay, then we will continue with the symmetrical components. With some problems, we will continue with this topic. Yeah. So we'll continue the session. See, yesterday we have discussed about the symmetrical components is expressing complex power in terms of symmetrical components. Now I'm taking up one problem on this concept. Go through this one. Yeah. So go through this question once. See, an unbalanced three-phase system has the symmetrical components of voltages and currents. Symmetrical components of voltage and currents as V0 minus 0.1, V1 0.9, V2 minus 0.1. I0 equals to minus J 0.5, I1 2 minus J1, I2 minus J1 per unit. Find complex power flow in the phase A. Only in the phase A, we have to calculate the complex power flow. 2. find the total three-phase complex power. And he said in the problem itself, choose a base value as 200 MVA three-phase. You have to select the base MVA as 200 MVA three-phase. With respect to this base value, we have to calculate the complex power flow in the phase A, absolute value. Similarly, three-phase complex power, absolute value. Okay, irrespective of the symmetrical components and all, generally, what you say complex power in one of the phase, maybe phase A, simply it is nothing but VA into IA conjugate. Complex power in the phase A is nothing but VA into IA conjugate. What is VA? VA0 plus VA1 plus VA2. See, whatever the symmetrical components they have given here, those are definitely with respect to phase A only. So we know phase A sequence voltages, phase A sequence currents. By using these two, we try to calculate the values of VA and IA, and you take VA into IA conjugate, that will give you complex power flow in the phase A. Okay, right. So I will take in the next slide solution. So from the data what they have given, zero sequence voltage VA naught equals to minus 0.1, positive sequence voltage 0.9, negative sequence voltage minus 0.1. Okay, next, zero sequence current, that is minus J 0.5, positive sequence current, that is 2 minus J1 per unit, and negative sequence current, that will be minus J1 per unit. Okay, now part A we are going to solve here, part 1. So complex power in the phase A, complex power flow in the phase A, Okay, so I am calling it is SA, which is VA into IA conjugate. Okay, now we calculate phase A voltage. What is phase A voltage formula? VA0 plus VA1 plus VA2. And that summation, if you take minus 0.1 plus 0.9 minus 0.1, so you may get this number 0.7 per unit. Phase A voltage is 0.7 per unit. Okay, what is current IA? So it is IA0 plus IA1 plus IA2. IA0 plus IA1 plus IA2. And if you sum up these three currents, real part will be 2, imaginary part will come minus J 2.5 per unit. Okay, now we calculate the complex power SA in the per unit domain, VA into IA conjugate. Okay, yeah. So let's say now SA is equals to VA 0.7, IA conjugate means 2 plus J 2.5 in the per unit domain. 2 minus J 2.5 conjugate means 2 plus J 2.5. So you take that real part, it is 1.4 plus J, imaginary part will come to be 2.5 into 0.7. Na? So 1.75 per unit. 1.75 per unit. It is complex power in the phase A in the per unit form. Complex power in the phase A in the per unit form. Okay. (1.4) plus J 1.75 per unit. And this we have to convert into absolute form. Means you have to multiply this with the S base. What S base you have to consider now? Is it S base per phase or S base three phase? I need your answer. We have to convert this into absolute form. With what S base we have to multiply? S base three phase or S base per phase? S base per phase. Very simple thing. Listen, please, listen. This voltage VA is a phase voltage. IA is a phase current. Okay. So to convert this into absolute form, we have to multiply with the phase voltage base, phase current base. Phase voltage base into phase current base is a phase MVA base. Okay. So from the data given, S base three phase value, it is 200 MVA. 200 MVA. And if you take up S base per phase number, which is 200 by 3, 200 by 3 MVA. Okay, so SA, complex power SA in MVA form is nothing but complex power SA in per unit multiplied with S base per phase. We have to consider S base per phase. And you take up this multiplication, J 1.75 into 200 by 3. Okay, so you get some real part, maybe in megawatts, and imaginary part you get in MVR. Okay, so get this number 1.4 plus 1.75 I into 200 by 3. Real power is 93.333 megawatt. 93.333 megawatt. Reactive power is 116.67. 116.67. Like this. Maybe sometimes in examination, they may ask you only real power, or they may ask you only reactive. Chances are there. Chances are there to ask you only real power and reactive power rather than the whole complex power. Okay, fine. Next, this fine. And next one, it will be a bit confucius for you. Next one, what I'm going to do. Second part of this problem. Second part of this problem is, what is a three-phase complex power value? What is a three-phase complex power value? That's what he is asking. See, simply listen please. Total three-phase complex power is nothing but phase A complex power plus phase B plus phase C. Yes or no? Means what you have to write here? What you have to write? VA into IA conjugate, phase A complex power. Phase B complex power is VB into IB conjugate. And phase C complex power is VC into IC conjugate. You have to write. But already you know VIA, okay. But how to find VBIB? By using symmetrical components of voltage and currents, we should go for VBIB. Again, by using symmetrical components of voltage and currents, you should go for VCIC. Then you have to substitute here to get SABC. Rather than that, in the previous class, we derived one equation, right? We derived one equation for total three-phase complex power as 3 times of VA0 IA0 conjugate plus VA1 IA1 conjugate plus VA2 IA2 conjugate. That equation we have derived. That equation we are going to use now to calculate the three-phase complex. Okay, yeah, kindly listen. So I am writing this as from previous derivations, VA0 IA0 conjugate plus VA1 IA1 conjugate plus VA2 IA2 conjugate. Already these values are directly available to us. This multiplied with 3 will give three-phase complex power. Okay, now you substitute these numbers a bit quickly. So VA0 number minus 0.1. Okay, so what is IA0 conjugate? IA0 conjugate, it will be plus J 0.5. Come plus J 0.5 plus VA1 number 0.9. And what is IA1? IA1 is 2 minus J1. Conjugate means 2 plus J1. 2 plus J1 plus VA2 minus 0.1. And what is IA2 and conjugate to that? What is IA2? Minus J1. Conjugate means you will get plus J1 here. Plus J1. And you calculate this number, you get this in per unit form. So it is minus J 0.05 plus 1.8 plus J 0.9 minus J 0.1. Okay, so find out that real part value. So 3 into 1.8 is a real part. 5.4 per unit is a real part. 5.4 per unit is a real part. And imaginary part, if you take, it's 0.9 minus 0.9 minus 0.1 minus 0.05. Okay, 0.75 into 3. So it will be plus J 2.25 per unit. Plus J 2.25 per unit. It's a three-phase complex power in the per unit form you got. Three-phase complex power in the per unit form we got. Okay? Yeah. See, after getting this one, this we have to convert into obsolete form. With what base we have to multiply this one? That will tell you. Is it S base per phase or S base 3-phase? That's the question. Common sense. Common sense you have to apply, right? Don't tell the answer just like that. Tell by thinking that thinking the question what I've asked you. What base we should consider here? S base per phase or S base 3-phase? Listen all of you. Listen all of you. All are saying wrong answer. Look here. Look here. SABC is equals to VA into IA conjugate plus VB into IB conjugate plus VC into IC conjugate. Just listen my words. Kindly listen my words. VIA conjugate plus VBIB conjugate plus VCIC conjugate. Now, see this VIA conjugate absolute value. Listen to me. VIA conjugate or SA, you can say SA. SA absolute value, and this is SB, and this is SC. SA absolute value is nothing but SA per unit into which base? SA absolute value is nothing but SA per unit into which base? Per phase or 3-phase? Per phase. Okay. So I can write this as SA per unit into S base per phase. That's the first one, SA. What is SB? SB per unit into S base per phase. S base per phase. And what is SC? SC per unit into S base per phase. All of you getting my words? SC absolute value per unit value into S base per phase. SB absolute, SB per unit into S base per phase. Similarly, SC. S base per phase common. After taking the S base per phase common, you can write SA per unit plus SB per unit plus SC per unit. All multiplied with what? S base per phase. S base per phase. What is this SA VIA conjugate in per unit form? Okay. And SB VBIB conjugate in per unit form. SC VCIC conjugate in the per unit form. So this per unit summation multiplied to S base per phase we have to consider. Multiplied with S base per phase we have to consider. And the summation what we have here, we have replaced it with the help of symmetrical components. With the help of symmetrical components as 3 times of VA0 IA0 conjugate plus VA1 IA1 conjugate plus VA2 IA2 conjugate. This whole complex power calculated in per unit domain multiplied with S base per phase we have to write. S base per phase. This is a way of exact understanding. Exact understanding. Yeah. All of you understood this slide, what I have given? Just I have written this one in the reverse way. I have taken the SABC exact complex power or absolute value. From that, per unit into base, I have written. Base I have taken common. Whatever the per unit complex power you have, that I have rewritten in terms of the symmetrical components of voltage and currents. Okay. Now, all of you, please answer me. Whatever the per unit complex power you calculated now, SABC, by using this summation, by using this phase A plus phase B plus phase C, you got this number in per unit form. With what base we have to multiply this number? With what base we have to multiply this number to get the absolute? Per phase base or 3-phase base now? It will be a per phase base. Again, somebody is saying 3-phase. Again, somebody is saying 3-phase. Okay, per phase base. So I can write in the next slide. SABC from the problem in terms of MVA is equals to calculated complex power in per unit 5.4 plus J 2.25. 5.4 plus J 2.25 per unit value into S base per phase. S base per phase. So it will be 5.4 plus J 2.25 into 200 by 3 in terms of MVA. Okay. Again, in the examination, sometimes they may ask you only real power, or sometimes they may ask you only reactive power also. Chances are there. So real part is 360 megawatts, and reactive power you will get like 150 MVAR. 150 MVAR. Okay. Yeah, which system we are discussing? Be clear about this one. Which system we are discussing? Unbalanced system we are discussing. All the things whichever we are doing is for unbalanced system. I will make your doubts a bit clear. First, follow the things what I am saying you in a sequence. All your doubts will be clear. Yeah, so let's move with the next slide. I'm taking up one more problem. The starting two problems what we are discussing today, these are a bit untapped area in the examination. These problems are untapped area in the examination, both GATE as well as in the ESE. These are a sort of untapped problems. Untapped areas also you can fill. Yeah. So go through this question. The symmetrical components of voltages in an unbalanced system. Is saying that the system is unbalanced. Well, and symmetrical components of voltages in that unbalanced system are V0. So as I said earlier also, but still somebody is asking me in the Q&A tab, sir, how V0 is 0.1, how you have taken that as VA0? That's what I said earlier itself. If you said simply the sequence voltages V0, V1, V2, we should take these sequence voltages are corresponding to phase A. Like VA0, VA1, VA2, we have to take as a general convention. Okay. The base value is 11 kV line to line. Voltage base is given 11 kV line to line. Okay. First one, find VA in per unit form as well as in the kilovolts. Second, find VAB in per unit form as well as in the kilovolts. Okay. Yeah. So let's take up the solution. Let's take up the solution here. First, sequence voltage is given VA0, VA1, VA2. Sequence voltages. It is 0.1, 0.9, 0.1 per unit, 0.9 per unit, 0.12 per unit. No units. Per unit means no units. Okay. Next, base voltage is given 11 kV line to line. Base voltage is V base, you can write. Line to line is given 11 kV. 11 kilovolts. Then V base per phase will be obviously 11 kV by √3 you have to consider. Without thinking star, delta, anything. Simply V base line to line 11 kV. V base per phase means it is 11 by √3. That's it. Okay. So generally I am saying V base per phase is nothing but 11 kilovolts by √3. Fine. What's the first one is asking? Phase A voltage, right? Right. Phase A voltage is asking means VA. What is that VA formula? VA0 plus VA1 plus VA2. That summation is nothing but 1.12 per unit. What's the angle of that? It didn't given any angles for these sequence voltages, right? Means obviously angle of each sequence voltage is 0. The angle of each sequence voltage is 0. So angle of the phase A voltage is also 0 degree. If you want to write it is at an angle of 0 degree in the per unit domain. Phase A voltage. Phase A voltage. Untapped area. Untapped area in the sense they have not asked any question in this area till now in the examination, not undamped. Okay. Next. Yeah, Pratik Pramod. That's what I am saying you. They have not mentioned anything. So simply line to line voltage base is given. You consider this as terminals. terminals of the equipment. You consider this at the terminals of the equipment. The terminals of the equipment per phase base is nothing but line to line base by root 3. I said already, you will have a confusion of line to line voltage base and per phase base if you are doing calculation for delta winding, only delta winding. At terminals, if you are considering, it will be line to line base and per phase base is line to line base by root 3. Okay, tell me please, this VA we got in per unit form. I want to convert this into absolute. I want to convert this VA into absolute form. With what base you have to multiply this one? Is it per phase base or line to line voltage base? Per phase base or line to line voltage base? You have to multiply that with per phase base. Okay, right. So VA in terms of kilovolts is VA, what you have in per unit, multiply to V base per phase. Means you can get 1.12 at an angle 0 degree into 11 by root 3 kilovolts. Okay, calculate this number. It will be 7.113 kV. 7.113 kilovolts. VA in terms of kilovolts is 7.113 kilovolts. Fine. Second part of this problem, same problem. Second part of this problem is calculating line to line voltage VAB. Calculating line to line voltage VAB means you should take VA minus VB. VA minus VB. Yeah. So I'll take in the next slide. Second part of the problem is line to line voltage VAB. It is nothing but VA minus VB. VA minus VB. Now you can say, but you don't have direct values of VA and VB now. You have only symmetrical components. So let's write VA in symmetrical components as VA naught plus VA1 plus VA2 minus VB in symmetrical components. VB in symmetrical components will be VA naught plus alpha square VA1 plus alpha into VA2. Yesterday we have discussed about this formula VB, VA naught plus alpha square VA1 plus alpha into VA2. And you take the subtraction quickly. VA naught minus VA naught cancel out. VA1 minus alpha square VA1. So you take VA1 common. So you have 1 minus alpha square plus VA2 common 1 minus alpha. Like this you get. What is VA1 number? VA1 0.9. VA1 number is 0.9. What is this 1 minus alpha square value? 1 minus alpha square. You go with the phasor diagram or you keep that in the rectangular form. Calculate that 1 minus alpha square. Already I said yesterday how to calculate 1 minus alpha and 1 minus alpha square. Okay. So 1 minus alpha square if you take, I think you will get this as root 3 at an angle of plus 30 degrees. Like this you will get. Root 3 at an angle plus 30 degrees. And VA2 value given in the data 0.12. VA2 value given in the data 0.12 into 1 minus alpha. You may get this as root 3 at an angle minus 30 degrees. Root 3 at an angle of minus 30 degrees. Okay, so let's calculate this number. It's 0.9 root 3 cos 30 degree plus j 0.9 root 3 sin 30 degrees plus 0.12 root 3 cos 30 degrees minus j 0.12 root 3 sin 30 degrees. Okay, you take the real part and imaginary part separately. So this in this VAB, real part may come as 1.53. Real part may come like 1.53 in per unit form. Imaginary part will be plus J 0.675 per unit. We calculate this in magnitude and angle form. Means in the polar form, if you write 1.672 will be the magnitude. Angle of this will be 23.82 degrees per unit. Okay. Real part is 1.53, imaginary part is 0.675, magnitude 1.672, angle will be 23.82 degree. This is a line-to-line voltage VAB in per unit form. Line-to-line voltage VAB in per unit form. Okay. Yeah. Now you have to convert this line-to-line voltage into absolute form, means kilovolts. You have to convert this number into kilovolts. With what base you multiply this one? With what base you have to multiply this one? Is it per phase base or line-to-line voltage base? Per phase or line-to-line? Yeah, somebody is saying correct and somebody is saying wrong. Again, you should think in the similar way. Just have a look here, for example. Look all of you. Look. VAB kilovolt equal to VA kilovolts minus VB kilovolts. VAB kilovolts equals to VA kilovolts minus VB kilovolts. What do you mean by VA kilovolts? That is nothing but VA per unit into V base per phase. Just now in the previous problem we have written. VA kilovolt is nothing but VA per unit into V base per phase minus what is VB kilovolt? VB per unit into again V base per phase. Again you should say V base per phase. You take this V base per phase common. Then obviously VA per unit minus VB per unit multiplied with V base per phase. So already we calculated that VA per unit minus VB per unit till now. Already we calculated the VA per unit minus VB per unit till now. And that you multiply with V base per phase in order to get that VAB in kilovolts. Okay. Tell me all of you, with what base you have to multiply this VAB value? You should multiply that with the V base per phase. All of you understood? Whoever is said line to line. Singham, Mamata. Mamata, have you understood? And Muhammad Faizanuddin, have you understood this? What I said? Vishnu. Yeah. So I will be moving ahead to calculate the number. So VAB in kilovolts, nothing but per unit value 1.672 magnitude. Angle will be it's 23.82 degree. 23.82 degree, and this multiplied with V base per phase means 11 by root 3 in kilovolts. 11 by root 3 in kilovolts. Okay, so you calculate this value. How much? 1.672 into 11 by root 3. 10.618. Only magnitude will change. Angle will be remain same. 10.618. Angle will be 23.82 degree kilovolts. Angle will be 23.82 degree kilovolts. Okay, that's it. So what we have learned from this problem, that we have to recall actually. That we have to recall. One simple blind rule. If you are converting per unit quantities of unbalanced system into absolute, per unit quantities in unbalanced system into absolute form, better to use a per phase base values only. Better to use the per phase base values only. Maybe per phase base voltage as well as per phase base apparent power you have to use. Okay, and Yeah, how to convert into polar form? Yesterday I have given some exercise, right? You should take square root of real part square plus imaginary part square. That's the magnitude. The angle will be tan inverse of imaginary part by real part. That you might have studied even in complex numbers. Okay, listen here. Now, for more clarity, to get a bit more clarity, I will be moving to one example with respect to balanced system. I will be thinking about only balanced system now. Look here. I'm taking the heading as balanced system. Balanced system. Okay, observe here. Observe. At a bus bar, voltage magnitude is I said the heading already, balanced system. Okay, at a bus bar, voltage magnitude is 0.95 per unit. Voltage magnitude is 0.95 per unit. Base voltage is equals to 132 kV line to line. Base voltage is equals to 130 kV line. Just look at the statement what I am saying. Just look at the statement what I am saying you. Listen. See, balanced system only, balanced system. Bus bar voltage is saying 0.95 per unit. What do you mean by that 0.95 per unit in the data given? Is it per phase per unit value or line to line per unit value? Is it per phase per unit value or line to line per unit value? Anybody? Which per unit value? Let's assume per phase per unit. Why to take that as line to line? That may confuse you. You consider that as per phase per unit only. Per phase per unit value. So, with effect of that, listen, with effect of that, I will take 0.95 per unit as phase A voltage. Okay, let V phase per unit magnitude. Magnitude of phase voltage per unit is 0.95 per unit. Not only that, phase A voltage I will assume as 0.95 at an angle 0 degree, means phase A voltage we are taking as the reference. Phase A voltage we are taking as reference. Okay. What is phase B voltage? 0.95 magnitude only. Balanced system, no? Balanced system, that's why all the three phases voltages will have same magnitude, 0.95. But angle if you calculate, it will be minus 120 degree you get in per unit. Following all of you. Now, listen here. Now, what is that VAB value? VAB per unit is how much? VAB in per unit form if you do, it is nothing but phase A per unit voltage minus phase B per unit voltage. Phase A per unit voltage minus phase B per unit voltage. And that is 0.95 at an angle 0 degree minus 0.95 at an angle minus 120 degree. Okay, you calculate that magnitude value and associated angle. Calculate that magnitude value and associated angle. That may come like 0.95 into root 3. Angle will be plus 30 degrees per unit. Plus 30 degree in per unit form. Like this you will get. And this if you multiply with what base? What base you have to multiply this one? Anybody? With what base you have to multiply this one? V base per phase, na? You have to multiply this with V base per phase. Means you have to take 130 kV by root 3. Root 3 will be cancelled, right? Root 3 will be cancelled. So I will write in the next slide. VAB in kilovolts is nothing but 0.95 root 3 at an angle of 30 degree multiplied with V base per phase means 130 kV by root 3. So 0.95 root 3 at an angle 30 degree into 132 kV by root 3. You take up only magnitude, forget about the angle for time being. You take up only magnitude here. So VAB kilovolts is equals to 0.95 into 132 kilovolts. 0.95 into 132 kilovolts. Okay. 0.95 into 130 kilovolts. What is that 0.95? What's that 0.95? That is simply voltage per unit, right? Whatever the voltage is said in per unit form, that's 0.95. So this you can write it as simply voltage per unit value given in the data. And what is 130 kV? What is 130 kV? V base line to line. V base line to line. V base line to line. Please kindly understand the conclusion now. With respect to balanced system. With respect to balanced system. This is one conclusion you can take. Second one, what is the value of VA in kilovolts? Means phase A voltage in kilovolts. Per unit value already have 0.95. Per unit value we have already 0.95 into per phase base voltage you should take. So 130 kV by root 3. Means this VA value in kilovolts is nothing but per unit voltage into voltage base per phase number. Per unit voltage into voltage base per phase number. Okay. Per unit voltage multiplied with the voltage base per phase number. Yeah, some of you may have some confusion. So from this point, particularly in case of balanced system, listen please. Particularly in case of balanced system, listen. Particularly in case of balanced system, if you said simply voltage magnitude is 0.95 per unit, voltage magnitude is simply he said 0.95 per unit. Then if you multiply that per unit voltage with the line-to-line voltage base, if you multiply that per unit voltage with that line-to-line voltage base directly, you will get that line-to-line voltage absolute number. You will get that line-to-line absolute number. Okay. If you multiply that per unit voltage, with the per phase base, you are going to get the per phase kV. Means per phase absolute voltage. Yeah. Have you understood this? Please tell me. So from this point, what I am going to consider is, particularly in case of a balanced system, line-to-line voltage per unit number, I will write the statements, kindly listen. Line-to-line voltage per unit number and per phase voltage per unit number, both are taken as same numbers. But whenever you are converting these per unit numbers into absolute form, we should multiply them with a respective base voltage. For example, if you want to get the line-to-line voltage, you multiply with the line-to-line voltage base. If you want to get the per phase voltage, you multiply with the per phase voltage base. This is a way how we have to understand now. Clear? All of you clear this statement? I'm writing this statement. Please listen. In case of balanced system, line-to-line voltage magnitude per unit, phase voltage magnitude per unit considered as equal. But to find V line to line in kilovolts, the per unit voltage shall be multiplied with V base line to line. And to find V phase voltage, one phase voltage in kilovolts, the per unit voltage shall be multiplied with V base per phase. Multiply this V base per phase. All of you understood this statement now? Yeah. Because you see, in case of unbalanced system, particularly unbalanced system, listen here. Stop writing, listen here. In case of unbalanced system, if I take up this VA per unit minus VB per unit, that's what you have done in earlier case also, right? You have taken that VA per unit minus VB per unit, but you are not getting that √3 factor. You are not, in case of unbalanced system, line to line voltage is not equals to √3 times of the phase voltage, right? Will not be equals to √3 times of the phase voltage. But it will happen in case of balanced system. In case of balanced system, line to line voltage equals to √3 times of the phase voltage. Whatever that √3 we have, that we are moving into base. That we are moving into base, and we are converting that base into line to line form like this. √3 cancelled, I am saying, and it's coming as line to line voltages. Yeah. All of you getting this one? Good. Clear now? Why I am taking this per unit voltage multiplied directly with the line to line voltage base to get line to line voltage in the balanced system. The reason is simply line to line voltage absolute value equals to √3 times of the phase voltage. That √3 what we have in the absolute form and √3 in the base gets cancelled out. So that we are assuming that per unit voltage will be remain same for line to line as well as the phase voltage calculations. Okay. Yeah. And the same rule, what I said here, can be applicable even for the powers also. Even for the powers also, the same rule can be applicable. Dear anonymous attendee, that's what I explained till now. Again, you are asking me how line to line per unit equals to phase per unit. That's what I explained till now. What are you doing? Are you listening to the class or not? Yeah, Vishnu Tej, I discussed that doubt many times. If you have still any doubt, you ask me in the doubt session later. Vishnu Tej. Okay. Let us think with respect to powers also in the same manner. Balanced system only I am taking that heading. Balanced system. Taking that heading. Okay, listen here. The complex power, or you say real power, no issue. The real power flow is, I'll say it is 1 per unit. Real power flow is 1 per unit. Right? And the base apparent power or base value, I write simply, is 100 MVA 3-phase. Base value is 100 MVA 3-phase. Real power flow is 1 per unit. Base value was 100 MVA 3-phase. Okay. Now again I am asking you the same question. Balanced system. Balanced system. I said real power is 1 per unit. Na? Real power flow is 1 per unit. What is that power given? Is it per phase value or 3-phase value? Is it per phase power or 3-phase power? What you want me to assume? Tell me please. 1 per unit given in the data. Is it per phase power or 3-phase power? Per phase. Good. Per phase. Per phase. So I'll write P per phase in the per unit form is equals to 1. P per phase in the per unit form is equals to 1. What is absolute value of this power? P per phase, absolute form is in terms of megawatt, nothing but the per unit voltage what we have, P per phase per unit value into S base per phase you should take. S base per phase means it is nothing but 1 into 100 by 3 megawatts. 1 into 100 by 3 megawatts. 1 into 100 by 3 megawatts. I will discuss this in different way. By this way also you can easily understand the previous thing what I said. Okay, I got the per phase power in megawatt absolute. Megawatt absolute. I want to find out three-phase absolute power. I want to find out three-phase absolute power. That is nothing but P three-phase megawatts. Megawatt is nothing but P per phase megawatt value multiplied with 3. P three-phase megawatt value is nothing but this per phase power multiplied with 3. Means what you get here. 100 by 3 is absolute power you calculated just now, and it is multiplied with 3. So it will come to be 100 only, right? Come to be 100. That 100 megawatt I will rewrite as 1 multiplied with S base 3 phase. 1 multiplied with S base 3 phase. Is it correct or not? Okay, if you are confusing with that number 1, better you take this as 0.8. I'm considering this number as 0.8 per unit. If you are confusing with 1. So you take this P phase as 0.8 per unit number, and this is 0.8 now. Okay, and you get multiplied with 3, and you have here 0.8 into 3 into, sorry, 0.8 into 100 by 3 into 3. 0.8 into 100 by 3 into 3. 3 will be cancelled out. So it will come to be 0.8 into 100 now. It will come to be 0.8 into 100. What is that 0.8 here? Real power per unit. Real power per unit. What is this 100? S base 3 phase. Following. So this, from this you can write P in 3 phase megawatt. P in 3 phase megawatt is nothing but, so simply P per unit into S base 3 phase. S base 3 phase. Okay. So from this again, what we can say is, whatever the per unit power he said in the balancer system, per unit power what he said in the balance system doesn't matter. Either you can assume that as a per phase power, or you can assume that as a 3-phase power, no issue. But if you are converting that per unit power into absolute form, we should take up the proper base. We should take up the proper base as a multiplication. For example, if you want to get per phase absolute value, multiply that per unit power with the S base per phase. If you want to get the 3-phase power absolute value, multiply that per unit power with the S base 3 phase. Following all of you, right? So I'll say in the next slide again in the similar manner, P per phase per unit, nothing but P 3 phase per unit. In the domain of per unit, per phase power as well as 3-phase power both are equal. And the same statements what I have written earlier, I am writing here. To get per phase absolute power, P per unit multiplied with S base per phase. Multiplied with S base per phase. And next, to get 3-phase absolute power, P per unit shall be multiplied with P per unit multiplied with S base 3 phase. S base 3 phase. Similar like previous. Amshi, Maya, have you understood this? Why it is P per phase? Have you understood this? So we can say that in unbalanced, to find absolute value, we need to multiply per unit with the base per phase to get any quantity like. Yes, Vaishnavi? That's your way of understanding. Whatever way you are capable to remember, you go in that manner only. Okay, good, good. Okay, I will tell one very simple question to you. Simple question to you to know whether you have understood or not. To know whether you have understood or not. Very simple. Just listen to me. Just listen to me. In balanced system, mod V equals to 0.9 per unit, comma, power P equals to 0.6 per unit. Okay. Base values are 220 kV, comma, 200 MVA, 200 MVA. Find absolute values of per phase voltage and powers. Per phase voltage and powers, comma, absolute values of three phase voltage and powers. Very simple question. Very simple. Just you can give the answers to me. Give the answers to me. What is P per phase absolute? P per phase in megawatt. What's the formula? Per unit power, what we have into S base per phase. P per unit into S base per phase. P per unit 0.6. S base per phase is 200 by 3. That's it. What is voltage per phase? Kilovolts. What is that? That V per unit into V base per phase. Yes or no? What is the V per unit? 0.9. What's the V base per phase? 220 by root 3. 220 by root 3 in kilovolts. And this is only for balance system. This is only for balance system. Next, what is the P phase? P3 phase megawatt. P3 phase megawatt. Again, you take 0.6 into 200 MVA directly. What is the V line to line in kilovolts? 0.9 into 220. Following? Right. So I can write P3 phase megawatt is nothing but per unit power 0.6. Three phase base is 200. And V line to line in kilovolts magnitude. Per unit value 0.9. Absolute value, base kV 220. Is it 0.9? Yes. 0.9 into 220 kV. That's it. Okay. In a similar way, I am taking one more example to you. One more example. In unbalanced system, in the unbalanced system, VA phase A voltage 0.85 at an angle 0 degree. Phase B voltage 0.8 at an angle minus 100 degree. Okay, per unit. In per unit. Comma. Real powers. PA, phase A real power 0.6 per unit. Phase B real power 0.3 per unit. Phase C real power 0.8 per unit. Okay. Base values 130 kV line to line, comma 100 MVA three phase. Same question. Find absolute values of BA and PA. Absolute values of BA and PA. Find absolute values of VAB and three-phase real power. Three-phase real power. It's an unbalanced system. It's an unbalanced system. What is VA absolute value? VA per unit into V base per phase. That's it. What is PA absolute value? PA per unit into S base per phase. That's it. What is VAB absolute value now? VAB absolute value. See, as VA and VB, as it's unbalanced system, you don't get equal per unit voltage for all the phases, right? You don't get equal per unit voltage for all the phases. At this time, what you have to do to get VAB absolute? First, you should find VA minus VB in per unit domain. That you should multiply with what? V base per phase. V base per phase. How to get three-phase real power absolute? Here, all the three powers are unequal. So, PA per unit plus PB per unit plus PC per unit you should take. That you should multiply with S base per phase. S base per phase. Yeah, please kindly tell me, have you understood this problem? It is by this problem, are you clear where to use a line-to-line voltage base and per phase voltage base for easiness in the calculations? So I'll write VA in kilovolt. VA kilovolts is nothing but VA per unit into V base per phase. Okay, so VA per unit number 0.85. Of course, at an angle 0, V base per phase is 220 kV by root 3. V base per phase is 130 kV by root 3. 132 kV by root 3. Okay, and PA in megawatt, nothing but PA per unit into S base per phase. S base per phase. What's the PA per unit number? 0.6. 0.6. S base per phase 100 by 3 megawatts. That's it. What is VAB kilovolts? You have to write VA per unit minus VB per unit into V base per phase. Okay, you write these numbers if you want. 0.85 at an angle 0 minus 0.8 at an angle minus 100 minus 100 degree. This multiplied with 132 by root 3 kilowatts. And PABC three-phase power in megawatt. PA per unit plus PB per unit plus PC per unit, you take up the summation into S base per phase. S base per phase. And it is 0.6 plus B power 0.3, C power 0.8. 0.3, 0.8. S base per phase is 100 by 3. MVA. Megawatts it is. Megawatts. Like this. Yeah, good. You are correct, Jitendra. You are correct. Good, Srikanth. The clarity you should get after understanding this one, you should get clarity what base we have to use at what conditions. Yeah. See, we will do one phasor diagram type problem here. We'll do one phasor diagram type problem. If you have completed, I will move to next slide to take up that problem. See, Siva Gopi and remaining people are asking me. See, base values will be remains as it is. V base per phase is nothing but V base line by root 3. Whether the system is a balanced or unbalanced one. Your operating voltages may be balanced or unbalanced. Okay, that's a different issue. Base values are independent on your system, right? Base values will not change according to your system variations. Getting copy? Whether the system is a balanced one or unbalanced one, whatever it is, V base line to line equals to V base per phase into root 3. That's it. Yeah. Next. Unit will be megawatt only, right? Real power it will be in megawatt only. Let's take one more problem. It's a previous gate examination question. By this, we will almost wind up this one. Of course, one theory concept also we have to discuss here before moving to the next chapter. You read these statements. I'm showing options in the next slide. Just here if possible. These are options. Go through it. Go through this question once. Previous gate examination question it is. Previous gate exam question. 3 identical star connected resistors of 1 per unit are connected to an unbalanced 3-phase supply. Supply is unbalanced. The load neutral is isolated. Load neutral was not connected to ground. Anyhow, that is not at all required in the solution. But still, okay. The symmetrical components of line voltages in per unit. Line voltages or line to line voltages, both will have same meaning in this chapters. Line voltages in per unit calculations are VA, B1, AB line to line voltage, 1 in the sense positive sequence. Positive sequence line to line voltage, VAB, X at an angle theta1. And VAB2 means negative sequence AB voltage, Y at an angle theta2. You see this statement. If all per unit calculations are with the respective base values, all per unit calculations are with the respective base values, comma, the phase to neutral sequence voltages are. Phase to neutral sequence voltages are. Yeah. See, let's see the solution. According to the data, he has given line to line positive sequence voltage value X at an angle theta1. Now he is asking us to know what is a VA1 or VAN1, means phase voltage in the positive sequence. He is asking us to know phase voltage in the positive sequence. Let us do the problem only with respect to positive sequence first. Later on, we will move to negative sequence. But you have this type of idea now. This type of idea. First, what voltages I have to take? Line to line or phase? Forget about problem. Forget about problem. It is easy to take first phase voltages, converting them to line to line. Because after drawing line to line, VA minus VB, VB minus VC, VC minus VA, after drawing these voltages directly, getting VA, getting VB, getting VC, difficult. Little difficult. That's why first I will take VA, VB, VC. From these voltages, we try to find what is VAB, what is VBC, what is VCA if it is required. Okay, so first we will start our analysis with the phase voltages for positive sequence, then we will move to line voltages. Okay, irrespective of the problem. Irrespective of the problem. So just I will say positive sequence here. Positive sequence. First I am showing phase voltages here. Phase voltages in the positive sequence. It is a VAN1 voltage. VAN1 voltage. phase A or VA1 also you can write for your comfort. VAN1 or VA1. Phase A positive sequence voltage. Now, phase B positive sequence voltage will be in lagging, right? Phase B positive sequence voltage will be in lagging by an angle of 120 degrees. Like this you can see. So this is a phase B positive sequence voltage VBN. Next, this angle is 120 degree. Next, phase C positive sequence voltage. Phase C positive sequence voltage. Again, it was having an angle of 120 degree with respect to phase A. Maybe like this we can say. This is the phase C positive sequence voltage VCN1, and this angle is also 120 degree. 120 degrees. Okay, just listen to the solution what I am making you. Listen to the solution. I want to find out line to line voltage. Means VAB1 we have to calculate. What do you mean by line to line voltage? VAB, phase A voltage minus phase B voltage. Whether these are balanced or not, that you tell me first. Whether these are balanced or not. Definitely, these are balanced only, right? These are balanced voltage only. These are balanced voltages only. Okay? Positive sequence, these are balanced. So first I will take negative of phase B voltage, negative of the phase B voltage. Then I will add that VA with minus VB, will get VAB. So I will be showing that negative of phase B voltage here. Okay, so we'll take that. In this manner, is a voltage minus VBN1. This voltage is minus VBN. Now, if we add these two together, VAN1 and minus VBN1, we'll get the required one. So I am making that addition. Kindly observe here. Okay. Kindly check this addition once. Trying to adjust it phasor diagram. So like this, we have to make that additions by parallelogram principle. We are doing that addition. Right? So observe this VAN1 minus VBN1. We are making that addition, and after doing that addition, ultimately you will get this voltage in this manner, right? And this is VAN1 minus VBN1, nothing but the voltage VAB1. Nothing but the voltage VAB1. And what is the angle between this VAB1 and VAN1? 30 degrees. Because you know, this whole angle is 120 degree I shown already, and this angle will come to be 60 degree blue color angle, and this green color angle will be obviously 30 degrees. Green color angle will be obviously 30 degrees. Getting? What voltage they have given in the question? What voltage they have given in the question? VAB1, how much? X at an angle theta1. Means this VAB1 voltage is X at an angle theta1. This is in per unit domain. Per unit domain. How is VAN1? How is VAN1? Magnitude of VAN1. Anybody please tell me? Magnitude of VAN1. Magnitude of VAN1. Is it X or X by root 3? Is it X or X by root 3? See, if it is absolute value, it will become by root 3. If it's absolute value, it will become by root 3. So as it is a what we call per unit number, we should consider this as X only, right? We should consider that as x only. But how is the angle? It will be lagged by an angle of 30 degrees. It was lagged by an angle of 30 in the sense theta 1 minus 30 degree in the per unit domain. For your clarity, if you want to write this x, what I have taken in case of phase is on V base per phase. It is on base voltage per phase. And whatever the x value we have taken here in VAB1, this is on the base value of V base line to line. That's on the base value of V base line to line. Okay? Per unit it is same. Again, somebody is asking me, sir, in the question they said unbalanced, right? They said it is unbalanced. Unbalanced. That's why we have both positive sequence and negative sequence. It's an unbalanced system. That's why we have both positive and negative sequence. If you think about only positive sequence, it is balanced, right? If you think about only negative sequence, it is balanced. And if you combine both, the resultant system is unbalanced. We don't know about it right now. He didn't ask the question with respect to the original system. He's asking the question with respect to only positive sequence and negative sequence. Yeah, next. Let's take the negative sequence. Negative sequence phasor diagram. Quickly. Negative sequence phasor diagram I am taking up. Negative sequence phasor diagram. Again, first I will draw VAN2, VBN2, VCN2. These voltages I will draw. Then I will take up the line to line. So let's say this is the phasor VAN2, let's say. VAN2. Now I am showing VBN2 here. Will be shifted by an angle of 120 degree. Like this, we are showing it is VBN2 and VCN2 I am showing now. Right. So this is the voltage VCN2. Now you take VAN2 minus VBN2 as VAB. So negative of this B I have to consider now. Negative of this B we have to consider. Yeah. So this is that minus VBN2 voltage. Minus VBN2 voltage. And then you add the VAN2 minus VBN2 together, we'll get VAB2. VAB2 you'll get. I'm doing that addition by parallelogram principle. Okay. So let's this addition. Right. So finally, you will get that VAB2 something like this. VAB2, so which is VAN2 minus VBN. And this angle, if you calculate, similar to the previous phasor diagram, and it will be again 30 degrees. So in previous problem, absolute value in per unit of light and phase are not came equal. Why? Absolute value in per unit of absolute value in per unit. What's the meaning of that? Absolute value in per unit. What's the meaning of that? So VAN1 X, not X by root 3. How? That's what we explained earlier also, Mr. Vignesh. That's what we said earlier also, right? Vignesh. In case of a balanced system, per phase voltage per unit value, line to line voltage per unit value are treated as equal on their respective base values. On their respective base values. The respective base values means if it's a per phase voltage, calculated on the per phase voltage base. If it's a line to line voltage, calculated on the line to line voltage base. That's why per unit voltages will come equal, but line to line per unit value taken on the line to line voltage base, per phase per unit value taken on the per phase voltage base. Okay, fine. See, in the problem, he said line to line VA-B2 as Y at an angle theta 2 in the per unit form. Y at an angle theta 2 in the per unit form. What is VA into now? What is VA into? Magnitude will be Y only. Magnitude will be Y only, but it is leading by an angle of 30 degree. So it will be theta 2 plus 30 degree in the per unit form. Theta 2 plus 30 degree in per unit form. Again, same comment you have to make here. This Y, particularly VAB to Y, that Y is on V base line to line. V base line to line. And this Y is on V base per phase. This Y is on V base per phase. Magnitude only I am saying you Uravukanda Satish. Magnitude. You multiply with per phase voltage base, you get magnitude of phase voltage. You multiply with line to line voltage base, you get line to line voltage magnitude. Okay, so what's your answer from the options given? X at an angle theta 1 minus 30 degree, Y at an angle theta 2 plus 30 degree. Only one option is matching to that, that is option B. Option B. See, remaining options also there. He has taken x by root 3, y by root 3, x by root 3, y by root 3. They don't confuse you. They don't confuse you. But still by root 3, if you look, you might fall in a trap to select this answer. But angles will give a clear discrimination in the options. Angles will give clear discrimination in the options. For example, you see x by root 3, theta 1 minus 30 degree, y by root 3, theta 2 minus 30 degree they have given. But what is the angle? Theta 2 plus 30 degree. Okay, but anyhow, they have mentioned this statement clearly. We should consider the per unit calculations on their respective base values. Yeah. So the angle how you are taking VA and you go through the angles, Rekha. I already explained in this diagram about angles. Same angles you should consider here also. Again, you are asking me to explain the same thing. Repetitions. This is 120 degree total. Right? And this angle will be 60 degree, obviously. And this is half of that 60 degree, which is 30. Okay, done. See, till now we discussed about symmetrical components. Symmetrical components. Now I'm going to give you steps to be followed. Steps to be followed in the analysis of an unbalanced system. Steps to be followed in the analysis of an unbalanced system. Yeah. So next heading I am giving here. Steps to be followed in the analysis of unbalanced system. Unbalanced system. See, actually, we introduced our symmetrical components and all in the view of the unbalanced system analysis only, right? We introduced the symmetrical components and all in the view of the unbalanced system analysis only. Now we are going to think about what are the steps to be followed. Yeah, let me write each and every step and then I will explain about it. Step number one. Step number one. Convert given ABC components of voltages and currents into symmetrical components by using equations what we studied. Okay, convert ABC components or ABC, no need to write components, voltage and currents. ABC, voltages and currents into 0, 1, 2 means symmetrical components, voltages and currents. Voltages and currents. First step is this. Second step. Obtain some relation or get some relationship between symmetrical components of voltages and currents. You will get some equations, right? VA0, VA1, VA2, IA0, IA1, IA2. You will get some equations. Get some relationship between voltages and between currents. Get the relationship between symmetrical components of voltages and currents. Voltages and currents. Get the relationship between symmetrical components of voltages and currents. Okay. Next thing. Third one I am saying, construct positive sequence, comma negative sequence and zero sequence Thevenin equivalent networks with respect to the point of unbalance. Right? I will discuss about that statement also. Construct positive, comma negative and zero sequence Thevenin impedances, Thevenin networks with respect to the point of unbalance. Okay. Next, after constructing these sequence networks, Thevenin networks, give connection among these three networks, positive, negative, and zero sequence networks. We have to give connection among these three by following the relations what you got in the step. Okay. Yeah. So fourth one, give connection between sequence networks by following relation obtained in step. By following the relation obtained in the step 2, you have to give the connection among these sequence networks. After giving that connection, simply what I say is do network analysis, apply KVL, KCL on that connected network, find out sequence components of voltages and currents as some numbers. Okay. So do network analysis and find 0, 1, 2 means sequence components, voltages and current values. Voltages and current values. So after getting this one, finally, after getting this 0, 1, 2 voltages and currents, you convert these values back into ABC. Okay. Convert 0, 1, 2 voltages and currents into ABC voltages and currents. ABC voltages and currents. ABC voltages and currents. Clear? So these are the various steps to be followed. I said you already, I will explain these steps by taking some diagram. See, in the previous problem, even though they have not mentioned it as respective base values, what is the meaning of proceeding with unbalanced system there? Right? Already we divided that unbalanced system into two balanced, positive sequence and negative sequence. We have to do separately. You no need to do analysis on the unbalanced system there. We have to do on the positive sequence and on the negative sequence. That results we have to combine. That is the result of the unbalanced system analysis. Okay, next. Let's take one simple network here having number of operators, generator, line, transformer. Okay, just look here. This is one generator we have, and this is a transformer and one transmission line wire. And these are buses. You take 1, 2, 3 buses. Listen, please, listen. You assume that it's operating at no load. You assume that it's operating at no load. Means you don't have any currents. You don't have any currents in the phase A, phase B, phase C right now. Okay. Listen, all of you, listen. At this bus, you have 3 wires, right? Phase A wire, phase B wire, as well as a phase C wire. At this bus 3, we have 3 wires actually, physically speaking. Phase A, phase B, phase C. Phase A, phase B, phase C. Initially, all the 3 wires are carrying 0 currents. Now, unfortunately, I had a single line to ground fault on the phase A conductor. Phase A to ground fault was active. Even after getting the fault on phase A to ground, still B current will be 0. C current is also 0. B current is 0. C current is also 0. But as a conductor is grounded, as a conductor A is getting grounded, definitely it will carry some current, which you use to call as fault current sometimes. Okay, listen please, listen carefully what I am saying you. So if you check the phase currents now, phase A current IA, phase B current 0, phase C current is also 0. These are the phase currents. What are the phase voltages? What is VA value? A is getting grounded, right? If A is getting grounded, VA value will turn down to 0. What is VB? It's not grounded. So VB is non-zero. We don't know. VB is non-zero. We don't know. What is VC? Also we don't know. Following? Yeah. Now, system is balanced or unbalanced? Tell me quickly. Whether the system is balanced or unbalanced? Unbalanced only. System is in the unbalanced state. As if the system is in the unbalanced state, we have to apply symmetrical components by following these steps. What's the first step we have here? Convert ABC voltage and currents into symmetrical components. So first you have to convert these currents into symmetrical components. You write the matrix. We have IA0, IA1, IA2. These are sequence components of currents equal to 1 by 3, 1, 1, 1, 1 alpha alpha square, 1 alpha square alpha into IA, IB, IC. What are these B and C currents? Zeros. B current is 0. C current is also 0. IA value you keep as it is. Okay. Now, what you will get this IA0 from this matrix multiplication? What you get IA0 from this matrix multiplication? 1 by 3, 1 into IA, 1 into 0, 1 into 0. So IA0 is nothing but IA by 3. What is IA1? 1 by 3, 1 into IA, alpha into 0, alpha square into 0. So IA1 value is also IA by 3. What is IA2 value? IA2, 1 by 3, IA 0, 0 means it's again IA by 3. Let's think about only currents, voltage and all we will discuss later. First think about currents. IA0 value, we get something, IA1, IA2. What's the relation? What's the relationship between these currents? That is, the three sequence currents are equal. I can say that the three sequence currents are equal. That is the relation. That's a step number. What is the step number? Step number 2. Get the relationship between the symmetrical components of voltage and currents. That's what we got here. Maybe currents relation we got. What's the next step we have? Construct positive, negative, and zero sequence Thevenin networks with respect to point of unbalance. With respect to point of unbalance means in our analysis, bus 3 fault location is a point of unbalance. So with respect to bus 3, we should construct positive sequence Thevenin network, negative sequence Thevenin network, zero sequence Thevenin network. See, in the construction of the positive sequence Thevenin network, first we should know how to represent generator in the positive sequence network, how to represent transformer in the positive sequence network, how to represent line in the positive sequence network. By representing that, we should find out Thevenin impedance with respect to bus. Clear? Similarly, negative sequence network construction we should do. Generator representation, the negative sequence, transformer representation, line representation we should take, and we have to take up the negative sequence Thevenin network. Similarly, zero sequence also. After getting these three networks, positive, negative, and zero sequence networks, what is our next step? What's our next step? Step number 4. Give the connection between the sequence networks by following the relation obtained in the step 2. Step 2 relation is what? All the three sequence currents are equal. Now, what you have to do simply is, as all the three sequence currents are equal, connect three sequence networks in series. Connect three sequence networks in series. By that way, we are capable to satisfy this statement. After doing that, what's the next step again? What's the next step? Do network analysis. Means you should apply KVL, KCL on that network, what we got, resulted network. Find out sequence voltages and currents. After getting those sequence voltages and currents, numbers, convert them back into ABC voltage and currents. Convert them back into ABC voltage and currents. This is a procedure what we have to follow in the analysis of unbalanced system by using symmetrical components. Yeah. Now I am asking one very, very simple question to you. If you have understood this, are we clear about step 1? Step 1, are you comfortable to do or not? Yes, we have equations. We have many equations so that we are comfortable to do the step number 1. Step number 2, getting that relation depends upon the unbalance. Whatever the unbalance you want me to study, that will decide the relation. But step 3, we should be careful now. We have to study that step 3. Means how to represent each apparatus in the positive sequence network form, negative sequence network form, zero sequence network form, and how to construct the positive, negative, and zero sequence Thevenin networks. That we have to study. I think remaining steps also clear for us. Giving the connection depends upon the relation. Network analysis, it's a regular process what you do. Last one, converting the symmetrical components back into ABC. These equations also we have exercised already. Following all of you. So what step we have to concentrate now? What step we have to concentrate mainly? Step number 3. So our next chapter is dealing with that step number 3, so-called construction of the positive, negative, and zero sequence networks. Clear? So I'm moving to next chapter. This chapter will end at this point. Yeah. Sequence networks construction. Chapter number 3. Sequence networks construction. Yes. See, listen. I will explain that unbalanced system again in the doubt session. Listen here. See, from this chapter, first we have to think about generator representation in the sequence networks. Next, transformer. Next, we have to think about line. But before moving to the generator and transformer, generally we used to get star winding and delta windings, right? In the generator as well as in the transformer, sometimes you get star, sometimes you get delta. First, we should be familiar about these windings. How to represent star winding in the positive, negative, zero sequence networks form. Similarly, delta winding. That we'll learn first. That we'll try to learn first. With the basic of that, we will move into what we call generator and transformer. Yeah. So let's take up the first heading in this. First heading in this one. Sequence networks for sequence networks for star winding with grounded neutral, of course, with grounded neutral of Zn impedance. Means the neutral of that star winding was grounded with an impedance of Zn. That's the idea. So I'll show the star winding. See, this star winding may be for alternator, maybe for transformer. You don't think about that apparatus name right now. Just I'm showing one star winding like this. These are terminals ABC, phase terminals ABC, and this is a neutral which is connected to ground with an impedance of Zn. Neutral connected to ground with an impedance of Zn. And the terminal voltages of these star winding I am showing as VA, VB, and this is VC. And currents I am showing IA, IB, IC. IB, and this C current is IC, like this way. Okay, first. First thing, listen. See, impedances of these windings I am going to talk first. Impedances of these windings. For positive sequence current flow, these windings may offer an impedance of Z1. So I'll call simply Z1 as a positive sequence per phase impedance of the winding. Positive sequence per phase impedance of winding. Okay, I will explain again. Z2 I am taking. Z2 notations only. Maybe Z1 equals to Z2 or may not be equal. That depends upon the apparatus what we discuss later. But for time being, I'm showing the difference in the notations. Okay, Z2 is a negative sequence per phase impedance of the winding. Negative sequence per phase impedance of the winding. Per phase impedance of the winding. Similarly, Z0, that is the zero sequence per phase impedance of the winding. Zero sequence per phase impedance of winding. Zero sequence per phase impedance of the winding. Z1, Z2, Z0. Okay, next thing. Listen. Phase A voltage or ABC voltage are unbalanced. Currents IA, IB, IC also unbalanced. Okay. So I am writing these voltages and currents in terms of symmetrical components. In terms of symmetrical components means VA I will be writing as VA1 plus VA2 plus VA0, VB, VB1 plus VB2 plus VB0, VC, VC1 plus VC2 plus VC0, and IA similarly. Positive sequence, negative sequence, and zero sequence current summation. B current. IB1 plus IB2 plus IB0. And the C current is coming like IC1 plus IC2 plus IC0. Like this, we get the sequence currents. Written simply in terms of symmetrical components. Okay, so I want to take up this. See, if you are doing positive sequence analysis, I am explaining this one briefly. Just listen first. Just listen. All of you stop writing. All of you stop writing. Just listen. Symmetrical components we can't apply on impedances. No, we should not apply that on impedances. That's what I am saying you. But you said Z1 positive sequence impedance, Z2 negative sequence impedance, Z0 zero sequence impedance. What is Z1? Each winding will offer an impedance of Z1 for the flow of positive sequence current. That's the meaning. What is Z2? Each winding will offer an impedance of Z2 for the negative sequence current flow in the winding, IA2 current. What is Z0? Each winding will offer an impedance of Z0 for the zero sequence current. These are the impedances offered by this winding, for different sequences of the current flow. For different sequences of the current flow. Okay? Is it clear, Manish Kumar? Okay. Listen. First, if you are doing positive sequence analysis, what you have to take is voltages as positive sequence, VA1, VB1, VC1. VA1, VB1, VC1 you should take. Okay. And currents, IA1, IB1, IC1 we have to consider. IA1, IB1, IC1. Impedances will be Z1, 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 but this neutral impedance will be remains constant. Neutral impedance Zn value will be remains constant irrespective of the sequence what you are studying. By making a small assumption that no mutual linkages, listen my words please, no mutual linkages between this neutral impedance and the windings. So that irrespective whether windings are carrying some currents, positive sequence, negative sequence, zero sequence, whatever may be the nature of the current flow in the windings, it may not show any effect on the neutral impedance value. Okay? Yeah. So I'm writing that statement also for you. Assume that there exist no mutual linkages. No mutual linkages. Mutual linkages between neutral impedance Zn and phase windings. And phase windings. That implies Zn will be constant. Will be a constant value. Irrespective of sequence of current, neutral impedance will be remains fixed number. Okay, next thing. Let's continue like this. First, before moving to positive, negative, and zero sequences, I want to say some more thing here. As all currents are going out, IA, IB, IC, let's take this neutral current in this direction, IN. Taking the neutral current in the direction IN. That itself is a ground current also, right? That itself is a current flowing in the ground. Already I said in the yesterday problem. Neutral current, ground current, both will be same. What is that? Neutral current formula. neutral current or ground current formula. Neutral current, or you can call it as ground current formula IN. Apply KCL at this node. If you apply KCL at this node, obviously IA, IB, IC, three currents are outgoing. So neutral current is nothing but summation of the three phases currents. IA plus IB plus IC. Then if you take this summation, what you will get? What you will get this summation? Tell me. That is nothing but 3 times of the zero sequence current. 3 times of zero sequence current. You make that summation. IA1 plus IB1 plus IC1, 0. IA2 plus IB2 plus IC2, 0. IA0 plus IB0 plus IC0. That is 3 times of zero sequence current. 3 times of zero sequence current. Always neutral current or ground current is nothing but 3 times of the zero sequence current. This equation is not going to be changed irrespective of the system. This equation is not going to be changed. Okay, grounded system, particularly for grounded system. Okay, next thing. What is this neutral voltage value? Actually, we used to consider ground as a reference plane for all the analysis. We used to consider ground as a reference plane for all the analysis, and we'll take that ground voltage as 0. Ground is our reference. So obviously this ground potential VG is equals to 0. Then what is this neutral potential? What is it neutral potential? Simple. You write current equation. You write current equation IN, which is nothing but 0 minus Vn by Zn. From that we try to get the neutral voltage equation. Okay. So at that neutral point, we can write. At that neutral point, you can write. Yeah. So you can write here 0 minus Vm by Zn, voltage difference by Zn, is a neutral current IN. So that neutral voltage will come to be minus IN into Zn. Okay. Else that IN you can replace with 3 times of IN0 into Zn. Most of the times they used to ask magnitude of the neutral voltage only. Magnitude of the neutral voltage. After calculating this, just pick up only magnitude value. So this is the expression for the neutral voltage. Expression for neutral voltage. Minus IN into Zn, else you write minus 3 IA0 into Zn. Next thing. Let's take up a positive sequence first. Positive sequence network analysis. So I'm taking in the next slide. Yeah. So positive sequence network. Positive sequence network. Just repeat the 3-phase diagram, star winding diagram. Like this. So these are the outgoing terminals, as we said, AB, C, and this is a neutral which is grounded with an impedance of Zn. This neutral is grounded with an impedance of Zn. And already I said ground voltage is 0. Already I said ground voltage is 0 as a reference. Next thing. For positive sequence analysis, you know, these voltages are VA1, VB1, VC1 voltages. Currents. IA1, IB1, IC1 currents. IA1, IB1, IC1 currents. What are the impedances of the windings? Z1, Z1, Z1. Impedances of the windings are Z1, Z1, Z1. Fine. How much is current flowing in the neutral now? How much is the value of current flowing in the neutral? Anybody? What is the current flow in the neutral? Yeah? 0. Current flowing in the neutral will be 0. 0. 0. Because if you apply KCL here, IA1 plus IB1 plus IC1, that is the neutral current. As these are balanced currents, positive sequence currents, right? These are balanced currents. Sum of the three equals to 0. So neutral current will be equals to 0 obviously. Okay, next. I'm sorry, this is Z1. It's not Z2, it's Z1. All are Z1 only. All the values are Z1. Okay, next thing, listen. See, if this neutral is carrying 0 amount of current and 0 into Zn, that will be also 0, then how much is your neutral voltage here? In this problem, your neutral voltage is also equals to 0. Neutral voltage also equals to 0. Tell me now, whether the system is balanced or unbalanced? Whether the system is balanced or unbalanced? Balanced. As the system is balanced, can we do per phase analysis on this one? As the system is balanced, can we do per phase analysis on this one? Yes, we can do the per phase analysis on this. Per phase analysis means simply you take only phase A network out. You take only phase A network and do network analysis on that. That itself is a phase A result. The same result we can extend for phase B as well as for phase C also. See, as this neutral voltage itself equals to 0, I'm going to consider this per phase network with a reference of neutral. With a reference of neutral, we are going to consider this phase network. Means my interest is to tell you whatever the positive sequence voltage VA1 we have, that is measured with respect to neutral reference. Measured with respect to neutral reference. Okay. Some people may have a confusion. I will tell you. I will try to avoid that confusion to you. Just I am asking one basic question. Simply I have shown one conductor to you outside. One conductor I have shown you outside. I am asking you measure the voltage of the conductor. Measure the voltage of the conductor. With respect to what you measure? Is it with respect to neutral or with respect to ground? With respect to ground or with respect to neutral? With respect to ground. See, always, listen please, listen. Always ground potential is equals to 0. Ground potential is equals to 0. Neutral potential may or may not be 0. Neutral potential may or may not be 0. But always ground potential equals to 0. So strictly speaking, we have to draw the per phase network. We have to measure the voltage with a ground reference only. But in case of balanced system like positive sequence, not only ground voltage, neutral voltage is also equals to 0. That's why I am considering neutral as a reference. Neutral as a reference. Because this Zn is carrying 0 current, it is not at all effective to me. So by removing the Zn from our view, I am taking only neutral as a reference here. Okay. So I am drawing per phase network for this. Per phase network. So this is A, and here you have Z1, and I'm considering only neutral as a reference. And you know positive sequence voltage measured with respect to neutral reference. And this current, you know, IA1 here, and this voltage Vn is equals to 0 for the positive sequence. Neutral voltage is equals to 0 for the positive sequence. Okay. Now, just you apply KVL to this loop and try to write the equation for VA1. Try to write equation for VA1. It may come like minus IA1 into Z1. You apply KVL for this. Right? 0 minus VA1 by Z1 equals to IA1. Because current is going out like this. 0 minus VA1 by Z1 equals to IA1. So VA1 equals to minus IA1 into Z1, you can see. So this is about the positive sequence per phase network construction. Next, I'll take negative sequence network in the similar manner. Let's move. to the next slide. Okay. So I'm moving to the next slide. So I'm giving that heading as a negative sequence network. Negative sequence network. Let's draw same three-phase star connected winding with that neutral grounded. Right. So this neutral is grounded with an impedance of Zn. And ground potential equals to 0. These are the outgoing terminals. I am showing ABC. Voltages I am keeping first. It is VA2, VB2, PC2, currents IA2, IB2, IC2. Okay, and these sequence impedances Z2 na negative sequence. So each winding will offer an impedance of Z2 for negative sequence current. Z2 for negative sequence current. Okay, next thing. What is this neutral current? 0. Because summation of IA to IB to IC2, that will be 0, right? Summation of IA to IB to IC2, that will be 0. Neutral current is 0. And neutral current is 0, that 0 into Zn is 0. So obviously this neutral potential is also equals to 0. Neutral voltage is also equals to 0. Okay. So strictly speaking, as I said earlier, you have to take ground as a reference. Ground as a reference. But in the negative sequence network analysis, neutral voltage is also coming as 0. So let us take neutral as a reference to the per phase network construction. Okay. So I am considering neutral as a reference in the per phase network construction. So that whatever the VA2 we have here, I can say this is measured with respect to neutral or measured with respect to ground. Both will give same meaning. Both will give same meaning. But generally, they use to say negative sequence voltage is measured with respect to neutral itself. Okay. So I'll draw per phase network of this. Means only phase A network I will repeat here. Per phase network means phase A network I will repeat. So it's a terminal A. And you know this impedance is Z2. Okay. So this is a neutral voltage 0. And this point voltage, negative sequence voltage, I will show it is VA2. Current here is IA2. Okay, VA2, IA2. And you can write that VA2 as negative of IA2 into Z2 with the help of that KVL application. The help of KVL application. Okay. Next thing. Zero sequence network will draw in the similar manner. ACB negative sequence only. Yes, Revat Kumar. What's doubt in that? ACB negative sequence only. Will you change physically winding if you are changing current? Tell me, Mr. Urokanda Satish and Revant Kumar, will you change winding itself if you are changing sequence of current? Same in both except notation. Yes, that's it. That's it, Aishwarya. Next, zero sequence network. Let's take zero sequence network. Zero sequence network. Same again, star connected winding we have. like this. And these are outgoing terminals. We are showing ABC. Right, ABC outgoing terminals, and this is a neutral point grounded with an impedance of Zn. Okay, so voltages VA naught, VB naught, VC naught here, and currents will be IA naught, IB naught, IC naught, and winding impedance Z naught for negative sequence. Each winding impedance is Z naught here, Z naught. That's your view of taking Kushal. Neutral current is going in, coming out. That's your view, how you are going to consider. So I am taking current going upward. Why it is so means ABC currents are going out. Okay. So this is a neutral current IN. How much is it neutral current IN now? That will be 3 into IA naught. IA naught, IB naught, IC naught, all the three are equal. That is equals to 3 into IA naught. It won't be 0 now. So neutral current will exist in case of zero sequence analysis 3 times of the zero sequence current. And how much is your neutral voltage? Neutral voltage is definitely non-zero in this case. Neutral voltage is definitely non-zero in this case. But always ground potential equals to 0. But always ground potential will be equals to 0. Now you tell me, this is the node voltage of A, that is VA naught, measured with respect to what? Is it with respect to neutral or ground? With respect to ground. See, in the earlier case also, VA1, VA2 measured with respect to ground only. But as a neutral voltage is 0, we have taken neutral as a reference. But here, neutral voltage may or may not be 0. So you should consider this ground as a reference all the time. Means I can say this VA naught voltage is measured with respect to ground. Okay. Now simply you try to find out equation for this VA naught. Try to find out the equation for VA naught. You go in some direction. Maybe this direction only I will take. Positive to negative VA naught voltage. Then as a current is going up, neutral current is going up. This is positive symbol and this will be negative symbol. How much is the drop? IN into Zn. And we have to circulate. We have to move our loop in this direction. In this direction. IA naught current is going up here. Because this branch current is only IA naught. Neutral current is 3 into IA naught. Phase A branch current is only IA naught. And this will create a drop like plus minus IA naught into Z naught. And you have to sum up all the 3 voltages and that will be equals to 0. That is a zero sequence phase A equation. Zero sequence phase A KVL equation. Okay. So applying KVL for phase A loop. KVL for phase A loop. So plus minus VA naught. Again, we have plus minus IN into Zn. Again, you have plus minus IA naught Z naught. That is equals to 0. And if you write down this VA naught value, so it will come minus IN into Zn minus IA naught into Z naught. And what is that IN we have? 3 into IA naught. So it will come minus 3 IA naught into Zn minus IA naught into Z naught. IA naught into Z naught. Okay. So from this, you take that minus IA naught common. You will get here Z naught plus 3 Zn. Minus IA naught common. So you'll get Z naught plus 3 Zn. Okay. See, if you look at this previous equation, VA1 or VA2, whatever it is. For example, VA1, if you look at VA1, for that VA1 we have written minus IA1 into Z1. Minus IA1 into Z1. See, your VA naught equation also looking same, right? Your VA naught equation also looking the same. But here you have minus IA naught into Z naught plus 3ZL. In place of IA1, you have IA naught here. In place of Z1, you have Z naught plus 3ZL. Means, how this zero sequence circuit will come for you? Simply, we have an impedance of Z naught plus 3ZL. We have an impedance of Z naught plus 3ZL. Terminal voltage is VA naught. Current flow is IA naught. Clear, right? So if you convert this equation into network form, so equivalent network or phase A network for zero sequence, phase A equivalent network, or sometimes you can say per phase network also, no issue. Phase A network means per phase network also you can say. Simple. Total impedance I should keep Z0 plus 3ZL, showing here. This is Z0 and this is 3 times of ZL. Okay, and this is ground. With respect to ground only we have done that KVL application. And this voltage as a whole I am showing as VA naught. That's the voltage VA naught. Current flow in this circuit is IA naught. That's why we have written here VA naught equals to minus IA naught into Z0 plus 3Z. Vaishnavi, if you are changing or if you are doing negative sequence analysis, will you physically change the winding position in the motor? Sorry, in the generator? Will you change the physical position of winding? Huh? Okay, listen here. Next thing, just observe here, one small concept I am saying you. Current flow in this loop is IA naught. Current flow in this loop is IA naught. So I am showing this current is obviously IA naught here. IA naught is at current flow. And you have a bottom terminal positive and upper terminal negative. Okay. How much is this voltage? IA naught into 3ZN. IA naught into 3ZN is a voltage here. Now, what is this node voltage? What is this node voltage? Anybody? IA naught I will hit here. What is this node voltage? You take top terminal positive, bottom terminal negative. Top terminal positive you take, bottom terminal negative you take. How much is that voltage? That will be minus IA naught into 3ZN. Minus IA naught into 3ZN. This is the value minus 3 IA naught into ZN. And this is nothing but the neutral voltage in the original three-phase system, right? That is nothing but the neutral voltage in the original three-phase system what you have. Following means my interest is to tell you as this voltage is nothing but the original neutral voltage of your three-phase system. This point what we have itself I am going to call as neutral. This point itself we are going to notate as neutral, indicating the point as neutral voltage with respect to ground. Indicating the point voltage as neutral voltage with respect to ground. Yeah. So from this point, if you want to draw zero sequence network, this is a point here, right? This term is here. If you want to draw zero sequence network, what I should say? A to neutral, I should keep Z0, so-called zero sequence impedance of the winding, Z0. Whereas from the neutral to ground, we should keep 3 times of the neutral impedance existing in the three-phase system. 3 times of the neutral impedance existing in the three-phase system. Okay, I will write that statement. The impedance to be kept in between neutral and ground, in per phase network in per phase network, per phase zero sequence network will become or will be three times of actual or original neutral impedance. Original neutral impedance. 3 times of the original neutral impedance or actual neutral impedance. In bracket 3Z. 3Z. Okay. One more statement. Generally, positive sequence voltage, negative sequence voltage measured with respect to positive and negative sequence voltage are measured with respect to neutral reference, because neutral voltage itself equals to 0 in the positive and negative sequence. Whereas zero sequence voltage is measured always with respect to ground reference. Okay. Yeah. So next statement. VA1 and VA2 positive and negative sequence voltages are measured with respect to neutral reference. Neutral reference. In bracket you write since Vn equals to 0 for positive and negative sequence analysis. Okay, next. Whereas zero sequence voltage VA0 measured with respect to ground reference always. Ground reference. Zero sequence voltage measured with respect to ground reference. Okay, by putting a step forward, I will say one more statement here. Positive and negative sequence networks are constructed with neutral as a reference. So while you are constructing the positive and negative sequence networks, you no need to bother what you have connected between that neutral and ground. But your zero sequence network is constructed always with a ground reference plane. Okay? Yeah, that statement also I made. Positive and negative sequence networks are constructed with the neutral reference plane. Neutral reference plane. Whereas zero sequence network constructed with ground reference plane. Ground reference plane. Constructed with ground reference plane. Yeah. So have a break for 10 minutes and after break, we will see variants in this star winding. Next case study I will take up as star solidly grounded I will take. Then star isolated grounding. Then we will make some conclusion on this. Then we will move to delta winding. Okay. So 10 minutes break. Yeah. So I have resumed the audio, video, and screen. So please kindly confirm. Okay. So next I am going to take up star winding only with the solidly grounded neutral. Star winding, solidly grounded neutral I am going to consider. Next slide. Star winding with solidly grounded neutral. Solidly grounded neutral. Star winding with solidly grounded neutral. Yeah. So just I will repeat the same star winding what we have chosen earlier. It was a star winding, right? So these are ABC outcoming wires of this winding having potentials like VA, VB, VC. ABC outcoming wires having potentials as VA, VB, VC, and carrying currents as IA, IB, IC, of course. IA, IB, IC currents. And is a neutral connected to ground with zero impedance. Solidly grounded neutral in the sense neutral grounding impedance is equals to 0. Solidly grounded neutral means you should think that neutral impedance is equals to 0. Neutral to ground impedance is 0. Okay, next. Again, each winding will have a positive sequence impedance of Z1, negative sequence impedance Z2, zero sequence impedance as Z0. And voltages you can convert into symmetrical components, or you can write into symmetrical components as VA1 plus VA2 plus VA0. Similarly, B and C also you can write. Currents also IA1 plus IA2 plus IA0. Similarly, B and C currents also you can write. Okay. Anyhow, I am not writing B and C because already we have written in previous problem. So previous heading. Okay. Now you please tell me in this case, how much is the neutral current? How much is neutral current in this case? IN. Anybody please tell me the formula for neutral current? Please tell me formula for neutral current. It will be obviously 3 into I0, right? 3 into I0, obviously. Neutral current is nothing but 3 times of zero sequence current. Okay. How much is the neutral voltage VN? VN. What's the formula for neutral voltage here? That is minus IN into Zn. We have written in the previous case. So as it is minus IN into Zn, as Zn value was 0, so obviously this will be equal to 0. Minus IN into Zn, as Zn value was 0, neutral voltage will be equals to 0 in this case. Okay. Now we take positive sequence network, negative sequence network, and then zero sequence network. These three we have to consider. See, just look back to the previous thing. Positive sequence network means we will draw as it is in this manner. Look here. Positive sequence network means as it is we will draw, but this Zn we will keep as 0. Zn will keep as 0. Do we get any change in the network analysis if you are doing for positive sequence? Even if Zn is some non-zero number or Zn equals to 0, do you have any change in this per phase network? Do you have any change in this per phase network? Yes or no? No, we don't have any change in the per phase network. So that positive sequence per phase network will be as it is of previous case. Okay? Yeah. So I'm drawing directly now. Positive sequence per phase network. Positive sequence per phase network. So it will be up to neutral, we will keep that positive sequence impedance of winding Z1, and you have this voltage as VA1 and this current as IA1. So VA1 is nothing but minus IA1 into Z. Minus IA1 into Z1. That's the positive sequence network per phase. Okay, next. How is a positive, sir? How is a negative sequence network we can expect? Will it be same as previous one? For example, you see this is a negative sequence three-phase network we have drawn in the earlier case, but now in the present case, neutral impedance is equals to 0. So I will keep this Zn equals to 0. Even though you keep that Zn equals 0, you don't get any change in the per phase network, right? Three-phase network wise, you may have a change, but analysis wise, you don't get any change. Analysis wise, you don't get any change. So negative sequence per phase network will be as it is of previous one. Okay. Yeah. So I can say negative sequence per phase network. Negative sequence per phase network will be same as previous one. So it's a terminal A. Up to neutral, we have to keep that negative sequence impedance Z2. And here I am showing that negative sequence voltage VA2, which is nothing but minus IA2 into Z. Minus IA2 into Z. But there is a significant change in the zero sequence network. There is a significant change in the zero sequence network. Let us draw, at least for this one. Let us draw that three-phase zero sequence network, and I will convert that into per phase manner. Okay. Yeah. So I will show in the next slide. I will be showing in the next slide. Zero sequence network. Three-phase network I will draw first. Zero sequence network. First we have three windings in that star connection. These are ABC terminals coming out. ABC terminals coming out. And these are voltages VA0. Okay. First I have to complete this. Grounded. Zn is equals to 0. Zero sequence impedance of each winding is Z0. Voltages at the terminals are VA0, VB0, VC0. These are voltages at the terminals. Currents IA0, IB0, IC0 currents. Okay. Then you please tell me how much is your neutral current here? How much is the neutral current here? That is nothing but IA0 plus IB0 plus IC0. IA0 plus IB0 plus IC0. So it will be 3 into IA0 here. 3 into IA0. Neutral current is 3 into IA0, and neutral to ground impedance is 0. Neutral to ground impedance is 0. And of course, ground voltage is 0. Now, as we said the earlier procedure, if you are constructing zero sequence per phase network, A to neutral, we will keep that winding zero sequence impedance Z0. Whereas from neutral to ground, we should keep 3 times of Zn. 3 times of Zn. So as Zn equals 0, so the 3 into Zn, that will act as 0, obviously. Okay. Now I'll draw per phase zero sequence network. Zero sequence network per phase. Per phase network. The previous procedure I am following. A to neutral, we should keep zero sequence impedance of winding Z0. Neutral to ground, we should keep 3 times of Zn. Neutral to ground, we should keep 3 times of Zn. So, of course, as the Zn value was 0, it will come to be 0 here. Come to be 0. So, this is a value VA0. This is a value VA0. And this is a current IA0. That's the current IA0. Okay. So this is about the zero sequence network of star solidly grounded neutral. Solidly grounded neutral. Now I will extend the same thing for star winding with isolated neutral. Star winding with isolated neutral. Yeah. So if you have completed, I will move to next slide. Yeah. So I'm taking up the next slide. Star winding with isolated neutral. Isolated neutral. See, isolated neutral in the sense, neutral is not going to be connected to ground. That's the meaning. Neutral is not connected to ground means neutral to ground impedance is equals to infinite. Okay. Star winding with isolated neutral means neutral not connected to ground. Not connected to ground. Connected to ground. Or you can write that neutral impedance is equals to infinite. Or you can say neutral impedance is equals to infinite. Yeah, let me draw the three-phase diagram. Three-phase diagram once. Phase A winding. We have phase B and phase C. A, B, and this is C. Right? ABC. And it is at point neutral. And this is ground. Neutral and ground not connected together. That's what we are saying just now. And that neutral impedance is equals to infinite. Neutral impedance is equals to infinite. And voltages you have VA, VB, VC as it is of a previous one. Currents also you have IA, IB, IC. If you want to write these things in symmetrical components, sequence impedance for positive for each winding Z1, negative sequence impedance of each winding, zero sequence impedance of each winding, Z1, Z2, Z0. Okay. How will be the positive sequence network for you? How will be the positive sequence network for you? How will be the positive sequence network? It will be same. Positive sequence network will be same as the previous. Yes or no? How is the negative sequence network? That also be same. Okay. So positive and negative sequence networks will be as it is of the previous one. But you have some change in the zero sequence network. So we concentrate on the zero sequence network mainly in this. Yeah. So I'll write the statement what I said now. Positive and negative sequence per phase networks will be similar to previous case. Similar to previous case. But if you want to draw the zero sequence network, what you should do is A to neutral, we should keep Z0. A to neutral, we should keep Z0. Neutral to ground, we should keep 3 times of Zn. 3 times of Zn means 3 into infinite, that will be infinite. Okay. So zero sequence per phase network, I am drawing directly. Zero sequence per phase network. So this is a point A to neutral, zero sequence impedance of winding, neutral to ground, we should keep 3 times of Zn we said. So 3 Zn in the sense it will come to be infinite. So of course, as it is open, it is not going to carry any current. As it is open, it is not going to carry any current. IA0 value is equals to 0 because of the open circuit. Yeah, can you please tell me in this previous one, maybe original model, how much is neutral current here? How much is the value of neutral current? 0, because neutral is not connected to ground and neutral will not find any closed path here. So neutral current will be equals to 0 in this case. Okay. So IN, I am writing here, neutral current IN is equals to 0. Neutral current IN is equals to 0. Okay. So neutral current is becoming 0 means I can say zero sequence current equals to 0. but there may be an existence for the positive and the negative sequence currents in the system. There may be an existence for positive and negative sequence currents in the system, and this IA will consist only IA1 and IA2. IB will consist only IB1, IB2. IC will consist only IC1 and IC2 currents. Okay. So if the system is carrying only positive sequence components, then the system is balanced, we will say only positive sequence, then we will assume that neutral potential equals to 0. Only negative sequence components, system is balanced. At that point also we'll assume that neutral potential is equals to 0. But what is neutral voltage if the system is carrying only zero sequence current? How much is the value of neutral voltage if the system is carrying only zero sequence currents? How much is it Vn here? How much is the neutral voltage? Is it 0 or non-zero? Is it 0 or non-zero? We can't say that. We can't say. How much is that value? That value is nothing but Va0. Neutral voltage and zero sequence voltage both will be equal. Va0 and Vm are equal in this case. Yeah. Next thing. Whatever that neutral to ground impedance we are keeping now, that will show effect. Only on the zero sequence network of the system. Okay, so that neutral to ground impedance will not show any effect on the positive and negative sequence networks. Else, I can say the same statement in other way as the nature of neutral grounding. The nature of neutral grounding will show its effect on zero sequence network only. Right? So it won't show any effect on positive and negative sequence networks. It won't show any effect on the positive and negative sequence networks. Okay. Next thing. I'll write some statements here. Just tell me whether that statement is true or false. Okay. So I'm taking in the next slide. First statement I'm saying. If neutral current equals to 0, then always zero sequence current equals to 0. Is it correct statement or not? Yes, tell me please whether this statement is correct or not. Yes, this is true. Next one. If zero sequence current is equals to 0, then always neutral current is equals to 0. Is this correct or not? If zero sequence current is equals to 0, then always neutral current is equal to 0. That's also correct. That's also correct. Neutral current equals to 3 times of zero sequence current, right? IN equals to 3 into IN0. As IN is equals to 3 into IN0, if IN equals to 0, IN0 will be 0. If IN0 is 0, IN will be 0. Both are correct statements only. Any one among these two is 0, then obviously other value will become 0. Both these statements are true. Next statement I am saying. Next statement. If neutral voltage is equals to 0. neutral voltage Vn is equal to 0, then always zero sequence voltage is equals to 0. Is it true or false? Is it true or false? If neutral voltage is equals to 0, then always zero sequence voltage is equals to 0. I will show you one network. I will show you one network. This you consider. This network you consider. How much is neutral voltage in this case? Yes, even though you have some neutral current here, even though you have some neutral current, that neutral current into Zn, that is 0, right? Neutral current into Zn, that is 0. So obviously this neutral potential equals to 0 as a neutral is solidly grounded. Then neutral voltage is equals to 0 here. If neutral voltage is 0, what is VA naught? VA naught is having some formula IA naught into Z naught, right? So even though neutral voltage is equals to 0, there may not be a chance to say that the zero sequence voltage is also equals to 0. We can't say. We can't say. Following all of you, always is wrong statement. Always is wrong statement. Getting all of you? So if neutral voltage is equals to 0, that zero sequence voltage may or may not be 0. Zero sequence voltage may or may not be 0. Always, if you are writing here, that is false. That is false statement. Else, in another way, if you want to write a true statement, I'll write, if neutral voltage is equals to 0, then VA naught may or may not be 0, you write. May or may not be 0. So this you can say as a true statement. That you can say as a true statement. Okay. Other statement I am saying, other statement. If zero sequence voltage equals to 0, zero sequence voltage equals to 0, then always neutral voltage is equals to 0. Practically, I am saying this one practically. Tell me please. If zero sequence voltage is equals to 0, then always neutral voltage is equal to 0. Is it true or false? Is it true or false? It will be true. I'll tell you. Just previous we have, right? If VA naught is 0 in this circuit, VA naught is 0, then VN will be 0. Because VA naught, VN both are equal. Let's move to the previous circuit. Maybe this one, VA naught, I am saying 0. I am saying VA naught 0. Already VN is 0. That no issue here. Let's think about this circuit. See, practically in the sense, this neutral impedance may be in the nature of resistive or in the nature of reactive. Neutral impedance may be in the nature of resistive or in the nature of reactive. So that if this whole voltage is equals to 0, VA naught value 0, I am saying, whole voltage equals to 0, definitely voltage across Z naught as well as voltage across 3Zn, both values will be 0. Okay, so obviously neutral voltage will come to be 0. So if the zero sequence voltage is equals to 0, definitely neutral voltage equals to 0. But reversal is not true. Reversal is not true. Okay, yeah. So this is a true statement, but reversal is not true, what we are seeing. So these are some statements you can see. Else you can say one conclusion here. You don't find a strong, or you can say a concluded or generalized relation between zero sequence voltage and neutral voltage. You don't have a general relation between the zero sequence voltage and neutral voltage. Like you said in case of current, IN equals to 3 IN naught, IN equals to 3 IN naught. Such type of equation, you don't get between the neutral voltage and the zero sequence voltage. That's the problem. Okay, neutral voltage and VA naught can be calculated independently. Yeah, fine. Next thing. So till now we have seen the star network sequence networks. Star network sequence networks. Now let's move to delta winding sequence networks here. Next heading I am taking up. Next heading. Delta winding sequence networks. Delta winding sequence networks. Yeah. Delta winding sequence networks. Just I will show the delta winding here. Give these names as ABC. So these are the outgoing terminals. Outgoing terminals. Okay. So I will show these currents. Maybe this phase is carrying a current of IA in this direction. Phase current, phase winding. Better you say phase winding current, IA. And this phase winding current I am showing it is IB. And this phase winding current is IC. Phase winding currents IA, IB, IC. And these are terminals A, B, and it is C, I am showing. Okay. Now, terminal voltage I am calling. Terminal voltages, not phase winding voltage. I am calling terminal voltage. It is VA, this is VC, and this is VV. VV. Next thing. Each winding will offer an impedance of Z1 for positive sequence current flow, Z2 for negative sequence current flow, Z0 for zero sequence current flow. Z1, Z2, Z0 for positive, negative, and zero sequence current flows. Now, I'll say this VA is like VA1 plus VA2 plus VA0 in the similar way, because assuming that these are carrying unbalanced currents, windings are carrying unbalanced currents, obviously terminal voltages will be unbalanced. So I'm converting these voltages into symmetrical components like this. VB1, VB2, VB0 here. And this IA, IB, IC, you can write it as IA1 plus IA2 plus IA0. And IB also, you can say IB1 plus IB2 plus IB0. IC current, you can call IC1 plus IC2 plus IC0. Like this, you can say sequence current circulating in the winding A, B, C. Windings A, B, C. What is the outcoming line current of A? What is the outcoming line current of A? How much? IA current is entering to this node. KCL we have to apply. KCL application. Okay, to get the line current ILA, IA is a current entering, IB is a current going out. Means ILA will be IA minus IB. IA minus IB. Okay. What is the line current in the B? What is line current in the B? Observe here. IB current is entering, IC current is leaving out. IB entering, IC is leaving out. So you can call it is IB minus IC. IB minus IC. And what is this line current in the C? ILC. IC entering, IA is going out. So you can get this one as IC minus IA. You can get that current as IC minus IA. ILC current, IC minus IA. Okay. Next thing. See, for example, if you take positive sequence, I will tell briefly about positive and negative sequence. Our concentration is on zero sequence. For example, if you are taking positive sequence, you call these currents as IA1, IB1, IC1, terminal voltage as VA1, VB1, VC1. Listen please. IA1, IB1, IC1, VA1, VB1, VC1 voltages. All impedances will be equals to Z1. Z1. All are in ohms you take. Absolute. Ohms. Z1. System is balanced or not? System is balanced or not? If the windings are carrying only positive sequence currents, system is balanced or not? Yes, system is balanced. See, whenever you want to do per phase analysis here, whenever you want to do per phase analysis on this one, Whatever this delta connected impedances we have, that we have to convert into star. And you pick up only phase A of that. That is a per phase network of that delta binding. Yes or no? Right. Per phase network. Per phase equivalent network. Better state. But this Z1 I have given in ohms, right? Z1 I have given in ohms. So it will become Z1 by 3. If I have given this Z1 in per unit, that will be repeated as Z1 only in the star equivalent. Okay. Similarly, negative sequence also you can see. So I will write in the next slide as positive sequence per phase network. Positive sequence per phase network. Per phase equivalent network. In bracket you write from delta to star conversion. Delta to star conversion, right? This is outcoming terminal A. Outcoming terminal A. Up to neutral I am saying, because after converting the delta to star, you have a neutral point. This impedance is Z1 by 3 in ohms. If it is in per unit, you get that value as Z1 only, as we have discussed in the previous classes. And this terminal voltage is VA1, you can call terminal voltage. Whatever the current coming out, so-called line current, positive sequence line current. Positive sequence line current. IL-A1. Okay. Similarly, if you draw negative sequence network with the help of the delta to star conversion, negative sequence per phase equivalent network in bracket from delta to star conversion, you get as it is network here with a notation of 2 per phase network. So this is a neutral. Impedance is coming Z2 by 3 ohms, and this voltage is VA2, and this current coming out is ILA2. Okay, voltage is VA2, current coming out, so-called line current, that is ILA2, and this impedance I am saying is Z2 by 3 in terms of ohms. But zero sequence network, we should put more concentration. Zero sequence network, we should put more concentration. Let's draw three phase zero sequence network. After that, we will make some conclusions on this. Three phase zero sequence network of this winding. Three phase zero sequence network. So I am showing that delta winding here. Showing the delta winding. Right. Each winding impedance is Z0. Each winding impedance is Z0. And this is voltage VA0, and this is VB0, and here you have VC0, and these are A, B, C terminals. Okay, outcoming line currents, you call it is ILA0, zero sequence line current of phase A. Oh, sorry, this is B and this is C. Okay. The previous diagram we considered in that manner. C and B. And this is ILB0 current. And this is ILC0 current. Okay, and winding currents, let's consider from the previous diagram. Winding currents, let's consider IA0, IB0, IC0. In the windings, this current you have IA0 here. This current is IB0, and this current is IC0. Okay, IA0, IB0, IC0. Cannot get Z1 by 3. Why Z1 by 3? Delta to star conversion. Delta to star conversion, impedance will become by 3, right? Ohmic value. If it is absolute value, it will become by 3. Per unit value maybe remains same. And in this zero sequence, each winding impedance is Z0. Each winding impedance will be Z0. Z0. Simple, simple. Don't guess anything. Don't guess anything. All the time we use it to run with the application of KVL and KCLs only here. Just listen my words. Stand at this point. Okay, how many currents you have? IA naught current entering, IB naught current is leaving out, ILA naught current is leaving out. Okay, so I can say ILA naught is nothing but IA naught minus IB naught. Can I write that word? ILA naught is nothing but IA naught minus IB naught. Is it correct or not by KCL application? Is it correct or not by KCL application? Yes, but not only that, not only that, you know that IA naught, IB naught are equal, right? IA naught, IB naught currents are equal. See, if these two currents are equal, it will be zero, obviously. Means you don't have any zero sequence line here current. And where this IA naught current is going then, that is jumping into the phase A like this. Whatever the current IA naught we have in the phase A was flowing into the phase B as IB naught. Okay, done. IB naught is entering to this node, IC naught is leaving out. Then ILB naught, if you write, it is IB naught minus IC naught value, and this number will be again 0. That number will be again 0. Now, whatever the IB naught we have in this phase, that is entering into phase C as IC naught. That is entering into phase C as IC naught, and it's not flowing into the line obviously. And whatever the current flow in the IC naught you have, that is jumping into the phase A as IA naught, and if you see ILC naught here, that is IC naught minus IA naught, that number will be again 0. So the conclusion, what we have to make from this delta, is, I don't get any zero sequence currents in the outcoming lines of the delta. I don't get any zero sequence currents in the outcoming lines of the delta. And if there is any zero sequence current, exists in the windings of delta, then it will be circulated in the loop of the delta. Okay, so I will write in the next slide the statements what I said now. No zero sequence currents. Zero sequence currents will exist in the outcoming lines of delta. Outcoming lines of delta. Right? Outcoming lines of delta. Next step. If there exist any zero sequence current, in the windings of delta, then it will circulate in the delta loop. Then it will circulate in the delta loop. So all of you getting these words? It will circulate in the delta loop. This thing we have to highlight. If there exist any zero sequence currents, then only it will circulate in the loop. The possibility that the winding should have. Yeah, one thing, listen. Why can't we convert this delta to star? See, this delta to star conversion or star to delta conversion, we can do. Listen, please. Listen my words. Please. Delta to star conversion, star to delta conversion, we can do provided that the properties of original network was unaltered. If the properties of the original network are not changing, then we can move from delta to star, star to delta. For example, if you convert this delta to star, I can say that star equivalent something like this. This may be Z0 by 3, and this may be Z0 by 3, this may be Z0 by 3. These are the outgoing lines, right? Only zero sequence currents we are discussing now. Outgoing line currents are zero. Outgoing line currents are zero. What about the currents in the windings? What about the currents in the windings here? Is it zero or non-zero? Tell me, who asked this question? Pratik Pramod. Tell me please. What are the currents in these windings? It will become zero, right? Because line current is zero and phase current also zero in the star. Line current is zero, phase current is also zero in the star. But what is your original network? Is it delta or star? Delta is your original network that you have transformed to star with the help of that conversion. Okay, so now the question is, in the original delta, you have some currents in the winding, but after converting this delta to star, you are missing that component, right? So this star is not a perfect equivalent to delta what we have existing. Okay, you may say that, sir, to circulate some current in that winding, you ground this neutral. Okay, after grounding the neutral, not only winding, line will also carry current. Not only winding, line will also carry current. But in your original network, line should not carry the current. Line should not carry the current. I think all of you have understood the thing what I said. But this problem you don't face in case of what we call positive and negative sequences. In case of positive and negative sequences, we have some currents in the phase windings, as well as we have some currents in the lines. And if you are converting the delta to star, that equivalent will take care of that current flow. Okay, so I am removing this one. I think it's not needed right now. I am removing this one because it will confuse you in your notes. Okay, now I have to draw the per phase network based on these conditions actually. Before writing those conditions, I will tell one more thing. One more thing I will tell you. Just listen. Just listen. Line zero sequence current. Line zero sequence current. ILA0. What is the formula? What is the formula for the line zero sequence current? You have zero sequence current formula already. 1/3 IA plus IB plus IC. 1/3 IA plus IB plus IC. Same formula I will repeat here. Means what you get is 1/3 IA is nothing but ILA. Now line A current, line B current, line C current summation. 1/3 ILA plus ILB plus ILC. What are these ILA, ILB, ILC values? ILA, ILB, ILC values. I have in the three-phase network. ILA, IA minus IB. ILB, IC minus IA. ILB, sorry, ILB, IB minus IC. ILC, IC minus IA. Substitute that here. What you get? 1/3. ILA is IA minus IB. ILB, IB minus IC. ILC, IC minus IA. How much is this value? 0. That's it. This is also another way. This is also another way of understanding how that line zero sequence current is coming 0. Okay. Next thing. Now we have to draw that per phase network, zero sequence per phase network. Zero sequence per phase network. Simple. We have to follow these two conditions, what I said. Just try to understand here. This is some reference plane I am considering. Some reference plane. Reference. I have to show winding as well as line. Winding, line, both. showing winding here, Z0 impedance, winding. This is line, outcoming line A, outcoming line. What property I should introduce now? If there is any zero sequence current, it should circulate in the winding, but it should not flow into the line. If there is any zero sequence current, it should circulate inside the winding, but it should not flow into the line. See, to have a possibility of that zero sequence current circulation inside the winding, we have to make this close. I'm saying you don't ask me from where this circuit we are getting. We are developing the circuit. We are developing the circuit by satisfying those properties. Okay, so as a winding should have a possibility of current circulation, I am making a closed path for this winding current circulation like this. But this line must be in an open mode in the zero sequence, so that line will carry zero current. Line will carry zero value of zero sequence current. Okay. How did we assume that zero sequence phase current directions in delta cycle? If we change our direction of assumption, we'll get the same result. Yes, Adarsh actually, listen here. I'm doing some rough work here. Just listen. See, this is one line carrying a current of IA in this direction. This I am dividing into same line carrying a current of IA1 plus same line carrying a current of IA2 plus same line carrying a current of IA0. What is the direction of IA1? Same as the original current IA. What is the direction of IA2? Same as the original current IA. What is the direction of IA0? Same as the original current IA. So whichever the direction of the original ABC currents we have chosen, in the same directions, we should consider the currents of IA1, IA2, IA0. Okay. Okay. Now let's have some sort of conclusion now. Let's have some sort of conclusion with respect to zero sequence currents circulations, zero sequence currents circulation. So we have discussed different windings, right? I'm saying here winding, type of winding here, type of winding. Next, I'll say zero sequence current in the windings. Will it exist or not? That's the thing. IA not in the windings. Zero sequence currents in the windings. And next I am saying zero sequence currents in the lines. IA not in outcoming lines. Outcoming lines, I am sure. Lines. Okay. Type of winding, IA not in the windings, IA not in the lines. Yes or no? That's it. You should say yes or no, exist or not. First, see, we have seen different windings starting from star grounded, right? So I'll take first star grounded winding with an impedance of Zn. Star grounded winding with an impedance of Zn. Tell me please, if the star grounded winding with an impedance of Zn, do we have zero sequence currents in the lines? Do we have zero sequence currents in the lines? Check that winding once. It's a star grounded winding, right? Star grounded winding like this. Zero sequence currents, sorry, as a neutral is grounded, neutral current may exist definitely. If the neutral current is existing, zero sequence current will exist. In case of star, you know, line current and phase current both are exactly equal. Line current and phase current both are exactly equal. So if the star grounded winding, zero sequence current will exist both in the lines as well as in the winding. Not only that, both currents are equal. I don't know whether you have understood this or not. Have you understood this? If it is a star grounded winding, zero sequence current will exist both in the lines as well as in the windings. Okay, next. If the star solidly grounded winding, what will happen? Star solidly grounded winding, what will happen? In case of star solidly grounded winding also, you have a possibility of circulation of zero sequence current because neutral current may exist because the neutral is grounded. Right? Neutral current will exist in the sense zero sequence current will exist in the winding as well as in the line. Both will be equal again. Okay? So exist in the windings as well as exist in the outcoming lines. Star grounded winding. Next one. Star ungrounded winding. Ungrounded winding. Can you please tell me zero sequence current? Zero sequence current. Will it exist in the windings? Will it exist in the windings? No. See, as it is what we call ungrounded neutral, we don't get zero sequence current in the windings as well as in the outcoming lines, right? Does not exist in both what we call lines and winding. Does not exist in both lines and the winding. Next one, last one, just now we have seen delta. Tell me about delta. Is there any possibility of getting zero sequence current in the windings? Is there any possibility of getting zero sequence current in the windings? Yes, maybe, may exist. What about in lines? It does not exist in the lines. Okay, so I will try to recall this table later also, maybe in transformer sequence networks construction, right? But as we have discussed about windings, I have concluded that here itself. Yeah, so next, let's take a small problem. I will consider. It's a very simple one, of course. Small problem only. Yeah, see this one. Hey, this question, even we discussed without discussing about this delta also. But still, in here, just go through this question once. Go through this question. See, a delta connected balanced resistive load, connected across an unbalanced three-phase supply. Find positive sequence symmetrical components of line A. Find the positive sequence symmetrical components of line A. Line A current was not clear. Line A current. Okay. Line A current. Simple. Already you know IA current here. IC current is also given. What is IB current? What is IB current? What is IB current? Yeah. See, first of all, positive sequence component of current A we have to find. Na? So that is IA1 you have to calculate. What is IA1 formula? 1/3 IA plus alpha IB plus alpha square IC. That's a formula for IA current. IA already we have it as 10 at an angle 30 degrees. Amperes. These are in amperes. IC current is given 15 at an angle minus 30 degrees. How to get IB current? Anybody? How to get IB current? IB. Sum of the three currents equals to 0 in the delta, right? In case of delta, sum of the three line currents equals 0. Why? You don't get any zero sequence currents in the delta. Delta outcoming lines. Delta outcoming lines, right? So in case of delta winding, right, you can write line current summation. Line currents sum. Line current sum means IA plus IB plus IC, that is equals to 0. From which you can get IB, that you substitute in the IA1 formula. So from this IB you can write as minus IA minus IC. Therefore, positive sequence current IA1. Therefore, positive sequence current IA1 is equals to 1/3 IA plus alpha IB plus alpha square IC. Alpha square IC. Okay. So you substitute these values quickly. 1/3 IA. You get IA into 1 minus alpha here. Plus IC into alpha square minus alpha. Alpha square minus alpha. You substitute these numbers. What is IA current? 10 at an angle 30 degrees. IA current 10 at an angle 30 degrees. And what is 1 minus alpha? √3 at an angle minus 30 degrees. Plus, what is IC current? IC current is 15 at an angle minus 30. 15 at an angle minus 30 degrees. And what is that alpha square minus alpha? Alpha square minus alpha, you get √3 at an angle minus 90 degrees. Please kindly cross-check these calculations. Kindly cross-check these calculations, whether these are correct or not. Alpha square minus alpha is √3 at an angle minus 90. So I can write this 1/3 into, you can get 10 √3. 10 √3, the angle will be 0 degree. 30 minus 30, that will be 0 degree. Plus, it is 15 √3 at an angle minus 120 degree. 15 √3 at an angle minus 120 degree. Just to calculate that IA1 current from this one. IA1 current by expansion. You have to write this 15 √3 cos 120 minus j 15 √3 sin 120. Pick up the real part, imaginary part, and take up the magnitude and associated angle. Okay. So I am giving the final answer to you. I'll give the final answer to you. So it will be 7.63. Magnitude 7. Angle will be minus 79.1 degree. 11 degrees. And 7.637 at an angle of minus 79.11 degrees. That's the IA1. Okay. Next. So next, let's move to alternator. So just recall the procedure. So if anybody getting stuck at some point, what we are doing and all, if you get a doubt, just go back and check the previous pages, what we have done till now. So actually this study and all, we started to do the analysis on the unbalanced system. While we are doing analysis on unbalanced system, we faced one step that we have to construct the positive, negative, and zero sequence networks, right? Different networks for a given single line diagram. On that view, I said, I have to know how to represent generator in the positive, negative, zero sequence network form and transformer as well as a line. Okay. So for that purpose, initially I discussed about how to represent a star winding in the sequence networks form, delta winding in the sequence networks form. Okay. Now with the basics of this, we are entering into the apparatus. So first I will take alternator and we will see how to represent that alternator in the positive, negative, and zero sequence networks form. Okay. Yeah. So I will be discussing about star connected alternator initially. So the next heading I will be considering as star connected alternator. Right. Sequence networks of alternator. Sequence networks for alternator. Alternator. In bracket, you write star winding, of course, grounded. Star winding, of course, it is grounded. I can say. Star winding, of course, it is grounded. See, you will have some induced EMF. You will have some induced EMF in the phase A, phase B, as well as phase C. Okay. Along with those induced EMF, I should draw that star mode. So I'm showing phase A. So phase A, it's having some induced EMF as well as some internal impedance. Similarly, phase B, having voltage source along with some internal impedance. I'm showing phase C, voltage source along with some internal impedance, and these are outgoing terminals showing as ABC here. ABC, outgoing terminals, and this was a neutral and connected to ground with an impedance of ZN. Neutral connected to ground with an impedance of ZN. Okay. Now each winding will have a positive sequence impedance of Z1, negative sequence impedance of Z2, zero sequence impedance of Z0. As it is, we have done nothing. This is internal EMF EA, and this is the internal EMF of phase B, and this is the internal EMF of phase C. Internal EMFs EA, EB, EC. Terminal voltages I am showing like VA, VB, VC. And currents you have here IA, phase A current. It is IB, and this is AC. Similar study almost, but whatever the difference we have, that I will discuss. Yeah, look here. See, these alternators, so this alternator is carrying unbalanced currents. This alternator is carrying unbalanced currents. Because of these unbalanced currents flow, these voltages are also becoming unbalanced. Terminal voltages are becoming unbalanced. So that this VA you replace with VA1 plus VA2 plus VA0. As it is, we have done in the star. Similarly, VB also, VB1 plus VB2 plus VB0. Similarly, this VC also, C1 plus C2 plus C. And this IA current, what we have, IA1 plus IA2 plus IA0. IA1 plus IA2 plus IA0, you can see. Okay. Yeah. Next. So how much is this neutral current we can say here? How much is the current flowing in the neutral? Again, same. It will be 3 into IN. Neutral voltage, if we calculate, it will be minus IN into ZN. As it is, we have done in case of the star winding. Okay, anyway, I am not repeating it now. I am not repeating it. Else, if you want, you write just formula. Just formula you can write. In the next slide, anyhow, I will show. Neutral current is 3 times of the geosequence current. Neutral voltage is minus IN into ZN. Else you write minus 3 IN0 into ZN. Minus 3 IN0 into ZN. Okay, next thing. How will be these voltages? See, for example, if you are taking positive sequence network, positive sequence 3-phase network, I will be showing these voltages VA1, VB1, VC1, currents, IA1, IB1, IC1, impedances, Z1, 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 neutral impedance, ZN. What about these voltages? Induced EMFs. Induced EMFs means we have to take positive sequence induced EMF in the phase A, positive sequence induced EMF in phase B, positive sequence induced EMF in the phase C. Similarly, if you are doing for negative sequence, VA2, VB2, VC2, IA2, IB2, IC2, and these induced EMFs must be negative sequence induced EMFs in the alternator. Similarly, for zero sequence also, you should show zero sequence induced EMFs in the alternator. Following all of you. Now, first and foremost thing what you have to study is how will be these 3 induced EMFs, EA, EB, EC, that we have to study a little bit. So, for example, if you have an alternator here, this is one alternator I am showing, right? It's a stator. It's a stator of the alternator. Stator of the alternator. Right? Something like this we have stator of the alternator. And I am showing one rotor here. One rotor we have. Let me show simply like this. For easiness in understanding, I am showing it's a salient pole rotor. For easiness in understanding, I am showing this as a salient pole rotor, like this. Okay, now this rotor field winding is excited with a DC supply. Rotor field winding is excited with a DC supply. And this rotor is getting rotated with the help of a prime mover. Maybe by coupling a turbine to this, by coupling a turbine, hydro turbine or steam turbine, we are rotating that rotor, right? So we are rotating this rotor in this direction forcefully with some speed, maybe synchronous speed we will assume, maybe synchronous speed. And we have some poles here, formation, north pole and south pole we will assume, north pole and south pole. That is with respect to rotor. Next, in the stator, we have 3 phase windings: phase A winding, phase B winding, and phase C winding. The physical position of phase A winding may be here. This is a phase A winding I am showing. And this is a phase B winding with a physical displacement of 120 degrees. And this was a phase C winding with a physical displacement of 120 degrees. All of you getting this one? All of you getting this? Please tell me. These are little basic about the alternator what I am discussing further. Little basic. Next. Listen. See, because of this rotor rotation in the air gap, definitely the phase A winding, phase B winding, phase C winding experiences rate of change in the flux. So definitely we have some induced EMF in the phase A winding, phase B winding, phase C winding. Okay, so phase A winding induced EMF, we are using a letter of EA. Phase B induced EMF, EB. Phase C induced EMF, EC. See, the magnitude of these 3 induced EMFs might be equal. Magnitude of these 3 induced EMFs might be equal. By saying a simple statement that all the 3 windings are experiencing a constant flux. All the 3 windings are experiencing a constant rotor flux. So that we can say EA, EB, EC magnitudes will be equal. Magnitude of EA, magnitude of EB, magnitude of EC are equal by assuming that flux distribution is uniform. Flux rotor flux distribution is uniform, and rotor will rotate in only one direction. See, the rotor is rotating in only one direction, means it will rotate in only one direction all the time, right? Rotor is rotating in only one direction means it will rotate in only one direction all the time. It won't have a backward rotation. Definitely. It will rotate in only one direction. Not only that, the speed of rotor is constant, synchronous speed. Okay, flux distribution is uniform, and rotor always rotates at synchronous speed. Rotates at synchronous speed in only one direction. That statement also I will write for your satisfaction. In only one direction. It was an assumption. It was an assumption. Now you see. Now this is how you use it to get that 120-degree displacement and all. I want to tell this basic one to you. Just listen. First, this north pole flux you take as a reference. North pole flux you take as a reference. First, it is touching phase A. So I will assume that phase A induced EMF is maximum. After some time, it will touch phase B. Rotor will rotate, right? After some time, it will touch phase B. Then phase B will reach to maximum. After some time, it will touch to phase C. Then phase C will reach to maximum. Then after some time, again it will touch phase A. So phase A will reach maximum. That is a phase sequence. First, which phase voltage is attempting the peak value? Which phase induced EMF is reaching the peak value? Phase A first. After some time, north pole touching B. So B reaching to peak. Next, C is reaching to peak. That is a ABC phase sequence, what we are considering right now. ABC phase sequence. You write here according to the rotor rotation and winding names. This ABC, sorry, EA, EB, EC are in positive sequence. EC, induced EMFs are in ABC sequence. Or we are saying this as positive sequence. Not only that, the time gap, listen kindly. Time gap between peak value of A and B, peak value of B and C, again peak value of C and A. The time gap is equal. As a whole angle is 360 degree. That we are dividing into three parts, 120 degree. Okay, the time gap we are converting the angle that we are saying as 120 degree displacement. So in that perspective, my intention is to tell you simply, induced EMF in the phase A is like mod E at an angle 0 degree. Induced EMF in the phase B like mod E at an angle minus 120 degree. Induced EMF in the phase C like mod E at an angle plus 120 degrees. Like this, we have the induced EMFs in the phase ABC. Phases ABC. Now, as we are attempting to take up the sequence network analysis here, whatever the induced EMFs you have taken just now, you convert those induced EMFs into symmetrical components. You get positive sequence induced EMF, you get negative sequence induced EMF, you get zero sequence induced EMF. Those induced EMFs you take in the respective sequence networks in the further study. Okay, yeah. You please convert these induced EMFs into symmetrical components. What you get now? Convert these induced EMFs into symmetrical components. If you convert these induced EMFs into symmetrical, whether these are balanced or not. Yes, balanced. If you are converting these balanced induced EMFs into symmetrical components, you don't get the zero sequence induced EMF. You will get positive sequence induced EMF. That is nothing but EA. And you don't get negative sequence induced EMF. That is 0. EA2 value was 0. So only positive sequence induced EMF we are going to get in the alternator. You don't get the negative sequence as well as the zero sequence induced EMF. Okay, so I will replace simply this EA as EA1 and EB as EB1 and this EC as EC1. Please don't ask me again. Please don't ask me again. Why don't we have negative sequence induced EMF in the alternator? Why don't we have zero sequence induced EMF in the alternator? Don't ask me. I've already explained mathematically in a clear way. Okay, what's the reason means? Rotor is rotating at a constant speed, so-called synchronous speed, in only one direction, so that the induced EMFs are balanced induced EMFs. These are converging into symmetrical components means you get only positive sequence induced EMF. You don't get any negative and the zero sequence induced EMFs in the alternator. Okay, right. So next, I will be considering positive sequence network, three-phase network, then negative and zero sequence network. And at the end, I will try to give the differences between the sequence impedances. Z1, Z2, Z0, differences we will discuss. Yeah. So first, I'll take positive sequence network, three-phase network. Positive sequence, three-phase network of alternator. Yeah. So you have voltage source also here, right? Voltage source also. Neutral connected to ground with an impedance of ZL. Let's call these terminals ABC, EA1, VB1, VC1 voltages. Same as a star winding, except that we have a source here. Even IC1. These impedances will be Z1. Impedances will be Z1. And these are induced EMFs you can take here. EA1 positive sequence, EB1 positive sequence, EC1 positive sequence. How much is current flowing in this neutral impedance? 0. For positive sequence, current flowing in the neutral impedance is 0. Okay, next. So as a neutral current equals 0, so IN into Zn. IN into Zn is also equal 0. So this neutral voltage also coming as 0. Neutral voltage also coming as 0. So by the same rule, I can draw that per phase equivalent circuit with a neutral reference plane. I can draw the per phase equivalent circuit with a neutral reference plane, and I can show that per phase network here. Per phase network. So this is A, right? And you have Z1, and here it is source EA1. Source EA1, and this is neutral. And this voltage we are showing as VA1, and current here is IA1. Simple. What is it VA1 here? By the application of KVL, you can write VA1. Simply EA1 minus IA1 Z1. EA1 minus IA1 into Z1 you can write. Yeah. Next, let's write something about the Z1 here itself. The Z1. So in the next slide, I will be showing the Z1. Particularly in the view of a fault analysis, I am saying this one. Z1. It will be taken in different ways according to the state of analysis. Z1 value will be taken in different ways according to the state of analysis. See, this Z1 value can be taken as by neglecting resistance. By neglecting resistance, I am talking this one. JXD double dash. JXD double dash sometimes. Whereas XD double dash is direct axis subtransient reactance of the alternator. Else you write this one, direct axis subtransient impedance of the alternator. Subtransient impedance of alternator. Okay. So other way of expressing this Z1 is JXD dash, which is direct axis transient impedance of the alternator. Transient impedance of alternator. Whereas in another way, you can write it as XD. You can say this as D axis steady state impedance of the alternator. Steady state impedance of the alternator. Okay, according to the state of analysis, we can take any one of these three numbers, either XD double dash or XD dash or XD. Okay, I will explain about these terms even more clearly if you go into the fault analysis. You enter into the fault analysis, we used to get these terms clearly. Okay, for time being, just leave your doubts aside. We'll discuss about these impedances clearly in the fault analysis. Okay, this is about the positive sequence network. Let's draw negative and zero sequence networks also quickly. Per phase network also we have drawn. Okay, so next negative sequence network I want to take. Please complete it quickly. So I'm taking the next slide. Negative sequence network. Right. First, let's show that three-phase negative sequence network. Three-phase negative sequence network. So winding impedance Z2, and you don't have any voltage source here because EA2 is equals to 0. EA2 is equals 0. EB2 also equals to 0. This is a winding impedance. EC2 also equals to 0. And this is a winding impedance. Neutral is connected to ground with an impedance of Zn. Neutral is connected to ground with an impedance of Zn. So I'll say these voltages here, VA2, VB2, VC2. And currents IA2, IB2, IC2. Okay. Impedances, let's call Z2, Z2, Z2. Z. Next, what is this neutral current here? How much is the neutral current? 0 ohm. Because summation of three negative sequence currents will be 0. I'll write here if you want, if you get any confusion, EA2 equals to 0. EB2, EC2 also equals to 0. See, as a neutral current equals 0, that 0 into Zn will be 0 only. So obviously your neutral voltage is also equals to 0. So we can draw that per phase network of phase A. Phase A network we can draw aside as a per phase network. Per phase network I am showing per phase network. So this is a terminal A and this is Z2 impedance. Z2 impedance and this is neutral. And this voltage I am showing as VA2. Okay. And this current is IA2. Current is IA. So this VA2 we can write as minus IA2 into Z2. Minus IA2 into Z2. That's a VA2. Let's finish up the zero sequence also. Then we will go with the comparison of impedances. Z1, Z2, Z1. Okay. So let's say complete it first. I'll wait for 5 seconds. Please complete it. Again, I got a question. Why EA2 0, sir? Huh? Why EA2 is 0? Sairam Rohit. Go with the previous slides what I have discussed in your notes itself. Zero sequence network, I'll draw. Zero sequence network. Just three-phase zero sequence network I will show first. Z0. You don't have a voltage source here. EA naught equals to 0. EB naught 0. You have again Z0. EC naught also 0. You have again Z0. Like this. And this neutral to ground, we have an impedance of Zn. Neutral to ground, we have an impedance of Zn. And these are ABC outcoming terminals. Voltages we have VA naught, VB naught, and VC naught. And these currents are IA naught, IB naught, IC naught. IA naught, IB naught, IC naught. Okay, how much is this neutral current? How much will be the neutral current here? That will be 3 times of zero sequence current. Neutral current is equals to 3 times of the zero sequence current. IN equals to 3 into IN. And neutral voltage will be definitely not equals to 0 in this case. And similar to star winding, if you draw zero sequence network, per phase network for this, A to neutral, we should keep Z0. Neutral to ground, we should keep 3 times of Zn. Because that the whole circuit in the per phase manner is carrying a current of IA0. So we are making the impedance as 3 times and making the current to circulate as IA0. Okay. So per phase network I will draw. Zero sequence per phase network is A. Up to neutral, we should keep Z0. Neutral to ground, we should keep 3 times of neutral impedance. 3 times of neutral impedance, 3 times of Zn. So here you can call VA naught voltage. Call this as VA naught voltage. And this current, you know, it is IN. IN. Yeah. Next. Here, if you want to write EA naught value 0, EB naught 0, EC naught also 0. Yeah. Next. Some of you might have studied conditions for rotating magnetic field theory and all, right? So I will take the conditions for the rotating magnetic field theory first. Based on that, I will try to tell about what we call positive sequence currents rotating magnetic field, negative sequence currents rotating magnetic field, similarly for zero sequence. And then we will try to take up that differences and all. Okay? Yeah. First, look here. Conditions for rotating magnetic field, particularly with respect to three-phase system, I am saying. Rotating magnetic field creation. Conditions for the rotating magnetic field creation. First condition, there should exist 3 windings. Three-phase system I am talking, that's why I am saying. 3 windings which are physically displaced by 120 degrees. There should exist 3 windings physically displaced by 120 degrees. Next condition. These three windings should carry 3-phase balancing currents. Okay. these windings should carry balanced three-phase currents. Three-phase currents. Of course, if these two conditions are satisfied, definitely there exists a rotating magnetic field in the air gap. Definitely there exists a rotating magnetic field in air gap. Generally, in the alternator, obviously in the stator particularly, in the stator of the alternator, three windings are physically displaced by 120 degrees. Phase A winding, phase B winding, phase C winding. If time permits, I will show how that physical displacement we are going to get. And see, listen. I'm moving to the positive sequence model. This one. So I'm showing one rotor here in the air gap. Something like this. I'm showing one rotor. Just it's a schematic diagram. Okay. See, actually, this rotor is rotating in some direction with a synchronous speed. Synchronous speed, this rotor is rotating. I'm showing that here. Rotor is rotating in this direction with synchronous speed. Bracket, I will write rotor. Rotor speed is synchronous in certain direction. Listen. Kindly listen my words. Kindly listen my words first. Because of this rotor rotation in certain direction, we are having some induced EMFs in the stator. Those induced EMFs we considered as positive sequence induced EMFs. Those induced EMFs we considered as positive sequence induced EMFs. And we have some currents flow in the windings also, but right now we are taking only positive sequence currents, IA1, IB1, IC1. Okay. Again, I am repeating the statements. Kindly listen. Rotor is rotating in certain direction. We have positive sequence induced EMF with the stator. With respect to that, we have some positive sequence current flows in the stator windings, three windings. Now we have three windings in the stator, which are physically displaced by 120 degree. Not only that, now those three windings are carrying balanced currents, right? The three windings are carrying balanced currents. So the conditions for rotating magnetic field theory was satisfied. So definitely these positive sequence currents will create a rotating magnetic field in the air gap. In which direction that rotating magnetic field will rotate? Anybody please tell me? In which direction that rotating magnetic field will rotate? In the same direction of the rotor. Because whatever the induced EMFs we have now, the sequence of the induced EMFs is decided by the rotor rotation only. By that way, I can say that the positive sequence rotating magnetic field created by the positive sequence currents or same sequence currents will be in the same direction of rotor rotation. Okay, so I can show that positive sequence rotating magnetic field in the same direction of the rotor. At how much speed it will rotate? Means it will be at synchronous speed only, because frequency of these currents will be same as the frequency of the induced EMFs. Frequency of these induced EMFs decided by the rotor speed. So obviously the speed of the positive sequence RMF will be synchronous speed only, which will rotate in the same direction of the rotor. I will write that statement. Okay? Yeah. So I'll say because of positive sequence currents or a positive sequence RMF rotating magnetic field created in air gap rotates in same direction of rotor. Rotates in same direction of rotor. at synchronous speed. Rotates in same direction of rotor vector at synchronous speed. This is one statement. Second statement I am saying. Second statement. Look here, look here. Negative sequence network I have chosen. Here also we have a rotor first. Rotor, something like this. And this rotor is rotating in this particular direction with synchronous speed. Rotor is rotating in that particular direction with synchronous speed. Now, I am saying you same sort of conditions as a repetition. 3 windings you have. 3 windings you have, which are physically displaced by 120 degree, carrying balanced currents now. IA to IB to IC to are 3-phase balanced currents now. 3-phase balanced currents. But these currents sequence is opposite to the positive. Means these are negative sequence currents. Definitely, these negative sequence 3-phase currents also creates a rotating magnetic field in the air gap. Also creates a rotating magnetic field in the air gap. In which direction that rotating magnetic field will rotate? In which direction that rotating magnetic field will rotate? Anybody please tell me which direction? Just opposite direction, right? Just it will be in opposite direction to the positive sequence RMF, or you can say opposite direction to the rotor rotation also. So I can say we have some negative sequence RMF, negative sequence rotating magnetic field rotates in opposite direction with synchronous speed. With synchronous speed. Okay, that statement also I will write now. In the next slide, I will write. Leave some space 2 to 3 lines here. Leave some space 2 to 3 lines. A negative sequence RMF, created in the air gap and it rotates in opposite direction. Rotates in opposite direction to rotor at synchronous speed. At synchronous speed. Okay, this is the first statement with respect to positive sequence RMF. Second statement we are saying with respect to negative sequence RMF. Okay, listen to me. So this is that rotor picture you have, right? Roughly. And this rotor is rotating in this direction with synchronous speed. Rotor rotation in that direction, synchronous speed. Here you have some winding, damper bars and all, right? And this winding is excited with the DC source already, as you know, like this. How many rotating magnetic fields we have in the air gap now? How many rotating magnetic fields we have in the air gap? Yeah. Does it mean that even the fluxes are unbalanced? Both positive and negative exist? Definitely. Only 2, right? Only 2. Positive, negative we are discussing. 0 we have not discussed till now. I will discuss about the 0. Yeah, if anybody is still writing, please complete it. This slide. The previous slide. Okay, so now I will show first the positive sequence RMF in this direction. Positive sequence RMF in this direction with synchronous speed. Tell me now, for example, if you are sitting on the rotor, like this, with respect to rotor, by sitting on the rotor, how is it positive sequence RMF looks to you? How is it positive sequence RMF you feel? Is it rotating or stationary? Anybody? Stationary. It's not rotating, it will be stationary, brittle. By sitting on the rotor, if you look at the positive sequence RMF, it looks to be stationary because both are rotating at same speed, right? then there is no relative speed. As there is no relative speed between the rotor and positive sequence RMF, can we expect any EMF to be induced in this rotor because of positive sequence RMF? Can we expect any EMF to be induced in the rotor because of the positive sequence RMF? No, we don't have any EMF to be induced. Okay, that statement I will write first. So I am moving to this point number 1 where we have written that implies no relative speed between rotor and positive sequence RMF. Rotor and positive sequence RMF. That implies no EMF induced. No EMF induced in rotor due to positive sequence RMF. Due to positive sequence RMF, you don't have any induced EMF in the rotor. Okay. Next. Let's take positive sequence is over. Now, negative sequence RMF, if you consider, it will rotate in opposite direction. Negative sequence RMF, if you consider, it will rotate in opposite direction. With how much speed? Ns. With a speed of Ns. Now we tell me, if you sit on the rotor, how this negative sequence RMF looks to you? It's rotating in the reverse direction. You are rotating in one direction, but field is rotating in the other direction. Means with respect to you, you feel that the field is rotating at how much speed? Double the synchronous speed. Double the synchronous speed. Getting? So the relative motion we have between these two, negative sequence RMF and rotor, definitely we have some induced EMF in the rotor body, means rotor winding, as well as some dampers. Okay, that statement I will write. That implies there is a relative speed of 2ns between negative sequence RMF and rotor. Negative sequence RMF and rotor. Negative sequence EMF and rotor. That implies an EMF will be induced. EMF will be induced in rotor. Will be induced in rotor. At how much frequency? Rotor means you write field winding, damper bars, etc. Damper bars, etc. At how much speed? So at how much frequency? Double the synchronous frequency, means 2f, right? At double frequency. Double frequency, in bracket you write 2f. Means if you want to get that frequency, you know it is Pn by 120. Frequency formula, you know, Pn by 120. That n is now 2ns by 120. Means it is double the value of Pns by 120. Means it is 2f. See, because of this induced EMF, you know, already this field winding is a closed one. Field winding has its closed path. Damper bars also has its closed path. Because of the EMF induced, definitely some current will circulate in the field winding and damper bars. Okay, that may cause excess heating, rise in the heating of the rotor. Okay, this is one of the cause for the rotor overheating in the synchronous machine. Okay, so let's write the next slide. Next slide. That implies double frequency currents will circulate in the rotor. Double frequency currents will circulate in the rotor. Circulate in the rotor. Rotor means again field winding, damper bars and all. And it may cause for overheating in the rotor. Overheating in the rotor. Okay, so as a simple straight statement, could you please tell me who is a cause for rotor overheating in the machine? Who is a cause for rotor overheating in the machine? Anybody? You can say negative sequence currents. That's okay. Negative sequence currents. When these negative sequence currents are created, if the alternator is operating under unbalanced loading condition, if the load connected to the alternator is unbalanced, then the alternator has to supply unbalanced currents. There, we can have positive sequence currents as well as negative sequence currents. Because of that negative sequence currents, we have the rotor overheating in the machine. Okay, so I can say rotor overheating is due to unbalanced loading on the alternator. Unbalanced loading on alternator. Unbalanced loading on the alternator, or negative sequence current flow in the stator. Negative sequence currents flow in the stator. Negative sequence currents flow in the stator. Okay. So I'm showing previous slide. If anybody is still writing, please complete the previous slide. 5 seconds I will wait. Please complete it if you are still writing. Okay. Yeah. So please complete this one. So till now, just we have seen positive sequence RMF will not create any EMF. Negative sequence RMF will create an EMF. Double frequency in the rotor. Double frequency currents are created, rotor overheating. But we didn't discuss about that impedance, Z1, Z2 comparison and all. That we have to do now. Z1, Z2 comparison we have to do. Okay? Yeah. Listen here. So I'm taking one simple phasor diagram. Try to understand that phasor diagram. See this. First, again, I will take for positive sequence first. After that, I will take for the negative sequence. Positive sequence I am taking first. After that, I will take for the negative sequence. See, these are some axes I am considering. Direct axis and quadrature axis of the machine. Right? It's a direct axis of the machine I am considering. I'll show that in the what's called rotor also. And this I am showing as quadrature axis. Quadrature axis of the machine, right? Q axis of the machine. And this is direct axis of the machine, D axis of the machine. Okay. Look here. So whatever the polar axis we have in case of rotor, that is going to be called as direct axis generally. Else better, I will show that direct and quadrature axis in this figure. This is the direct axis, polar axis, or you can say direct axis of the machine. And it is a quadrature axis of the machine, Q axis. Quadrature axis of the machine, or you can say Q axis, like this way. Okay, let's move ahead. The present discussion what we are making. Yeah. Look here. Generally, flux produced by the rotor. Rotor is rotating continuously, right? Rotor is continuously rotating, means definitely you can say rotor flux is also rotating continuously. Okay, yeah, 1 minute, please. 1 minute, I will come back. Listen here. So now, see, if you think about the reactance of the machine, listen please. It's a direct axis we have shown, and the quadrature axis might be like this, as we said. Quadrature axis will be like this. So whenever the rotor is rotating, obviously rotor flux also rotates. Rotor flux also rotates along with the direct axis only, along with the direct axis. So always the rotor flux will lie on the direct axis in the phasor diagram. So I'm showing that here. So this is the flux. Flux produced by the rotor. Okay. Flux produced by the rotor along with the direct axis. Now we have some induced EMF in the stator, right? We have some induced EMF in the stator. You know, this is rotating in anti-clockwise direction. The induced EMF will be in lagging by an angle of 90 degree. Induced EMF will be lagging by an angle of 90 degree with respect to rotor flux. So you get the induced EMF along the quadrature axis. You get that induced EMF along the quadrature axis. So this is the induced EMF E, I can say. Induced EMF. Now, next one. Observe here. This is alternator. No resistance in the alternator winding. No resistance in the alternator winding. For example, if this alternator is experiencing a short circuit, kindly listen to my words. If this alternator is experiencing a short circuit, something like this, short circuit, then whatever the current you have, IA, armature current IA, because of this pure reactive nature of network, this current IA will be 90 degree lagging with respect to this induced EMF. We have that armature current 90 degree lagging with respect to induced EMF. Following. So I can say that the armature current or stator current might be along this axis. This is armature current IA I am showing. All of you understood this phasor diagram till now? Have you understood this phasor diagram? Yeah. Now we have some armature flux also, right? Armature flux will be in the same direction of the armature current because flux and current are in phase. I do expect we have some armature flux as phi A. Okay. Now, generally, synchronous reactance of the machine means XS means it will consist of two values. One is a leakage reactance of the machine, winding plus armature reaction reactance. Leakage reactance of the winding, and XA is a armature reaction reactance. Okay, XL leakage reactance we are showing. XA is a armature reaction reactance. Okay, done. Next thing. Actually, this armature reaction depends upon the air gap. Armature reaction value depends upon the air gap. Or first of all, armature reaction means effect of the armature flux on the main field flux. Means effect of the armature flux on the rotor flux, you can see. Armature reaction, shortly I am calling that as AR. Effect of armature flux phi A on main field flux. Or you can say rotor flux. rotor flux, main field flux, or you can say rotor flux. That's the armature reaction. See, when this effect is more, when this armature reaction effect is more means, if the air gap between that stator and rotor is very less, if the air gap between stator and rotor is very less, at the time I can say this armature reaction is more, armature reaction reactance is more, so obviously resultant reactance value will be more for the machine. Following, so armature reaction is high if air gap between stator and rotor is less. Stator and rotor is less. Okay, armature reaction is high if the air gap between the stator and rotor is less. Okay, kindly observe here. In this diagram, it may be. Yeah, 1 minute, please. In this diagram, along what axis we can say more armature reaction? Is it along direct axis or quadrature axis? Along which axis we can feel air gap is, armature reaction is more? Along direct axis or quadrature axis? Direct axis. Yes or no? Because air gap is less here, so armature reaction is more along the direct axis. Along the quadrature axis, obviously armature reaction will be less, we can say. Okay, just keep that thing in mind. Keep that thing in mind. No need to bother about that statement further. Now you think about this phasor diagram, whatever. This phasor diagram, we have taken 90-degree lagging current. This is armature flux, and this is a what we call main field flux, or you can say rotor flux. How is the effect of the armature flux on the main field flux? Is it only along direct axis all the time in this phasor diagram? Obviously, it is opposite to direct axis, right? As armature current, armature flux is quite opposite to the main field flux. I can say armature reaction is only along the direct axis. Armature reaction is only along the direct axis. Following all of you? Please tell me. So as if the armature reaction is only along the direct axis, we can treat or we can consider only direct axis reactance for the positive sequence analysis. That's why I said the positive sequence impedance as JXD double dash, or we say JXD dash or JXD. Only direct axis reactances we have considered here. Yeah, I don't know whether you have understood this statement or not. Are you clear? Are you clear about this one? So if you want to write, in this case, armature reaction is only along direct axis. So only direct axis reactances will be considered. Direct axis reactances will be considered. Only direct axis reactances will be considered. Yeah, actually, I forgot to tell you one more thing. Of course, it's a crucial term only. Just listen to me. This rotor flux is rotating in this direction. Okay, with a synchronous speed. What about this armature flux? In which direction it is rotating? Armature flux is rotating in which direction? In the same direction, right? In the same direction. That's what we said. Positive sequence rotating magnetic field rotating in the same direction of the rotor. So obviously, this is also rotating in the same direction with the synchronous speed. By the way, at any time you see both armature flux will lie only along the direct axis. So effect of the armature flux on the main field flux is restricted to direct axis only. All of you getting my words? Please tell me. Okay, now I want to show you the difference for the negative sequence. Yeah. negative sequence, I want to show the difference. Let me say same sort of heading here. Negative sequence here. Negative sequence. I will draw this phasor diagram as it is. As it is, I will draw the phasor diagram. We have the rotor flux, we have the induced EMF, but you have to take the negative sequence current further. Okay, positive sequence now, this phasor diagram. I will indicate IA1, phi A1. IA1, phi A1. Doesn't matter. Let's copy this same phasor diagram, but changes I will show you. Changes I will show. Look here. Look. So this current I will say IA2. This current I will say IA2 at some point. This flux I am showing phi A2. This flux I am saying phi A2. But what is the direction of this flux? What is the direction of rotation of this flux? Anybody please tell me? What is the direction of rotation of this flux? Definitely in opposite direction. Definitely it will be in opposite direction. Yes or no? Right. So this armature flux phi A2 will rotate in opposite direction. Will rotate in opposite direction with synchronous speed. With synchronous speed. But you see, at this particular instant, that negative sequence armature flux is opposing the main field flux in the direct axis location. But you see once, or else you assume that you sit on this rotor. You sit on this rotor axis. If you sit on this rotor axis, you will feel you are not rotating. But how is this negative sequence flux? Rotating continuously? Yeah. Are you understanding this or not? Tell me please. If you sit on the rotor flux, how is that negative sequence armature flux looks to you? Continuously rotating, right? Continuously rotating means how is the effect of the armature flux? How is the effect of the armature flux on the main field flux? Is it constant or varying? How is the effect of the armature flux on the main field flux? Is it constant or varying with respect to time? It's continuously varying with respect to time. Means, can I say the armature reaction varies with respect to time with the help of this conclusion? Right? So I can say from this now, armature reaction will vary with respect to time. Armature reaction will vary with respect to time. Not only that, as if the armature reaction is varying with respect to time, armature reaction reactance XA, armature reaction reactance XA also varies with respect to time along the direct axis and quadrature axis continuously. Okay, that implies reactance of machine will vary with respect to time, continuously between D and Q axis. D axis and Q axis. Between direct axis and quadrature axis. Okay. See, means I can say this reactance might vary in between XD double dash and XQ double dash. XD double dash and XQ double dash. Subtransient reactance only we are considering. So if it is continuously changing between XD double dash and XQ double dash, we should compromise to some number. So that I will be taking the average of these two reactances. As a negative sequence reactance of the machine. Okay, so I'll write in the next slide. So the negative sequence reactance of alternator is considered as X2 is equals to XD double dash plus XQ double dash by 2. Average of these two Else, if you want to write that terminology in terms of Z2, J xd double dash plus xq double dash by J xd double dash plus xq double dash by 2. Okay, what is Z1? Z1 is J xd double dash, but Z2 is J xd double dash plus xq double dash by 2, we can say. And the difference between xd double dash and xq double dash will vary from one machine to other machine. Difference between xd double dash and xq double dash may vary from one machine to other machine. Okay, next thing. Yeah, correct. Next. We have to make some comment on zero sequence now. We have to make some comment on zero sequence. Let's consider the zero sequence also a bit quickly. Zero sequence. Else I will tell in a brief way. Just try to understand about the zero sequence. How are the currents? In phase currents, na? Currents flow will be in phase currents. But windings are physically displaced by 120 degree. Windings are physically displaced by 120 degree, but currents are in phase. As the currents are in phase, these currents will not create any rotating magnetic field in the air. Because second condition was not satisfied. Two conditions I said. First condition satisfied. Second condition is not going to be satisfied. So we don't get any rotating magnetic field in the air gap because of the zero sequence current flow. Because of the zero sequence current flow. Not only that, we don't get any armature flux in the air gap at all because of the zero sequence currents. Okay, right. So as you don't have any armature flux in the air gap, can we have any armature reaction effect? Can we have any armature reaction effect with respect to zero sequence current flow? No, we don't have any armature reaction effect because of the zero sequence current flow, and we will get only leakage reactance of the machine. Armature reactance will not exist. So that zero sequence impedance of the machine is simply JXL, so-called the leakage impedance of the alternator winding. Yeah. So I'll say in the next slide, for zero sequence, I'm saying this one directly to you. For zero sequence, yeah, due to zero sequence currents, there will be no armature flux in the air gap. Armature flux in the air gap. No armature flux in the air gap. No armature flux in the air gap means that implies no armature reaction. No armature reaction. No armature reaction means I can say reactance, zero sequence reactance or zero sequence impedance is nothing but simply leakage impedance. Zero sequence reactance will be only leakage reactance of the machine. Leakage reactance of the machine. Only leakage reactance of the machine. So I can call zero sequence impedance Z0 equals to JXL. JXL. Okay. JXL. So let me write in an expanded way about the Z1, Z2, and this what we call Z0. And we will have a comparison between these numbers. Okay. Please kindly complete it. Yeah. So I'll say first of all, XD double dash if we take, it will be having leakage reactance as well as armature reaction reactance, both. XD double dash, so-called the direct axis subtransient reactance, we said no. It will consist a leakage reactance as well as armature reaction reactance, both. XQ double dash, if you take, again, it will consist both numbers, XL and XAQ double dash. XL and XAQ double dash. Okay. So my kind request is don't join with anonymous attendee name. My kind request is don't join with anonymous attendee name. Please join with your own name. Okay. Yeah. Next, if you take Z1 positive sequence impedance here, that is JXD double dash. What is Z2? JXD double dash plus X2 double dash by 2 average. And Z0 is nothing but JXL. JXL. Could you please tell me how will be these two numbers, Z1 and Z2? How will be these two numbers, Z1 and Z2? Maybe close. Maybe close. Sometimes, in some cases, Z1 results in higher compared to Z2. Some cases, Z2 maybe results in higher compared to Z1. How is Z0 compared to Z1, Z2? How is the value of Z0 compared to Z1, Z2? Definitely less. Definitely less. Yes or no? Z0 value will be definitely less compared to Z1 and Z2. What's the reason? XD double dash is XL plus XAD double dash. In these two, XAD double dash may be major one. XL is very, very less number. Of course, by looking at this itself, XD double dash is greater compared to XL, or XL is less compared to XD double dash, and Z0 will be definitely less compared to Z1. So by comparing these numbers, by comparing these sequence impedances, we can say Z1 may be close to Z2. Again, I am saying sometimes Z1 may be more compared to Z2. Sometimes Z2 may be more compared to Z1. But for an alternator, Z0 value will be very, very less compared to Z1 as well as Z2. Okay. Now, I'm asking very simple question as a conclusion here. Simple question. Straight answer I need. Straight answer. Why you are having a difference between Z1, Z2, Z0 numbers here? Why you are having a difference between Z1, Z2, Z0 numbers? Anybody? Why the difference is coming between Z1, Z2, Z0? Because of armature reaction. Armature reaction is a reason. Because of armature reaction, you are having a difference between Z1, Z2, Z0. If you don't have armature reaction, XAD double dash 0, XAQ double dash 0, then XD double dash is XL, XQ double dash also XL. All the three impedances is nothing but leakage impedance only. Following all of you. So the difference between Z1, Z2, Z0 in the alternator is coming due to the armature reaction. Okay? Yeah, let me write. The difference between Z1 comma Z2 and Z0 are due to armature reaction effect in the alternator. Due to armature reaction effect in the alternator. Yeah, next. So next we should start the next apparatus, that is a transformer. Transformer we have to start, and how to construct the positive, negative and zero sequence networks we have to study. Okay, have a break for 15 minutes. Okay, so after break we will be continuing with the transformer sequence networks construction. 15 minutes break. Yeah, class is up to 9. Class is up to 9. Manivannam, I will clear your doubt later. I said already, difference between transient, subtransient, all these things I will discuss later in fault analysis. Okay. Yeah. So the next topic what we are going to discuss here is sequence networks of three-phase two-winding transformer, right? Sequence networks for three-phase two-winding transformer. Two-winding transformer. Sequence networks for three-phase two-winding transformer. Okay. So I think audio video is clear. Yeah. Listen here. See, three-phase two-winding transformer means we have different connections of transformer like star-star connection, star-delta, delta-star, delta-delta like that. Okay, first we will discuss about that positive and negative sequence networks construction. After that, we will discuss about the zero sequence. Our main concentration is on the zero sequence network of the transformer representation. Yeah. See, first of all, if this is one transformer, it's having a positive sequence impedance of Z1 and negative sequence impedance of Z2, zero sequence impedance of Z0 in per unit domain. In the per unit domain, Z1 per unit, Z2 per unit, Z0 per unit. Strictly speaking, this is the way how we have to tell this one. Z1 is a positive sequence impedance of transformer referred to one side, effective impedance. Effective impedance of transformer referred to any one side. Similarly, Z2, negative sequence effective impedance of transformer referred to one side. Similarly, zero sequence also. How will be these three numbers to be expected? See, just now we discussed about alternator, right? In that alternator, we have some difference in Z1, Z2, Z0 values because of armature reaction. But in case of transformer, you don't have any armature reaction. Don't have any armature reaction. As if you don't have any armature reaction, all these three impedances in per unit domain are equal. That is nothing but JXL provided that transformer is lossless. Okay. So since no armature reaction in the transformer, armature reaction in the transformer, Okay. See, first I am considering a transformer of delta star. Just I will show positive sequence network for that. Okay, remaining all transformers at that point itself, I will conclude. Yeah. So I'm taking in the next slide. Look here. So delta star transformer, I'm considering. Delta star transformer. See, primary, it's in delta, I'm showing like this. Primary, I'm showing in delta like this. Okay, so these are three wires coming out. Three wires we have. Star I am showing, star, secondary star. Okay, so like this we have star, yes, star. So we have ABC terminals on primary, ABC terminals on the secondary. Next, listen. See, I will show primary winding impedance separate, secondary winding impedance separate. Primary winding impedance in per unit domain separate, secondary winding impedance per unit domain separate. Okay. So I am saying primary winding impedance Z1 per unit, or else Just I will show number. Just I will show number. It is some 0.2 per unit. This is 0.2 per unit reactance. 0.2 per unit reactance. Okay. See, actually, if I show a winding something like this in this diagram, this consists an ideal winding as well as a leakage impedance. Ideal winding, leakage impedance. Ideal winding, leakage impedance. Okay. This is having some number like 0.25 per unit. This is also having 0.25 per unit number. This is also having 0.25 per unit number. Okay, it's a neutral. It's a neutral. I am discussing this only for positive sequence analysis. Positive sequence analysis only I am doing. See, I said already, if you want to draw some per phase network for this, per phase network, we should convert the delta to star. If there is any delta like this, the delta you have to convert into star electrically. Now, if you convert this delta to star, do you have any change in this reactance number in per unit form? Do you have any change in that reactance number in per unit form? No, we don't have any change in the reactance value in the per unit form. So in the very next slide, for the same delta star transformer, I will redraw it. I will redraw it as primary delta converted to star like this. Primary delta converted to star in this manner. Okay. And the secondary already have a star. Let me copy that star as it is. Secondary already we have a star. I'm copying that star as it is. Yeah. And you know, this conversion, after doing that conversion, each reactance is 0.2 per unit. 0.2 per unit. And this is neutral. And this is also neutral. Neutral. You feel it's a phase A, primary side, phase A, secondary side. Capital A, small a, I am sure. Which analysis we are doing? Positive sequence only. That's why this delta to star conversion will be valid for us. Okay, now what I'll do is, for the positive sequence current flows in this transformer lines as well as windings, what is this neutral potential to be expected? What is this neutral voltage for positive sequence analysis? Anybody? What is a neutral voltage for positive sequence analysis? 0. Yes or no? 0. And what is this neutral voltage for positive sequence analysis? Also 0. So we can short these two neutrals together electrically. Electrically, we can join these two neutrals together like this, and you pick up only phase A out. You pick up only the phase A out. Means left side, from primary side, you have 0.2 per unit reactance and an ideal winding. Right side, 0.25 per unit reactance and an ideal winding we have to draw. Okay, so phase A network of this one, phase A network of this one. Look here, this is capital A. I am showing that impedance 0.2 per unit, and then we have an ideal winding here. I am showing that ideal winding in the red color, like this. Okay, this is a capital A, and this is neutral. And next, phase A of other side, phase A of other side, I am showing here. And you know, this is having a leakage impedance of 0.25 per unit. Yeah, so this is small a, secondary side, and this is a neutral. And both are having same potential. We said neutrals 0, joined together. Now, can we feel that this node per unit voltage, this node per unit voltage is equal? Anybody please tell me? In the per unit domain, in an appropriate way. In an appropriate way, can I say, phase difference may be there. Forget about the phase difference for time being. Forget about the phase difference for time being. Can we say this node voltage is equal as we have discussed in single phase transformer with proper basis on primary and secondary? Yes or no? Yes. So I can short these two together. By shorting these two together, this we replace simply with primary impedance in per unit form plus secondary impedance in per unit form. Like this, we will replace. It's 0.2 plus it is 0.25. Okay. So simply any transformer you have, is it a star star, star delta, delta star, delta delta? You try to convert You try to convert that into a star-star transformer, and you take up the phase A out, and that phase A per phase equivalent circuit itself is a positive sequence network of the transformer. Means my intention is to tell you here, whether the transformer is a delta-delta connection, delta-star connection, star-delta, star-star. Whatever may be the connection of the transformer, doesn't matter. In the positive sequence network, per phase network, it is represented simply as a series impedance. In the negative sequence network also, it is going to be represented simply as a series impedance. In case of zero sequence, that connection, that what we call per phase network, depends upon the winding connections of primary and the secondary. Yeah, if you have understood this statement, I think I can move ahead. It's okay, I think, all of you. Is it okay for you? I will write the statement. I will write the statement anyhow. Yeah. Yeah. So I'm writing that statement. Whoever is asking me to repeat, please go through this statement. Irrespective of transformer connection, it is going to be represented as series impedance, in bracket in per unit domain, series impedance in bracket in per unit domain, right? For positive and negative sequence equivalent circuits. Positive and negative sequence equivalent circuits. Okay, so I'm repeating the statement. Any transformer connection you have, for example, I started with delta star, delta side leakage impedances I have given, star side leakage impedance I have given. Delta I converted to star for positive sequence analysis. After converting that to star, I considered only phase A of both windings, and I have removed the coupled circuit with the proper base selection, and we represented that as a simple series impedance. So in the positive sequence network form, this delta star transformer in the per phase manner represented as a simple series impedance. If it is a star delta transformer, again it's going to be represented in the same way by converting that secondary delta to star. Delta, both deltas you convert into star and you draw the per phase model in that manner. So in that view, irrespective of winding connections of transformer, it is going to be represented as a simple series impedance for the positive sequence and the negative sequence analysis. Okay, so for any connection of transformer, positive sequence network will be represented simply like this. It is Z1 per unit. Okay, if you want, you can show this is a primary side 1 and it is secondary side 2. Primary side, secondary side. That's the indication 1, 2. Next, in case of negative sequence, also it is represented simply as a series impedance Z2 in the per unit form. Z2 in the per unit form. So again, this side it is 1 and this side it is 2. Primary, secondary. That's the indication primary, secondary. Or PS also use better because 1, 2 we are using for notations of positive and negative sequences, right? So it's a primary, secondary, right? So it's a positive sequence per phase network, and this is a negative sequence per phase network. Yeah, is this clear, Vinita? Are you clear about this one, Vinita? Yeah, neutral voltage is 0 for a balanced system. I have discussed already, Bhanuchandra, if it's a balanced system, your neutral voltage will be 0. That's it. Phase difference is ignored. Already I said Dhanvi at the beginning itself, I said that is neglected, that phase difference. So if Z01 per unit present, then that will be sequence itself. Yes, see, actually, this Z1 itself is Z01 per unit. Z2 itself is Z01 per unit. We do not confuse you, just I spelled those words. Z1 per unit means what? It's the effective impedance of transformer referred to any one of the side in per unit. Z2 per unit means what? The effective impedance of transformer referred to any one of the side in per unit. All of you getting my words? Okay, next. I want to discuss about zero sequence network of transformer from this point. Zero sequence network of transformer. This is very, very important for GATE examination as well as ESC examination. Today itself, we discussed about properties of windings with respect to zero sequence current. I'm showing those properties, this one, this slide. Star grounded, any nature. Solidly grounded means with Zn equals to 0. Or having some Zn, having some non-zero value of Zn. Any nature of this one. Zero sequence current exists both in the lines and windings. In these two cases, zero sequence current will exist both in the windings and lines. If the star ungrounded, we don't have zero sequence current in the windings as well as we don't have zero sequence currents in the lines. Delta, it may exist in the windings, but it may not exist in the lines. Following all of you, it won't exist in the lines, but it may exist in the windings. Yeah, recall this what we call table, what I have mentioned earlier. With effect of this table, we are going to draw zero sequence network for different connections of transformers. Okay, yeah. So let's move. First of all, as an example, I am considering one transformer here. It is of connection star grounded delta. Connection is star grounded delta. It's the primary side, secondary side. Primary side, secondary side. Kindly listen my words. Stop writing. Stop writing. Stop writing. Just listen. Just listen. Total impedance means better I will show primary winding leakage impedance, secondary winding leakage impedance connected in series in per unit form. Primary winding leakage impedance, secondary winding leakage impedance connected in series. Whole I will call Z0. Whole I am going to call simply Z0. Next thing, it is some reference plane, maybe ground you can treat. Reference plane, else you can treat that as ground. Okay, it's a primary winding PW. It's a secondary winding SW. It is a primary line, outcoming line. Primary line, just I will indicate that as P. And it was secondary line, just I will indicate that as S. All of you understood this point. Primary line, secondary line. Primary winding, secondary winding. But primary winding, secondary winding, leakage impedances will be connected in series. And whole impedance, I am naming it as Z0. Z0. Tell me first, tell me. What is a property of primary winding? What is the property of primary winding? What is the connection we are having there? Star grounded, right? Connection is star grounded. What's the property of that star grounded connection? It will allow zero sequence currents both in the lines as well as the winding. Both in the lines as well as winding. Not only that, that value was equal. So definitely I will have some zero sequence currents in the primary line as well as I will have the zero sequence current in the primary winding. Not only that, these two values are equal. To manipulate that, to achieve that condition, I will be joining these two together simply like this. So that whatever the zero sequence current will flow in the primary line will flow into the primary winding also. Will flow into the primary winding also. All of you understood this? All of you understood this? Please tell me. What is secondary connection? What is secondary connection? Delta. What's the property of delta? What's the property of delta? Zero sequence current may exist in the winding, but it won't exist in the outcoming line. Means secondary line current is zero. Secondary line, zero sequence current is zero, but it may exist in the winding. Means you should provide that facility. we should provide that facility for the current circulation in the secondary winding by manipulating this diagram. So that I will join this to reference in this manner. So that I am providing a facility for the current circulation in the secondary winding and I don't have current in the secondary line. This will be the zero sequence network of star grounded delta transformer. Getting all of you? One more transformer I will take for your understanding. For your understanding, I am showing one more transformer here, delta star. Delta star. Again, first what you should do? Primary winding impedance, secondary winding impedance. Overall impedance is Z0 simply. It's a primary line and it's a reference and it was a secondary line. Secondary line. So I'm showing it's a primary winding. It's a secondary winding. Tell me, what is the primary connection? Delta. What's the property of delta? Property of delta with respect to zero sequence current. No current exists in the line, but current may exist in the winding. Current may exist in the winding means we should provide a facility. We should provide a facility in the circuit to have a current circulation in the winding. So I will be closing this, allowing some current flow in the primary winding. Allowing some current flow in the primary winding, closed path. What is secondary winding nature? What is secondary winding nature? Star ungrounded, right? Star ungrounded. If it is star ungrounded, what is the property of that? We don't have any current in the secondary line, as well as you don't have any current in the secondary winding also. You don't have any current in the secondary line and you don't have any current in the secondary winding also. Following all of you? Now, a small question I am asking you, I will repeat it anyhow later. Secondary winding is not carrying any current. Will that primary winding carries the current or not? Secondary winding is not carrying any current. That's okay. Will that primary winding will carry current or not? No, because of open, right? Because this is open, this side is open, this side current is zero. Obviously, primary winding current also becomes zero. This is the thing I said you earlier. I said you earlier, delta, in the lines, you don't have zero sequence current at all. But in the winding, if you have, it will circulate. But in this case, even though I am providing closed path for the current flow in the primary winding, but still, as the secondary winding is not carrying, primary winding current also becomes zero. Primary winding current also becomes zero. Clear? Now, but we, in the view of this is the exact way of understanding. It's the exact way of understanding the transformer zero sequence network. But in the way of examination, or what we call remembrance, we used to keep some series switches and shunt switches. Series switches and shunt switches. We will operate those switches according to the nature of winding connection. By that way, we can get that per phase model easily. Okay, yeah, let me show in the next slide. Next slide. Switching diagram. Switching diagram for zero sequence network of a transformer. Zero sequence network of a transformer. Okay, so I will show two windings are there, but I don't show as a two. Single impedance I will show. You should assume that that is a part of primary and secondary. Okay, I'm not showing it as two. I am showing only one. One impedance here, Z0, which consists primary as well as secondary, both. Next. Look here, it is a series which I am keeping on primary side. Series switch on secondary side. Okay, and here I am keeping one shunt switch on primary. And one more shunt switch on secondary side. Okay, it's a primary line, it's a secondary line. consists both windings, primary and secondary. Simple. See, listen here. If I close this series switch on primary, what it is indicating? Primary switch is getting closed means you are allowing current in the line as well as in the winding. For what nature of winding it will happen? Star grounded winding. So if it is a star winding, we have to operate the series switches. And for example, if you close this shunt, it will allow current in the winding, but it won't allow current in the line. Means for delta, we have to close the shunt switch. Okay, series switch operated for star windings. Series switch operated for star winding. And then shunt switch operated for delta winding. Series switch operate for star winding. Shunt switch is operate for delta winding. Okay, next. This one means this series and shunt switches position depends upon the primary. Or else I'll write simply primary. For primary switches, these are secondary switches. Secondary side switches. Yeah. So if you have any more doubt, we will be clearing those doubts as we move ahead with the zero sequence networks further. Yeah. So let's take with the star ungrounded first. Okay. Later on, we will modify the connection. We'll conclude it. Please complete this one first. Yeah, so I think I can move. First, star ungrounded. Simply, first you draw that open diagram. Don't keep switches and all, it will confuse you. Just you take this as open diagram consisting series connection and a shunt. Shunt may not be there. I don't show that shunt also for you. Just simply like this you show. It's a primary line and it was a secondary line, and this is a zero sequence impedance of windings, primary and secondary. Let me copy this one. Okay, done. Please listen. Primary, what's the connection we have? Star, but ungrounded. Star ungrounded means what is the property of that? It won't have zero sequence current in the line as well as in the winding, means this series switch should be simply open. Or else we have to close this with an impedance of infinite. Means obviously open only, right? Secondary, star ungrounded. Again, it won't allow zero sequence currents in the line as well as in the winding, means here also it will be in the mode of open, infinite. This is the zero sequence network for star ungrounded transformer. Both sides are ungrounded. Next one, star solidly grounding, star ungrounded. One side star solidly grounded connection, other side star ungrounded connection. Okay. So I will keep that open diagram here first. This is an open diagram. Next, listen please, listen. Primary what connection? Star solidly grounded, na? Star means series switch. Series switch we have to close. With how much impedance? As it is solidly grounded, Zn equals to 0, na? Zn equals 0 means we should close this switch with 0 impedance. Okay. Secondary side, what connection? Star ungrounded. Ungrounded means Zn equals the infinite on the secondary side. means we have to close a series switch with 3 Zn. 3 Zn means 3 into infinite, that will be infinite. 3 Zn. So 3 into infinite means it will be infinite obviously. Okay, next one. Next one. Star grounded solidly. Star with some Zn. Star with some Zn. For this, how to draw? Again, I will show open diagram here. It was an open diagram. Primary what connection? Star solidly grounded. Star means series switch. Series switch has to be closed with how much impedance? 3 Zn. Zn value 0 on the primary side. So simply this series switch is going to be closed with 0. Secondary what connection? Star with some Zn ground. Okay. Again, star means series which has to be closed with how much impedance? 3 times of the Zn. So we have to close this series switch with 3 times of Zn. Okay, I think all of you comfortable with this, what I am discussing. Next, I will show star with some impedance ground. Again, star with some impedance ground. So next I am showing star with some impedance ground, Zn1, I will show Zn1. And the secondary is also star only with some impedance ground, Zn2. Zn1, Zn2. Okay, so I will show that open diagram like this. Primary closed with how much impedance? 3 times of Zn1. Star means series which has to be closed with 3 times of that neutral impedance. Means here you have 3 times of Zn1. Secondary has to be closed with how much impedance? 3 times of Zn2. 3 times of Zn2. Like this, the equivalent, zero sequence equivalent circuit. Okay, next one. Delta star for this transformer. First, again, you show open diagram. This is an open diagram we have. Open diagram. Primary what connection? Delta. Primary is delta. Delta in the sense what? Shunt switch has to be closed on the primary side. Primary side, shunt switch has to be closed like this. What is secondary? Star ungrounded means series switch has to be closed with infinite impedance. Series switch has to be closed with infinite impedance like this. Okay, delta, primary, shunt switch closed. Secondary, star ungrounded, series switch closed with infinite impedance. Okay, next one, delta star with some Zn impedance. If Zn is 0 or non-zero, whatever it is, same circuit will be used with that particular Zn number. I will take up this open diagram like this. Open diagram means primary line, secondary line, Z0. That's it. Primary what connection? Delta. Means primary shunt switch has to be closed. Primary shunt switch has to be closed. Secondary what connection we have? Star grounded. Means the series switch has to be closed with 3 times of the neutral impedance. Series switch has to be closed with 3 times of neutral impedance. 3 times of Z. Like this will be. Delta, star grounded. Next one. Star delta will take star grounded delta, delta ultimately. Yeah. Next one is star delta transformer. Star ungrounded delta. Star ungrounded delta. Star ungrounded. Primary star ungrounded means series which has to be closed with infinite impedance. Ungrounded is Zn equals to infinite. So here you say 3 Zn equals to infinite. Means it is open. Right? Secondary delta. Delta means shunt switch will be closed. Secondary delta in the sense shunt switch will be closed. Next one. Star with some impedance grounding of Zn. delta. Star with some impedance grounding delta. Yeah. So you can see here, star with some impedance ground means series which will be closed with 3 times of Zn. Okay. Secondary, sir, primary star with some Zn ground. So series which will be closed with 3 times of Zn. Secondary, delta means shunt switch is going to be closed here. Shunt switch will be closed. Next one, delta delta. Last one is delta delta. So let's show that open diagram first, like this. Primary what connection? Delta. Delta means shunt switch will be closed here. Secondary, delta, again the shunt switch has to be closed like this. Okay, so like this we are going to get the connections. Zero sequence networks for various transformer connections. Yeah. So next, let's take one small previous gate problem. With the help of that previous gate problem, I want to tell you some more thing. So I'm moving with the next slide. Yeah, go through this one. Tell me your answer. Which of the following network represents the zero sequence network of star delta transformer? Means it is star ungrounded. Star ungrounded. If you want, I'll write in bracket. Y ungrounded delta. Y ungrounded delta transformer. Yeah, what's your answer? Y ungrounded delta transformer. Which of the following option is correct? Okay, let's continue with the thing what we have discussed till now. Means we try to construct the zero sequence network for that star delta transformer. Already we have it in your what we call theory. So it's a star delta transformer zero sequence network I have to take. So star in the sense primary series which will be closed with 3 times of Zn. Zn equals to infinite here, so it will be simply open. Secondary what connection? Delta. Delta in the sense, you know, it is shunt switch closed. Shunt switch will be closed. Which circuit is equivalent to this one? Among these ABCD options, which option is equivalent to this one? Anybody? Which option is equivalent? See, listen. Whether that option is equivalent or not means property of network should be remain same. Property of the network should be remains same. What is the property of this network first? That we have to discuss. Listen, stop writing. Stop writing. Just listen to my words, what I am saying. Property of this network means you have to inject some current on the primary lines. Check whether that current is flowing or not. Okay. And you inject some current on the secondary lines. Check whether that current is flowing or not. That will decide what is the property of this star delta transformer. Okay. For example, if you keep one current source at this primary terminals like this, you keep one current source at the primary terminals in this manner. Will it flow? Will it flow? Will that current flows or not? Anybody please tell me. Will that current flows or not? I need your response. I need your response. Will that current will flow or not? No. Means the conclusion is simply from primary side, we don't have any current entry into the transformer. Zero sequence. Zero sequence current, it won't enter from the primary side. That's one conclusion. Let's remove it. You keep the same current source on the secondary side. You keep the same current source on the secondary side. By injecting some current here, will it flow into the transformer? Will it flow into the transformer? No, it won't flow into the transformer. Means what? The property of this connection is it won't allow zero sequence current from primary side into the transformer as well as from secondary side into the transformer. Following, which network is satisfying that property exactly? Which network is satisfying that property exactly by means of that current injection? But current source should not be added in parallel. It's not parallel addition, Harshvardhan. It's not a parallel addition, right? Tell me anybody. Which option is correct with respect to that condition? For example, if you take A, option A, if I keep some current source here, if I keep some current source at this place, present place, if I keep some current source at this place, that current may enter, right? Current may enter and it may flow. Whether the current will close its path or not, it depends upon the other equipment. It depends upon the other equipment what you have decided to do. Similarly, if you keep some current here, there is a possibility for the flow. There is a possibility for the flow because I don't have any open circuit in the transformer. The other equipment will decide will it flow or not, strictly speaking. For example, if you keep some current here, will it flow or not? Yes, we have a closed path. Means it's not at all an answer to me. B is not at all an answer to me. What's the property of star ungrounded delta transformer? We should not have any current circulation from primary lines as well as from secondary lines. But this B is completely deviating the property. A also completely deviating the property. Now, if you keep one current at this place, at C, if you keep some current at this place, will it flow or not? No, because of open circuit here. Because of the open circuit, it won't flow. And again, if you keep some current here, will it flow or not? No, again, it is facing an open circuit. Okay, now if you keep some current here, will it flow or not? No, because of open circuit. Because of the open circuit. But if you keep some current here, will it flow or not? Yes, because it's providing a closed path. Means D is not again an option to me. D is again, it's not an option to me. Understood, all of you? Understood. So which option is suitable equivalent circuit for the transformer star delta? That is C. C is a transformer. Somebody is saying B, C, D. Yeah. Only C is a suitable option. Yeah. About A, I will discuss, Mallesh. So you write here if you want. This transformer, according to the circuit diagram what you have drawn, will not allow zero sequence current from any side. Okay, so circuit given in option C, will have the same property. So our answer will be C, obviously. Sai Charan. Option C, I am copying. Somebody is facing a doubt with this one. Just answer me what I am asking you. Option C, I have copied here. Don't think deeply, just it's a network analysis. Just it's a basic network analysis. What I am saying. I am keeping one current source at this side. Will that current flows or not? Tell me, Sai Charan Reddy. Sai Charan Reddy, will that current flows or not? Yeah. But for delta shunt path, see, just listen to me why you are questioning in different ways. Just listen to my words. Mr. Bonishri, Miss Bonishri, just listen here. Listen here. Current will flow or not? That you tell me, answer. No, it won't flow. Why? You have open circuit in the model, right? Whether the primary winding is closed or open, why you are bothering about that? Circuit is showing open here. Resultant circuit is showing open. So current will not flow on this side. Now, similarly, if you keep one current on this side, will it flow or not? No. Again, it's showing a open. Means this connection, means this circuit will not allow the current flow either from primary side or from secondary side, which is satisfying the property of the star delta transformer. Star delta transformer. Yes, Mutreddy Vashishta, whatever the statement you said is correct. Yeah. According to this question, option A. See, option A is also correct in the sense, actually, that depends upon the other equipment I said. That depends upon the other equipment. For example, listen here, listen. Look here once, look here. I have one generator, star solidly grounded, and I have one transformer, some connection, whatever it is. Some connection. I don't know about the connection of the transformer right now. Okay. Now, how that generator is going to be represented in the zero sequence? How generator is going to be represented in the zero sequence? Up to neutral, we should keep the zero sequence impedance of generator. Neutral to ground, we should keep zero shorted. Neutral to ground, we should keep zero shorted. Now, this is a transformer. Na? This is a transformer. Assume that it's a star delta transformer, what we are discussing now. Assume that the transformer is a star delta transformer. Okay. Now, if you keep that star delta transformer circuit as it is there, this one. Star delta transformer circuit as it is here. As it is, I am keeping the star delta transformer circuit. Just have a look, all of you. Star delta transformer circuit we kept here. Now tell me, if I inject some current at this place, some current at this place, will it flow into transformer or not? No, because of open circuit. Now, if I inject some current at the P location, will it flow into the transformer or not? Listen my words. Will it flow into the transformer or not? No, because of open. It may flow into generator. It may flow into the generator. That was second issue. Is it clear? Who is asking this one? Gurudatta. Gurudatta, are you clear about this one? Please tell me. Now, according to you, you want me to consider. Yeah, Rakesh, please listen what I am saying you. Kindly listen to me, please. For example, if you take up the option A for the star delta transformer, let us say, if you take option A for star delta transformer, I should show the circuit in this manner, right? I should show the circuit in this manner, right? From option A, if you follow option A, this is your circuit, right? This is your circuit. Now tell me, if I keep 1 per unit current on the secondary side, 1 per unit current on the secondary side, will it flow into the circuit or not? Will it flow into the circuit or not? Yes or no? Yes. It will be flowing into circuit. Is it the property of your star delta transformer? Is it the property of your star delta transformer? Rakesh Reddy. No, it is not the property of the star delta transformer. So can we choose this option A for our star delta transformer? No, we should not choose the option A. Getting all of you? Yeah. Okay. Next, let's make a simple conclusion based on these circuits what we have studied. Just look at this one. Look at this. Continuously, I used to ask some questions to you. Just make out your voice, right? Yes, correct, Nishit. Why delta don't have shunt switch on? Anuj Singh, I am explaining that thing only till now. No option is exactly matching to the circuit what we have. So we have to choose one of the circuit among the options given, which will have the property of same of our original circuit. Okay, next. Listen here. Star ungrounded, star ungrounded. Star ungrounded, star ungrounded. This side I will keep one current source. This side I will keep one current source. Will it flow into circuit or not? Yeah, please tell me. If I keep one current source, will it flow or not? No, because of open circuit. If I keep one more current source here, will it flow it or not? No, open circuit. So I don't have current entry from primary side into the transformer, as well as I don't have current entry from the secondary side of the transformer. So I will say that simply this transformer will not allow any zero sequence current circulation. This transformer will not allow any zero sequence current circulation. Next one. Star grounded, star ungrounded. Star grounded, star ungrounded. Primary side I am keeping current source. Will it flow or not? Tell me please. Will it flow or not? No. Why? Because of open circuit. Open circuit, Tumla, Akash. Just look at the circuit. Don't guess the answer just by. Look at the circuit and tell me the answer. Vinita, if I keep one current source here, will it flow into the circuit or not? Because of open, it won't flow. It won't flow. And if you keep one current here, will it flow or not? No. Means star ground star transformer will not allow the zero sequence currents. Even primary also will not allow the zero sequence currents. Okay, next one. Star ground, star ground. Star ground, star ground. Primary, you keep one current source here. Keep one current source. Will it flow or not? Chance is there. Chance is there to have the current flow in the transformer, provided that the equipment above the transformer providing the closed path. Providing the closed path. Okay. And if you keep current source on secondary side, will it flow or not? Yes, it will flow into the transformer, provided that equipment before to this transformer providing the closed path. Is it okay? Right. Means I can confirm that star ground is allowing the closed path for the zero sequence currents. Allowing the closed path for zero sequence currents. Next one. Again, star ground, same scenario. Delta star, unground. Delta star, unground. Current source I keep at P. Current source I keep at P. Will it flow or not? No. Open. Current source I will keep at S. Will it flow or not? No. It's open on this side also. Whereas delta star grounded, primary if you keep, it won't flow, but if you keep on secondary, it will circulate, right? It will circulate. Means what you should say is, particularly in case of delta star ground, you may not have zero sequence current in the primary line. You don't have exactly zero sequence current on the primary line, but on the secondary line, it may exist. Possibility is there for the existence. Primary winding, it may exist. Secondary winding also, it may exist. Clear? Anonymous certainty, just you are in a mode to just to give type, what we call something to type. You are not listening to the class completely. Yeah, listen to me. Delta star ground. Primary line it won't have. Primary line it won't have. Secondary line it is having. Primary winding will have. Secondary winding will have. Okay, this clarity we should have about this transformer delta star. Next one, star delta, star delta. Keep one current source here, it won't flow, open. Keep one current source on the other side, it won't flow, open. Means star delta will not allow any zero sequence current. Star delta will not allow any zero sequence current. Following all of you? Right. Star ground delta, star ground delta. Keep one current source here. Keep one current source. Will it flow or not? Yes, it will circulate in the loop. Yes. If you keep one current here, will it flow or not? No, because of open. So whatever the star ground delta transformer you have, it will offer a closed path for zero sequence current in both windings, and only in primary lines. But in secondary line, you don't have any current flow at all. Secondary line, you don't have any current flow. In case of delta delta, I don't have any zero sequence currents on both sides. Yeah. Next one. Listen. Next one. Next, one more logic I am going to tell you. Just listen to me. Star unground. Star unground. Will it allow zero sequence currents? No. Primary will not allow. Secondary, star unground. Will it allow? No. Transformer will not allow the zero sequence current. Primary is not allowing. Secondary is also not allowing. Transformer will not allow the zero sequence currents. Second transformer, primary star ground. It will allow, which we feel actually. If I say simply star ground winding, not in the transformer, nothing. Star ground winding, I say, it will allow zero sequence current. That I can say. Secondary what connection? Star unground. Secondary is not allowing. Secondary is not allowing. See, if the secondary winding is not allowing the zero sequence current, primary zero sequence current also comes to be zero. If secondary is not allowing the zero sequence current, primary zero sequence current also comes to be zero. Means overall transformer will not allow the zero sequence current, we should say. So in case of star ground star transformer, primary will not allow, secondary also will not allow the zero sequence current. Anybody having a doubt in this? Please tell me. Anybody having a doubt in this one? Yeah. Are you clear about this? What I said? Tell me star ground star. Star ground star. Will it allow zero sequence currents or not? Star ground star. Will it allow zero sequence currents or not? Only star ground means it will allow. But if it's a star ground star transformer, a secondary is not allowing, primary will not allow. Clear? Okay, next transformer, star ground, primary star ground, na? Will it allow or not? Yes. Secondary star ground, will it allow or not? Yes. Both windings are providing closed path for zero sequence current. I can say transformer will provide the closed path for zero sequence currents. Clear? Right. Next one. Star ground, same. Delta star. Please kindly listen. Delta. Only delta, irrespective of transformer. Only delta. Will it allow or not? Only delta. I am asking you. Will it allow or not? Yes, it will allow. In the windings, not in the lines. Star unground, it won't allow. As a secondary is not supporting for zero sequence current, primary current also comes to be zero. Following all of you. Yes, means what I am particularly saying here is MMF balance. Magnetomotive force balance. N1I1 must be equals to N2I. So if secondary current is existing, then only primary current will exist. If primary current is existing, then only secondary current will exist. If any one current is absent, other current will become zero. Is this clear? Next, tell me about this one. Delta star ground. delta star ground. Delta, will it allow? Yes. In the windings, it will allow. Next, I should check for other winding also actually. Star ground allows. Primary is allowing, secondary is also allowing. Definitely this transformer will allow the closed path for zero sequence currents. Both windings will carry. May not be both lines. Only secondary line is carrying the zero sequence current, we should see. Similarly here, star delta, primary is not allowing. You no need to bother about secondary. Whatever the connection it may be, transformer will not provide a closed path for zero sequence currents. Star ground delta, primary allowing, secondary allowing, transformer will allow. But delta delta is an exceptional case. Delta delta is an exceptional case. In the delta delta transformer, you don't have any zero sequence currents at all. Okay, delta delta, you don't have any zero sequence currents at all. Okay, now tell me, from this complete discussion, what we have done, which transformers will allow closed path for zero sequence currents? Which transformers will allow closed path for zero sequence currents? Transformer connections which allow closed path for zero sequence current. Zero sequence currents. Tell me, which transformer connections will allow? Star ground, star ground. Star ground, star ground. Or you say any mode of this one. Star solidly grounded, star solidly grounded. Else you say star with some impedance ground, star solidly grounded. Okay, this one connection. Next connection, delta star ground will allow. Delta star ground will allow. Else you say delta star solid ground. Star ground delta will allow. Or you can say star solid ground with delta. Star solid ground with delta will allow. Only these three transformers will allow the closed path for the zero sequence currents. Delta delta will not allow the closed path for zero sequence currents. Okay, one more small condition I want to tell you. One more small condition. If we see simply a transformer connection, whether the zero sequence currents will be carried by both windings or not. Both windings or not. How we can confirm is both windings individually should provide closed path for zero sequence currents. Both windings should provide closed path for zero sequence currents individually, and one of the winding among these two must be star grounded. That you can get from this. One of the winding among the two must be a star grounded one. Then only we will say the transformer will allow the closed path for zero sequence currents. Okay, right. Transformer will allow closed path for zero sequence currents. Zero sequence currents if both windings are providing closed path. Both windings are providing closed path and one of the winding must be star grounded. One of the winding must be star grounded. Star grounded. Okay, so this was a condition we have to maintain. I will try to compare this with third harmonic current. Now, somebody is asking a doubt. Okay, so I will ask one more simple question before going for the third harmonic current comparison. Very, very simple question I will ask you. The next slide I am giving. Next slide. question. It's a MSQ, multiple select question. Multiple select question. Okay. Which of the following represents zero sequence network of Y grounded or Y ungrounded by Y grounded transformer. Y ungrounded, Y grounded transformer. Option A. Option B. Option C. Option D. Option multiple select question. All are correct. All are correct, right? Star ungrounded, star grounded. Primary is not allowing closed path for zero sequence current. Even though secondary is allowing, that current also becomes zero because primary is not allowing. Means my zero sequence network simply acts as an open circuit. Zero sequence network simply acts as open circuit. It won't allow a current from any one of the side. Either it won't allow from primary side or it won't allow from the secondary side. No side it will allow. Which option is correct according to that statement? All the options are correct. If it is which question? MSQ, multiple select question. If it is MCQ, multiple choice question, MCQ, then you can go with the option A. If it is a MCQ, you have to go with the option A. If it is a MSQ, we should give option as all. All are correct. Okay? Yeah. Solution, I'll write. All circuits given in options are not allowing zero sequence currents. Zero sequence currents, which is a property of Y ground transformer. So all options circuits are suitable, are correct. All options are suitable, or you can say correct. Getting? Yeah. Next. Somebody asked me a doubt with respect to third harmonic current. Third harmonic current and this zero sequence current. What is the difference? What is the difference between these two? Yeah. So I will take one small table to explain the differences between them. Zero sequence currents, what we are discussing now. Okay. Currents on one side. Third harmonic currents. On the other side. Before saying about this, actually, course, some people may be knowing about this, some people may not, I think so. Still, you may study it later. You may study it later. So before studying that, you should have this clarity. Zero sequence currents in the transformer or zero sequence currents in the network are due to what? Zero sequence currents are due to what? Anybody? Zero sequence currents are due to what? Unbalanced loading. Unbalanced loading or unbalanced current flows. Zero sequence currents, what we are discussing in the present study, zero sequence currents due to unbalanced loading. Unbalanced loading on the system. Third harmonic currents are due to what? Third harmonic currents are due to what? Anybody? Third harmonic currents are due to what? Nobody is answering. Two chances are there to get the third harmonic current. Two chances are there to get the third harmonic current. One is a non-linearity in the transformer core. Non-linearity in the transformer core is one reason. Other reason is non-linear load. Load itself is non-linear and it's drawing some harmonic currents. Okay, two chances are there. One, due to transformer core non-linearity, Second reason to get the third harmonic currents is due to non-linear loads in the system. Maybe power electronic converters, rectifiers, these loads. Okay, non-linear loads in the system also causes for the third harmonic currents. Yeah. Next one. Listen here. Don't confuse. If it is zero sequence current, what I am talking about, zero sequence current, what I am talking, it should exist on both sides of the windings. It should exist on both sides of the windings. Right? It won't exist only one side. It won't exist only on one side. It should exist both sides. One side is providing closed path, other side is not providing, means the first side also current will become zero. First side also current will become zero. That's the thing. But you see, third harmonic currents, particularly due to transformer core nonlinearity. Transformer core nonlinearity means that that particular third harmonic current will be a magnetizing current. Will be a magnetizing current. Yes or no? That magnetizing component can exist only on one side also. Only on one side also. Even though the other side is providing closed path or not, doesn't matter. Only one side also, this third harmonic magnetizing current can exist. But third harmonic load current you have because of nonlinear load. Because of the nonlinear load, you may have third harmonic load current. But that load current should exist on both sides again. I don't know whether we have followed this or not. Have you understood this difference in the third harmonic current again? Two types of third harmonic currents you have. One is magnetizing current, other is a load current again. Magnetizing current can exist on one side, no issue. But load current should exist on both sides. Okay, so in my differences table, what I am giving here, third harmonic currents, particularly magnetizing currents, I am comparing. Only magnetizing currents I am comparing. Third harmonic load current will fall in the category of the zero sequence current only. Maybe frequency is different. Frequency is different, but it will have the property of the zero sequence current exact. Okay, Vinayak, as we move ahead, I will repeat the things, okay, wherever it is necessary. Let's write the things now. Differences. First difference, zero sequence current, it's a component of load current. Yes or no? It's a component of load current. Load current. And what about this third harmonic magnetizing current? It's a component of magnetizing current. Already we have given the name. Component or part also you can say. Component of magnetizing current in the transformer. Magnetizing current in the transformer. Okay. And this component of load current should exist on both sides. MMF balance must be satisfied. Should exist in both windings of transformer. Both windings of transformer should exist in both windings of transformer, comma, MMF balance must be satisfied. Balance must be satisfied. Okay, but third harmonic magnetizing current can exist only on one side. Can exist only on one side of transformer. One side of transformer. MMF balance need not be satisfied. MMF balance need not to be satisfied. Need not to be satisfied. Okay. What is the frequency of the zero sequence currents? What will be the frequency of the zero sequence currents? And what will be the frequency of the third harmonic currents? Frequency of zero sequence currents and frequency of the third harmonic currents. Zero sequence currents frequency is F. Third harmonic is 3F. Both are cophasal. Both are cophasal. That's why we are comparing these two, strictly speaking. Right? Cophasal in nature. Cophasal in nature. Currents are cophasal in nature. These are also cophasal in nature. That's the reason exactly why we are going with comparison. Cophasal in nature. The common property is asking us to go for differences. Okay. Now, as a conclusion question, I am asking you here. Yeah, please complete it first. Please complete it quickly. Yeah, both will have their own disadvantages. Unbalanced loading is a disadvantage to you. This non-linear waveform of the currents, magnetizing current and all, that's also a disadvantage to you, right? Last comment I want to make here. Delta star transformer. Zero sequence current will exist or not? Transformer connection. IA naught in I'll say simply zero sequence current. I will write simply. Zero sequence currents. Load component, of course. And you say third harmonic magnetizing current. Third harmonic magnetizing current. Magnetizing current. Quickly fill this table with a tick mark and a cross mark. If it is existing, just you put a tick mark, and if it's not existing, just you put a cross mark. Star unground, star unground. Tell me your answer, please. Star unground, unground. Y. Do you have zero sequence current? No. Do you have third harmonic current? No. No. Star ground star. Do you have zero sequence current? No. Do you have third harmonic magnetizing current? Yes, in the primary. In the primary. Star ground. Do you have zero sequence current? No. Do you have third harmonic magnetizing current? Yes, in the secondary. Delta star, sorry, star ground, star ground. Star ground, star ground. We have zero sequence currents. Yes, on both sides you have. Third harmonic magnetizing current. Yes, on both sides. Delta star unground. Do you have zero sequence currents? No. Do you have third harmonic magnetizing current? Yes. Where? In primary. In the loop. Circulates in the loop. Delta loop. Delta star ground. Do you have zero sequence currents? Yes. Third harmonic currents? Yes. Star delta. Star delta. Do you have zero sequence currents? No. Third harmonic currents? Yes. In the secondary. And then star ground delta. Star ground delta. Zero sequence currents? Yes. Third harmonic currents also? Yes. And delta delta idle. Delta delta. Do you have zero sequence currents? No. No. No zero sequence currents in the delta delta transformer. Third harmonic? Yes. In the loop. Have you understood this one? Have you understood this table? Good. Okay, so at this point we stop our discussion. Tomorrow we will start with one numerical. Okay, so after completing that numerical, we will move to transmission line, positive, negative, and zero sequence networks construction. Okay, so we will pick up the doubt session now. If you have any doubts, you can raise your hands. Win.
Sir,
Tell me, Mubin.
sir, this third harmonic current, what is this actually, sir?
Have you completed transformer subject?
Yes, but in college, sir, but not in this.
Okay, anyhow, even though if you have completed in college, you might be knowing, right? In the 4-year series,
Yes, sir, that base.
that current only, that third harmonic component only we are saying.
Sir, we are seeing it as same as zero sequence current concept like that only, sir.
Same as zero sequence concept, but if it's a magnetizing current, it can exist only on one side also.
Okay.
It no need to exist on both sides. MMF balance N1I1 equals to N2I2 need not to be satisfied if it's a magnetizing current.
Okay. Sir, one more, sir. Sir, zero sequence and third harmonic are cophasal. Both are cophasal, sir.
Yes, yes.
Sir, it means third harmonic current of phase 1, phase 2, phase 3. Like that, we also have phasors, sir.
Yeah. Phasors, but they will rotate at 3 times of synchronous speed.
Okay, yes, sir.
Hmm.
Sir, and sir, please go to page 50, sir, 50, 51.
Okay.
Go, sir, forward, sir, 51.
Okay.
Sir, here what conclusions we made, sir? Please, can you please explain it one more?
Okay, to check, to know whether the transformer is providing closed path for zero sequence currents, you should check what is the primary connection and secondary connection.
Okay.
If primary winding is providing closed path,
Okay.
secondary winding is also providing closed path,
Okay.
then we can say that transformer is allowing closed path for zero sequence currents.
If any one is not providing, then not
Then the other winding will also will not provide,
only zero sequence.
only zero sequence.
Yes, sir. Thank you, sir. If
Okay.
any more, I'll ask later. Thank you.
Yeah. Vaishnavi.
Sir, in 34F, sir, 34.
Ah.
సార్ ఇక్కడ రియాక్టెన్స్ ఓన్లీ డైరెక్ట్ యాక్సిస్ ఏ ఉంటది, క్వాడ్రేచర్ యాక్సిస్ ఉండదు అన్నారు కదా సార్, అది ఒకసారి మళ్ళీ చెప్పరా సార్?
See, generally we have some leakage reactance for alternator. Along with that, we have some armature reaction reactance.
Sir, can you repeat, sir? I lost network, sir.
Yeah. Generally, we have some leakage reactance for alternator.
Yes, sir.
Along with that, we have some armature reaction reactance also.
Yes, sir. Yes, sir.
What do you mean by armature reaction? Effect of armature flux on main field flux.
Yes, sir.
Okay. Now,
Yes.
see, armature flux, sorry, main field flux is rotating in this direction where I have shown here.
Yes, sir.
Armature flux also rotating in the same direction.
Because it is because of positive sequence,
Positive
it is.
sequence. Positive sequence. So then, can I say that armature flux will lie always along direct axis only?
Yes, sir. Yes, sir.
So this armature flux is showing its effect on main field flux only along the direct axis,
Yes, sir.
right? So only direct
yes.
axis reactance itself is sufficient to do the analysis.
Okay, sir. Okay,
Whereas,
sir.
if you see negative sequence here, main field flux is rotating in one direction, armature flux is in the opposite direction.
Yes, sir.
How is the effect of armature flux on main field flux continuously changing with respect to position?
Yes, sir.
So it may vary between the direct axis and quadrature axis, right?
Okay, sir.
Understood. Just if you stand on the rotor, how is the negative sequence RMF for you? Rotating continuously.
Yes, sir.
At some time, that armature flux phasor is at this place. At
Yes,
some
sir.
other time, it may come here.
Yes, sir.
At some other time, it may come here.
Okay, sir. Okay.
At some other
ఇక్కడ
time, it may come
armature
here.
flux
It may
అనేది
come here. It may come here. Like that, it is continuously changing its position.
Okay, sir.
Then how is the effect of this armature flux on the main field flux changing with respect to time, right?
Yes, sir.
That's why armature reaction will change. Reactance also changes between direct axis and quadrature axis.
ఓకే సార్. ఓకే సార్, మరి ఇప్పుడు ఆర్మేచర్ రియాక్షన్ ఉండడం వల్ల మనకి యూసా కాదా సార్?
We have both advantages we have as well as disadvantages also.
ఓకే సార్.
Disadvantage is more voltage drop.
ఎస్ సార్.
Advantage is short circuit level will be less.
ఓకే సార్.
Okay. And one more disadvantage is it makes this analysis cumbersome, like this, very difficult. We don't have armature reaction alternator. Half of the electrical engineering, particularly power system analysis, will be easy.
Okay, sir.
Because of armature reaction only, all these analyses are becoming a bit complex.
ఓకే సార్. ప్రీవియస్ చాప్టర్లో ఒక క్వశ్చన్ చెప్పారు కదా సార్, అంటే ఎక్స్ పర్ యూనిట్ ఎక్స్ యాంగిల్ తీటా, ఆ క్వశ్చన్ ఉంది కదా సార్. అది అక్కడ x/√3 ఎందుకు అవ్వకూడదు? ఇప్పుడు లైన్ అనేది లైన్
on the respective base values means phase voltage per unit value, line to line per unit value, I will take same.
Phase voltage per unit value, line
to line voltage per unit value, I will take same in magnitude.
Okay, sir.
But phase voltage is on the phase voltage base.
Yes, sir.
Line to line voltage is on the line to line voltage base.
కానీ అంటే ఇప్పుడు అన్బ్యాలెన్స్డ్
By
సిస్టమ్
that way, the √3 will go out, right? Tell me. You are asking some more.
అదే సార్, అంటే ఇప్పుడు అన్బ్యాలెన్స్డ్ సిస్టమ్ లో మనకి అబ్సల్యూట్ వాల్యూ కావాలంటే మనము వి బేస్ సర్ఫేస్ తోనే
Yes, correct.
multiply.
Hmm.
అప్పుడు ఇక్కడ మనం బేస్ మీద ఏమి డిపెండెన్సీ అట్లేం ఉండదు కదా సార్. మళ్ళీ
ఉండదు.
మనము
మరి మీకు డౌట్ ఏంటి అక్కడ? వాట్స్ యువర్ డౌట్? ఎగ్జాక్ట్ డౌట్ దేర్.
అంటే ఇప్పుడు ఫేస్ అనేది x/√3 ఎందుకు రాకూడదు అని సార్ డౌట్.
బ్యాలెన్స్, రైట్?
న్యూట్రల్ సప్లై అన్బ్యాలెన్స్డ్ కదా సార్.
What is positive sequence? Are you doing analysis of whole system or only positive sequence there?
Only neutral sequence. Only positive sequence.
Only positive sequence means positive sequence alone is balanced, right?
Yes sir.
Then that √3 line to line voltage base, per phase voltage base, all these things can be used.
ఓకే. అంటే ఇప్పుడు ఇది బ్యాలెన్స్డ్ కాబట్టి ఇప్పుడు మన పర్ యూనిట్స్ అనేవి మాగ్నిట్యూడ్ సేమ్ ఉంటాయి అని చెప్తామా సార్?
Yes.
ఓకే సార్.
Okay.
ఓకే సార్.
Prudviraj.
Hello sir.
Tell me.
Sir, alternator ke the conditions for rotating magnetic field creation చెప్పారు కదా సార్. సార్ దాంట్లో నెగటివ్ సీక్వెన్స్ RMF అనేది ఎలా ప్రొడ్యూస్ అవుతుంది అని ఒకసారి చెప్తారా?
We have negative sequence currents in the stator.
హలో సార్.
We have negative sequence currents in the stator.
ఓకే సార్.
Those are balanced three phase currents.
ఓకే సార్.
3 windings physically displaced by 120 degree.
ఓకే సార్.
Conditions are sufficient, right, to create RMF.
ఓకే సార్. సార్ నెక్స్ట్ పాజిటివ్ సీక్వెన్స్ ఎక్స్ప్లెయిన్ చేశారు కదా సార్, డి యాక్సిస్ కి క్యూ యాక్సిస్ గురించి. సార్ దాంట్లో డి యాక్సిస్ కి క్యూ యాక్సిస్ కి ఫై అయ్యే ఉన్నాయి కదా సార్, అంటే ఒకే డైరెక్షన్ లో తిరుగుతున్నాయి కదా సార్.
అవును
సార్. ఇప్పుడు ఇది రోటర్ తిరిగి క్యూ యాక్సిస్ మీదకి వచ్చినప్పుడు 5A2 కూడా క్యూ యాక్సిస్ మీదకి వచ్చింది కదా సార్.
5A2
అంటే దీని ముందు స్లైడ్ సార్.
what do you want? Is it positive sequence or negative sequence?
పాజిటివ్ సీక్వెన్స్.
This one?
దిస్ వన్ సార్. ఇఫ్ ఇట్ ఈస్ రొటేటింగ్
Wait. Both are rotating, na?
బోత్ ఆర్ రొటేటింగ్ సార్.
Tell me, what's the doubt you have now?
ఇప్పుడు రెండు క్యూ యాక్సిస్ లోకి వచ్చాయి కదా సార్ అలైన్మెంట్.
Q axis also rotating, right?
ఓకే సార్.
Direct axis is rotating, quadrature axis is also rotating.
ఓకే సార్. దెన్ ఓకే సార్.
Okay?
ఓకే. That's it, sir. Thank you.
Okay. Sharath.
Sir, good evening, sir.
Good evening, Sharath. Tell me.
Sir, I have a doubt that how negative sequence currents will flow. Sir. Means
Actually, the system don't know about the positive, negative, and zero sequences.
yes. Sir.
System knows about only IA, IB, IC.
Okay.
Mathematically, we are dividing these currents into positive, negative, and zero sequence components.
Okay. Sir.
Some current is flowing, the system don't know. Is it a positive sequence or negative sequence or zero sequence? The division we have done for our analysis sake.
Means when the negative sequence currents will flow, the rotor MMF will rotate in opposite directions.
Actually, if the stator is carrying unbalanced currents in the air gap of stator, you get a positive sequence RMF as well as a negative sequence RMF.
Okay.
Both. But strictly speaking, what you should say is the rotating magnetic field is not a proper rotating magnetic field because of this resultant.
Okay.
Understood what I am saying?
Yes.
Yeah, that's the resultant thing. What the rotor or that RMF is going to experience.
Okay.
Okay, but For our analysis sake, for understanding sake, we are dividing that into positive sequence, negative sequence, and we are continuing to do the analysis.
Okay, sir.
Okay.
Yes, sir.
Tell me,
Sir,
any other
actually,
doubt you have, Sharat?
yes, sir. What is the difference between that symmetrical and unsymmetrical, sir?
Symmetrical and unsymmetrical. Symmetrical, you say it's a balanced sometimes. Unsymmetrical, you say unbalanced.
Means we are when unbalance takes place, we are getting the symmetrical components. We are dividing.
We are applying symmetrical components means unbalanced set is converted into set of balanced.
Okay, using that positive negative sequence, we'll get balanced. Okay, sir. And what is the difference between linear loads, non-linear loads, and balanced, unbalanced?
Balanced load means all the three phases are experiencing equal amount of load.
Okay.
For example, if it is one load you have, star connected load, if all these three load impedances are equal, 100 ohms, 100 ohms, 100 ohms, resistors, then it's a balanced one, right?
Yes, sir.
If one of the load was changed to, let us say, 60 ohms, then it will be unbalanced.
Yes, sir.
It's an unbalanced load. Okay?
Okay.
See, linear loads in the sense, if the load is consisting only RLC elements, then it's a linear one.
Okay, sir.
Like your induction motor.
Yes, sir.
Okay, like a fan.
Okay, sir.
Okay, those are nothing but simply resistive, inductive, and capacitive elements only. That's a linear load.
Okay.
Non-linear means if there's any power electronic converters.
Okay.
Like you see dimmer in your house, electronic regulator,
Okay.
which is used to control the voltage. Whenever it's controlling the voltage, definitely it will introduce some harmonics.
Yes.
It's a type of non-linear one.
Means non-linear load means it is the
Which
effect of
introduces harmonics, which will be using analog or power electronic components for controlling purpose, particularly.
Okay.
By means of that control, maybe they are using some sort of thyristor or something, which are having some switching timings and all. Because of that, there may be some harmonics introduced into current.
Okay, sir.
Okay, that's a non-linear load.
Okay. Okay, that's it. Thank you, sir.
Okay, any other doubt you have, Sharat?
No, sir, that's it.
Yeah. Tulasi.
Hello, sir.
Tulasi.
Sir, in 51.
1. Okay.
సార్ ఇప్పుడు క్లోజ్డ్ పాత్ ఉండాలి అని చెప్పారు కదండి సార్. కనెక్షన్స్ విచ్ అలౌ ద క్లోజ్డ్ పాత్ ఫర్ జీరో సీక్వెన్స్ కరెంట్స్ అని. ఇప్పుడు డెల్టా దాంట్లో చూసుకున్నప్పుడు ప్రైమరీ సైడ్ క్లోజ్డ్ కనెక్షన్ ఉండదు కదండి.
డెల్టా వైండింగ్.
ఎస్ సార్. డెల్టా అండ్ స్టార్ విత్ ఇంపెడెన్స్ గ్రౌండెడ్.
Delta closed, star grounded also closed, right?
సార్ ప్రైమరీ సైడ్ క్లోజ్ కాదు కదండి సార్.
Winding.
ఓకే.
If windings are carrying, I will say transformer is carrying, right?
ఓకే. అప్పుడు ఇంకొక సెంటెన్స్ కూడా చెప్తున్నారు కదండి సార్, ప్రైమరీ ఎగ్జిస్ట్ అయితే సెకండరీ ఎగ్జిస్ట్ అవ్వదు అని.
Okay.
అప్పుడు ఇక్కడ డెల్టా దాంట్లో ప్రైమరీ
lines we don't have, but primary windings we have, right? Winding.
ఓన్లీ వైండింగ్ కన్సిడర్ చేయాలి.
Winding, not lines.
ఓకే సార్, థ్యాంక్ యూ సార్. నెక్స్ట్ ఇన్ 56F సార్.
Okay.
సార్ ఇక్కడ ఆ థర్డ్ హార్మోనిక్ ఎగ్జిస్ట్ అవుతుందా లేదా అని ఎలా చెప్తున్నాం సార్ మనం?
Any one winding is providing closed path, it will exist. That's it.
ఓకే, క్లోజ్డ్ పాత్ ఉంటే.
Except star unground, remaining all transformers will have third harmonic magnetizing current in any one of the winding or in both windings also. For example, you have written star ground. Here it will have both primary and secondary will have.
Okay. Sir, in 34F. సార్ నెగిటివ్ సీక్వెన్స్ కి సార్ అంటే ఇంత రొటేషన్ చూపించారు కదండి సార్ నెగిటివ్ సీక్వెన్స్ కి ఒకసారి అలా చూపించారు
Negative sequence, it's not possible.
అంటే చేంజ్ అవుతుంది కదా అప్పుడు క్యూ యాక్సిస్ మీద కూడా వెళ్తుంది కదండి సార్ ఇది
Mhm. Okay, 1 minute. So this is stationary now. That rotor axis, what we said, that is stationary.
స్టేషనరీ
We are standing on that,
ఓకే సార్
and this is rotating.
రొటేట్
That rotation is not whole rotating. May rotate like this
ఎస్ సార్
at some time, right?
ఎస్ సార్
Means now you see how is that pi A2 effect on phi rotor? Position was changed or not?
ఎస్ సార్ అపోజింగ్
Again, it may rotate something like this. Chance is there. 1 minute.
ఓకే
Like this, it may rotate
ఎస్ సార్
after some time. Then again, position was changed for phi A2.
ఎస్ సార్
Effect is different now.
ఎస్ సార్
Again, if it is rotating something like this, it's going in this direction. Then again, position is different for phi A2.
ఎస్ సార్
Like that, whenever it is continuously rotating, position of phi A2 with respect to phi rotor is continuously changing. Sometimes that armature flux will show its effect on main field flux along the direct axis.
ఎస్ సార్
Sometimes those two will be superimposed, sometimes opposed, sometimes makes 90-degree positive, sometimes makes 90-degree negative.
నెగిటివ్ ఓకే
Okay, so that phi A2 armature flux may lie on the direct axis or may lie on the quadrature axis,
ఎస్
but rotor flux will lie always along the direct axis.
డైరెక్ట్
So the effect of the armature flux on the main field flux continuously changing between the direct axis and quadrature axis.
ఎస్ సార్
Okay,
ఎస్ సార్ గాట్ ఇట్
Yeah.
సార్ ఇన్ 19 ఎస్ సార్
what is that number?
19
19.
ఎస్ సార్ 19
Okay,
సార్ హియర్ దెన్ ఆ డయాగ్రామ్ ఒకసారి ఎక్స్ప్లెయిన్ చేసి
which diagram?
జీరో సీక్వెన్స్ సర్క్యూట్ నెట్వర్క్
This network we have drawn on our own way to meet the conditions.
ఓకే సార్
Okay, what are the conditions we have? Winding should allow zero sequence current, line should not allow.
ఎస్ సార్
So line must be kept open,
ఓకే
but winding should be closed.
క్లోజ్
That's it. That statement we implemented in the network.
ఓకే సార్ ఇక్కడ ఇది మరి ఐఏను ఎందుకు సార్ ఇలా తీసుకున్నాం మనము సేమ్ ఫేజ్ లో ఉన్నట్టు కాంపోనెంట్ సిమెట్రికల్
Because already you have considered IA in certain direction, right?
ఓకే సార్
What you are writing IA formula?
IA is equals to IA1 plus IA2 plus IA0
When we can sum up the three currents, if all the three are flowing in the same direction.
same direction. Yes sir, yes sir, I got it.
Okay, okay.
Yes sir.
Any other
Sir.
doubt you have, Tumsi?
Yes sir, నిన్న ప్రాబ్లం లో సార్ సెకండ్ యూనిట్ లో ఒక ప్రాబ్లం సార్ అది 1 minute సార్ సార్ ఇక్కడ లోడ్ కరెంట్ అడిగారు సార్ ద ఫేజ్ సీక్వెన్స్ కాంపోనెంట్ ఆఫ్ లోడ్ కరెంట్ ఆ క్వశ్చన్ లో అప్పుడు సమ్మేషన్ తీసుకోవాలి కదండి సార్ మనము ద పాజిటివ్ సీక్వెన్స్
Load current means you have to find out only phase A load current.
ఓకే
Only phase A.
సార్ అంటే ఇప్పుడు IA1 ప్లస్ IB1 ప్లస్ IC1
That
అది
becomes zero.
అవును సార్
What you do with that?
అంటే పాజిటివ్ అప్పుడు జీరోనే వస్తుంది కదా సార్ మనకి పాజిటివ్ సీక్వెన్స్
He is asking only what is the positive sequence component of the load current.
లోడ్
If I am asking you what is the load current in a three-phase system, will you answer some of the three currents or only one phase current?
సార్ సమ్ ఆఫ్ ద లోడ్ ఐ డిడ్ంట్ గెట్ ద క్వశ్చన్
I have a three-phase load.
ఎస్ సార్
Okay, three-phase load,
ఓకే
and it is drawing some power and some operating at some voltage.
ఓకే సార్
I am asking you what is the current drawn by the load. what you answer? Will you answer only one phase current or some of the three phases currents?
Only one phase.
That's it.
Okay.
That's the logic, right?
Okay, sir. Got it. Oh. That's all, sir. Thank you, sir.
Okay, fine. Muhammad Fayazuddin.
Hello,
Tell me.
sir. In sequence network construction, sir. Sequence network construction kada pondi, sir. In that, in sequence network construction, we have taken 3 times of for a zero sequence equivalent network. We have taken neutral impedance as 3 times of Zn.
Okay.
Because to consider 3 times of Ia effect.
Okay.
That is the reason to take 3 times of Zn neutral, na, sir.
I don't know all those things actually. I got my equation as Z0 plus 3Zn.
Yes, sir. 3 Z. That means
you tell what is the first one, what is the basic one you got. After that, what you have concluded, that you have to learn.
Yes, sir. We have taken 3 times of Zn neutral in that equivalent zero sequence network, na, sir.
Why we have taken? Why we have taken?
To consider 3 times of Ia not current, na, sir.
Not that. I have applied KVL for this phase A loop.
Yes.
I ended up with this equation.
Yes.
I have to represent this equation in the network manner.
Okay.
For that purpose, I have to keep an impedance of Z0 plus 3Zn.
Okay.
So I kept Z0 plus 3Zn. Later on, we concluded something.
Okay.
But what you should know is what the original one first.
Okay.
You should not say that ground or neutral is carrying 3 times of INR. That's why I'm keeping 3Zn here because current is INR. That is having some sort of lack of clarity. So we applied KVL for phase A loop. I got the impedance as Z0 plus 3Zn and current flowing in the circuit is INR. So in a INR current flow circuit, I should keep Z0 plus 3Zn as an impedance.
Okay.
Later on, the upper node of 3Zn is having a voltage as neutral voltage.
Yes.
Then I identified that point as a neutral in the zero sequence network.
Okay. Sir, I have some doubts, sir. Why we use this symmetrical analysis, or why we sort of take these unbalanced means these all things.
What
there is
type
a
of loads you have in
practical
your system?
unbalanced loaders, sir. But where we use, like in practical life, like power factor has
Unbalanced
some
network analysis, we will use this one. Particularly during short circuit fault, the system is becoming unbalanced.
Okay, but what we have, sir? What we do with that?
What we do with that means?
Means like in string efficiency, we just calculate insulating stress of insulator, na, sir. Such that we remove insulator and we keep new insulator at that point. So we have some meaning of that. We have some active meaning of that concept, na, sir, string efficiency. So what we have a powerful, that means what we have a active meaning of calculating all these, that means what is the need?
Okay, why we are studying about this unbalanced network, symmetrical components and all?
Yes, sir, that's what I'm asking.
Fault analysis.
Okay.
Again, your doubt is, what is the purpose of fault analysis?
Yes, sir. Fault analysis means when fault occurs, we need to calculate the rating of circuit breaker. Anything.
If it's during that short circuit fault, if the system is unbalanced.
Okay.
How to do that fault analysis?
Okay.
Getting me? Faizaluddin,
Yes, sir.
are you getting me?
Yes, sir, I am getting.
If the system is becoming unbalanced during a short circuit fault, definitely we have to follow symmetrical component study to do that fault analysis.
Okay. Okay. That's
So
it.
symmetrical components, simply it's a mathematical tool to
Okay.
analyze an unbalanced system of any kind.
Mm-hmm.
Okay, one such kind of thing we are going to discuss in the fault analysis.
Okay. That means any practical application, sir. That means
Practical
in
application means
grid application.
to do fault analysis. Why you are doing fault analysis again? Breaker rating selection, relay selection.
Yeah, that's the thing. Yeah.
But that is going to be done by fault analysis. To do fault analysis, we need symmetrical components.
Okay.
Without symmetrical components, can you do unbalanced fault analysis?
But approximately we can do by just
How?
the symmetrical fault analysis. No, sir. Just
Without symmetrical components, it is not possible to do the unbalanced fault analysis. Okay, approximation means you do that fault analysis without symmetrical components. You got the breaker rating as 100 MVA. Can it maybe by doing this symmetrical component study, I will get the breaker rating as 150 MVA. If you design a breaker rating of 100 MVA and you keep it in the system, but the actual fault level is greater than that, your breaker will damage.
okay.
Okay, but you may say something that, sir, by doing that without symmetrical components, I got 100. Okay, it's an approximation. I will make it as 200. You might be designing a 200 MVA breaker and you will be keeping in that system. Your breaker is safe, but you have spent a lot of money excess.
Okay.
Okay, for appropriate design of the circuit breaker and relay setting selection, it is required to go with the symmetrical component study for the unbalanced fault analysis.
Okay. Thank you, sir.
Okay. Sai Charan.
Hello, sir. Good evening, sir.
Good evening.
Sir, in balanced system, like we took some for finding, we derived some equations like for finding absolute values of line and per phase quantities of voltage and power. Sir, in that, why do we took this mod for voltage, sir, VAB?
Generally, if I write simply V, that is having some magnitude and angle, I said, right?
Sir, due to some network connection, I have
if I write simply some voltage V,
angle.
If I write simply some voltage V, what you have to understand from this, I said, it's having some magnitude as well as some angle, right?
Yes, sir.
But what is our
what
interest
would be the
there?
problem of taking?
What is our interest there? Our interest is to find only magnitudes, right?
Okay, sir.
That's why we have taken indicated that specially mod V.
Okay, sir.
Okay.
Sir, in steps to be followed in analysis of unbalanced system. Sir, in that fourth step, give connection between sequence network by following relation obtained in step 2.
Okay.
Understood this point.
No, that you will come to know if you move ahead. That's not end of those the topic actually.
Okay, sir. Okay.
Just to introduce the sequence networks, I discussed about it.
Okay, sir.
You will be cleared if you move on.
Okay. Sir, in alternator, sir. In alternator sequence network. In negative sequence network, we did not. You told that EMF will be 0 for 0 sequence and negative sequence. No, sir. Then in phasor diagram again in quadrature axis and Q.
That is a positive sequence induced EMF only, EA1.
No, sir, IA2, sir, negative sequence in case of negative sequence.
Whatever the EMF I have drawn there, that's a positive sequence EMF only.
Sir, can you please open 36th page, sir?
This is EA1 only.
Yes, sir, EA1 only. But from where do IA2 came from? I am asking, sir.
IA2 is coming due to the unbalanced nature of current flow, right? You have IA1. If you want me to show, I will show IA1 also here.
I was in the opinion that we don't get EA2, then how we got
EA2 is not there. The EA2 I have not shown. It's a simple induced EMF I said means it's a EA1.
Okay, sir. Because of unbalanced current unbalanced only, we got.
We are getting IA2 and phi-A2.
So unbalance of the whole source or unbalance of negative sequence, sir?
You only have to tell unbalancing of source
Yes, sir.
or
Unbalance of source. Okay.
unbalance of
Source, sir. Source.
why source is unbalanced? Source voltages are
If
equal.
If source is
Load is
unbalanced, only we
unbalanced.
will. Yes, sir. Yes, sir.
Load is unbalanced. That's why source is delivering unbalanced currents.
Okay.
Okay.
Sir, in transformers, you told we should neglect the line and we should only see the windings of primary and secondary, sir. But in star and star transformer, you did not say that there is a zero sequence current, no, sir.
Star ground and star.
No, sir. Normal star and star.
Star unground, star unground.
Yes, sir.
You don't have zero sequence currents. What's the doubt in that?
Sir, can you please open that, sir?
Okay. Both sides open, no, Charan?
So, if you take below one, we will have a continuity. So we should take Z0 as a primary and secondary, sir. Both primary and secondary.
Z0 will have half primary, half secondary.
Okay, sir. Okay. Another one, last one. Sir, in MSQ question. Sir, here why D is correct, sir, in MSQ?
All are acting as open circuits.
But if you neglect line here, there would be a closed circuit for a winding, primary winding. Sir.
Where?
In option D, sir.
Option D.
Yes, sir.
D or B? Bombay or Delhi?
Delhi, sir. Delhi.
It is open this side. It is open this side.
So, according to you said that we should neglect line. So, if we neglect line and we connect across this winding after the switch, then it would be closed circuit, no, sir.
But you see, if you see transformer block, transformer, you see transformer outside, right?
Yes, sir.
Which is accessible to you? Windings or lines?
Winding.
Which you can touch.
Sir.
Which you can touch.
Lines.
Where you can inject the current.
Lines only, sir.
Where there is a possibility of getting fault. Lines.
Yes. So I am confused with this both, sir. In one case you told we should neglect lines, and here you told, sir, we should take outside terminals. In both of them, I have confused.
Sorry, we have to inject the current at the lines.
Okay, sir.
By injecting current at the lines, you should check whether that current is flowing into the circuit or not.
Yes, sir.
Okay. When it will flow into the circuit means if both windings are providing closed path.
Okay.
Both windings should provide the closed path.
Yes,
and the
sir.
current should enter from any one of the line, primary line or secondary.
Okay.
Okay, have you understood? If you have any doubt, ask me. Be clear.
Okay, sir. You told that if the primary is provided something you told, sir.
If primary winding and secondary winding both are providing closed paths,
Okay, sir.
Then I will say transformer is providing closed path for zero sequence currents. Because zero sequence current can't exist only on one side.
Okay, sir.
If it is existing, it should exist on both sides.
Okay, sir.
Else, no side.
Yes, sir.
Okay.
Yes, sir.
So if both windings are providing closed path and one of the winding is star grounded, then transformer will allow closed path for zero sequence currents.
Okay, sir. Yes, sir. Thank you, sir.
Okay, correct. Gurudatta.
Hello, sir.
Tell me, Gurudatta.
36 app, sir, please.
What is it?
36 app.
Okay.
Sorry, sir. Next page. Sir, here how we say that negative sequence of reactance of alternate is constant.
It's variable.
Oh, sorry. I say I write it constant, sir.
No,
Okay, sir,
it's
got it.
variable.
Okay, sir, got it.
That's it.
Okay, sir.
Variable, as it's variable, we are assuming that as a constant number xp double dash plus xq double dash by 2 as an approximation.
Okay, sir.
Okay. Pallavi.
Sir, 31F. Diagram, sir. Next. So diagram that consists negative sequence RMF and positive sequence
Which one?
RMF. No, sir. Negative sequence and positive sequence RMF and we consist rotor. Yes, sir. So here this synchronous speed rotor initially that rotated in synchronous speed and positive sequence RMF is induced. Okay, and also it has negative sequence RMF, but both are in opposite direction, na sir? Positive and negative.
Yes,
and
yes.
I understood this, but sir, RMF rotor rotate with 2 times of synchronous speed. How, sir?
No. With respect to rotor, negative sequence RMF rotates at 2 ns.
Means negative sequence RMF. Okay, sir. Only that.
Not total RMF, only negative sequence.
Only negative sequence RMF at speed is.
That's what we have written, I think, here.
Flowing rotor.
You see, relative speed is 2 ns between negative sequence RMF and rotor.
Okay, sir. That's only confusing. I think relative speed between them.
No.
Okay, sir. Thank you.
Okay. Any other doubt you have, Pallavi?
No, sir.
Soundarya. Soundarya, do you have any doubt?
Hello, sir.
Tell me.
79F, sir.
79.
Yes, sir. 79F.
79 we don't have today, I think.
Power 3 phase equals to per phase power, sir.
Okay.
In Y multiply of 3, sir.
If you want to get 3-phase power in a balanced system, 3 into per phase power you will write, right?
What, sir?
3-phase power in a balanced system is equals to 3 into per phase power.
Okay, sir. 34F, sir. Sir, once explain IA flux A1 and E rotor flux, sir. Once phasor diagram explains.
No, these are rotor flux we have. And 90-degree lagging, in 90-degree lagging, we will have an induced EMF.
Yes, sir.
Sequence induced EMF. 90-degree lagging to that, we have the positive sequence current. Because we assume that network is purely reactive, current is 90-degree lagging.
Okay, sir.
And if these phasors are rotating, always this armature flux will be along the direct axis only. Because it is a D axis, right?
Yes, sir.
So, effect of this armature flux on the main field flux will be acting only on the direct axis.
Okay, sir.
So armature reaction is constant.
Yes, sir. Sir, another one, sir. Yesterday problem.
Ah.
Three-phase system is said to be balanced MSQ question, sir. Three are same na, sir. Positive also balanced and negative sequence also balanced. Option C is positive and negative. Which MSQ question? Which one is selected, sir? Answer.
Anil.
So good evening, sir.
Good evening, Anil.
Sir, in 37, sir.
37. Okay.
Sir, how we can conclude that equations are x2 equal to?
We have two numbers, xd double dash and xp double dash.
Yes, sir.
Value is varying between the two.
Direct axis and quadrature axis. Sir, in last slide, sir, before.
What is the number? Can you tell?
Sir, 84F, sir.
84. That's the previous chapter, right?
It's the previous chapter.
Tell me, Anil, what's the doubt you have in that?
Sir, in this unbalanced system means we can conclude that. Sir, you have said that from points and I did not get that point.
Read it.
Sorry, in unbalanced system means we can conclude that absolute to convert to absolute form. Always we can multiply to s per base per base per base, sir. And suppose it is balanced system means I did not get that point, sir. Unbalanced
The balanced system, either you can use s base per phase or s base 3 phase.
S base per 3 phase.
If you multiply with s base per phase, you get per phase power.
Okay, sir.
If you multiply with s base 3 phase, you get 3 phase power. In case of balanced system.
Balanced system. Okay, sir. Thank you, sir.
Okay.
హలో సార్ సార్ అది మామూలు లోడ్ కరెంట్ వచ్చేసి సమ్ ఆఫ్ త్రీ కరెంట్స్ అంటాం కదండి సార్ మామూలుగా.
No. Load current means any one of the phase current you say, right? In the three phase system. If you make a sum, you should say current is 0. That's a neutral current.
ఎస్ సార్.
Load current means any one of the phase current.
ఎనీ వన్ ఆఫ్ ద ఫేజ్. ఒకవేళ అన్బ్యాలెన్స్డ్ లో అయితే సమ్ ఆఫ్ త్రీ కరెంట్స్ వస్తుంది కదండి సార్.
Some of the three currents also you should not say anywhere.
Okay.
If asking neutral current, then only you should say sum of the three.
Three
If
currents.
the unbalanced one, you should say phase A current, phase B current, phase C current, all the three.
ఓకే. అక్కడ అప్పుడు పాజిటివ్ కాంపోనెంట్ ఫేజ్ కరెంట్ అన్నప్పుడు అప్పుడు ఏ ఫేజ్
Any one of the phase will have same current, right? Positive sequence.
ఎస్ సార్.
Same magnitude.
ఎస్ సార్. ఈ రోజు చెప్పిన దాంట్లో పేజ్ నెంబర్ గుర్తులేదు సార్. డెల్టా వైండింగ్ ముందర కొన్ని స్టేట్మెంట్స్ చెప్పారు కదండి సార్.
Yes.
దాంట్లో లాస్ట్ లో ఒకసారి ఎక్స్ప్లెయిన్ చేయండి. ఎస్ సార్. లాస్ట్ వన్.
0, then always Vn equals to 0.
ఎస్ సార్.
For example, you take this circuit. This one you take.
ఎస్ సార్.
Va0 equals to 0.
ఓకే.
You assume that whole network is reactive. 3 Zetan also reactive in nature.
ఎస్ సార్.
Two reactors in series.
ఎస్ సార్.
Total voltage across that combination is 0.
0.
Means obviously each reactor voltage will be 0 only, right?
ఎస్ సార్.
Then obviously your neutral voltage is also 0.
0. ఓకే సార్.
Okay.
సార్ ఇంకొక
You have a combination of inductor, capacitor and connected in series. Overall voltage is 0. Then inductor voltage may not be 0. Capacitor voltage may not be 0. That's a different issue.
ఓకే సార్. We
That's
want
why
to
I have added one word as practical.
Okay, practically.
Practically means that capacitive neutral grounding may not be practical for us.
Okay.
Either we go for resistive grounding or reactance grounding.
Ground. Sir, in 13F, sir.
Okay.
సార్ ఇక్కడ విఎన్ కూడా 0 అవుతుంది కదండి సార్, అది
Why?
ఎలా వచ్చింది సార్? అంటే వోల్టేజ్ ఏం లేదు కదండి సార్. ఇప్పుడు ఇన్ఫైనైట్ ఇంపిడెన్స్ ఉన్నప్పుడు 0 వోల్టేజ్ ఉంటుంది కదండి సార్.
Is that
జీరో అవ్వదు. 10 into 1/1 + 2 5 volts ఉంటుంది.
what is current? What is current?
కరెంట్ 0 అవుతుంది సార్ అక్కడ.
0. What is this voltage?
5 volts.
0 into infinite.
Yes
Current
sir.
is 0, impedance is infinite. 0 into infinite, it's undefined.
Yes sir.
Means by this open circuit, 0 into infinite, I can't say what is that voltage.
Yes sir.
But it may exist from this circuit.
5 volts ఇక్కడ నుంచి చూస్తే ఎగ్జిస్ట్ అవుతుంది కదా.
So we don't know, right? Just I will clear this one. I will clear this one. Now tell me how much is this voltage?
We don't know sir.
We don't know.
Okay.
It may be 0, may not be 0, right?
Yes sir.
Who will decide it?
Okay sir.
Remaining part of the network.
Okay sir. Thank you
Okay.
sir. Okay, thank you.
Anil.
Hello, sir. Good evening, sir. Hello, sir. Am I
You may
audible?
tell me, Anil.
Yes, sir. I have a doubt regarding on today's class, sir. That is the difference between zero sequence current and the third harmonic current.
Okay.
In that, we have to set one point. Second point, that is zero sequence current can exist in both windings of transformer. MMF balance must be satisfied. What is meant by that MMF balance?
Primary MMF equals to secondary MMF.
Yes, sir. I know, sir.
That's it.
Why it is not? Why it is satisfied here?
Why it is?
Why it is must satisfy here?
If it is load current, it should be transferred from one side to other side, right? In the transformer.
Yes, sir.
Then if load current is not existing on one side, it won't exist on the other side also.
Okay, sir. Okay, sir. I got it, sir. Now.
Okay.
Okay, sir. Sir, I have a doubt in yesterday's problem, sir. Sir, can I read, sir?
Yeah, read it.
In an unbalanced three-phase system, the phase current IA is equal to 1 at an angle minus 90, sir, per unit.
Okay.
Negative sequence current of IB2 is equal to 4 at an angle minus 150 per unit.
Okay, what's the doubt you have in that?
I have a doubt regarding on how you calculate IA2.
IB2 already have.
Yes, sir. IB2 you have. Along with
You
that,
have to shift it by
IA
some angle to get IA2, right?
Sir, yes, sir. In that, how you get that IA2? I
You
cannot.
draw that negative sequence phasor diagram roughly.
Okay, sir.
This is A2. This is
yes,
C2.
C2.
This is B2.
Yes, sir.
Which value you know?
I want to know I2.
Which
IA2.
value you know? Which value you know?
You know IB2.
B2 you know.
Yes,
Which
sir.
value we have to get?
IA2 you know. You
A2.
want to get.
So B2, if you shift by an angle of 240 degree, you will get A2, right?
Okay, sir. Okay, sir. Yeah,
That's it.
yeah. It's clear, sir.
That's it.
Okay, sir. Thank you, sir.
Any other doubts? Please raise your hands. Any other doubts? Please raise your hands. Rakesh Kumar.
హలో సార్.
Tell me, Rakesh
సార్
Kumar.
మనం జీరో ఫేజ్ కరెంట్ ఇంకా మ్యాగ్నటైజింగ్ కరెంట్ చూసినాం కదా సార్, లాస్ట్ కి 2 డిఫరెన్సెస్. సార్ అందులో మీరు థర్డ్ హార్మోనిక్ కరెంట్ అని, సో యూ గివ్ ఎ రీజన్ ఫర్ దాట్. జీరో ఫేజ్ కరెంట్ ని మనం ఫండమెంటల్ కరెంట్ అని తీసుకోవచ్చు అకార్డింగ్ టు ఫోరియర్ సిరీస్ లో. జీరో ఫేజ్ కరెంట్ ఉంది కదా సార్,
జీరో సీక్వెన్స్ కరెంట్.
జీరో సీక్వెన్స్ కరెంట్ లో ఫోరియర్ సిరీస్ లో దాన్ని ఫండమెంటల్ కరెంట్ లాగా కన్సిడర్ చేయొచ్చా సార్?
యూ కెన్ కన్సిడర్.
ఓకే సార్, దట్ వాస్ మై డౌట్. థాంక్యూ సార్.
రామకృష్ణ.
Yeah, hello. Good evening, sir.
Good evening, Ramakrishna.
So in the 12th slide, sir.
Okay.
So in that, here you have written that positive and negative sequence per phase networks will be similar. But so here we don't know Vn, no, sir. So how would we calculate?
If it's a balancing system, it's a common assumption to say Vn is 0.
Okay. If not, how would we calculate Va1?
No. If it's a balanced system, neutral voltage we will treat as 0 only, right?
Yes, sir.
What is the doubt you have now?
No, sir. Okay, I have got that.
Yeah, if you want, who is this? Ramakrishna?
Yes, sir.
Just look here. This is a star neutral carrying balanced currents. IA1, IB1, IC1.
Yes, sir.
IB1, IC1, balanced currents. Neutral.
Okay.
Neutral to ground, we didn't kept any impedance.
Yes, sir.
Neutral current is how much?
Neutral
Zero.
current is just 0, sir.
Neutral impedance is how much?
So here infinite, sir. Here.
Infinite.
Open.
What is the neutral voltage?
So it is minus IN. We can't
say. 0 into infinite means it is undefined.
Yes, sir.
Let's do one practical exercise. We can't find mathematically.
Yes, sir.
Practically, we will make an attempt.
Okay.
How to measure voltage practically?
So,
Voltmeter.
Yes, sir. Voltmeter.
I will connect one voltmeter here.
Okay, sir.
Okay?
Yes, sir.
And how much current this voltmeter will carry?
So 0.
0. Why?
So IN, sum of all the three currents should be
0.
Yes, sir.
What is Zn now?
So Zn is so
very high.
Voltmeter. Yeah, yes, sir. High.
1 mega ohm.
Okay.
Then how much is this number? 0 into 1 mega ohm, 10 mega ohm, whatever it is.
0.
0.
Okay.
Practically neutral voltage is 0.
Yes, sir. I have got
So let us treat it as 0. Okay?
Okay.
Pratik.
Hello, sir.
Tell me, Pratik.
Hello, sir. The positive sequence RMF and negative sequence RMF, how this created, I don't know.
How these are created?
I can't get that. Sir.
We discussed that here, conditions for rotating magnetic field. We completed induction machine in your college?
No, sir.
In your college?
In college, yes, sir. College completed.
You might have completed.
I forwarded.
So conditions for rotating magnetic field theory I given here. 3 windings physically displaced by 120 degree. And the windings should carry balanced currents.
Yes, sir.
If these two conditions are getting satisfied, there may be a possibility of getting the rotating magnetic field. That condition was satisfied by positive sequence currents as well as negative sequence.
Yes, sir.
So definitely we have a positive sequence RMF created in the air gap as well as negative sequence RMF created in the air gap.
Yes, sir.
But as the sequence of currents are opposite,
okay,
the rotation of these two RMFs will be one and in the opposite direction.
Okay, sir.
Current, not only balanced currents, sequence of currents will decide the rotation of RMF, direction of rotation of RMF.
Okay, sir. Okay, sir. I
If
understand.
positive sequence is creating in the direction of rotor, negative sequence RMF will be created in opposite direction by the negative sequence currents.
Okay, sir. Due to the sequence of current, that is positive and negative sequence RMF is created. Okay, sir. Okay. Thank you.
Okay.
I get it.
Yeah. Any other doubts you have? Ramakrishna, you raised your hand. Do you have any doubt?
Yes, sir. Another doubt. So, in the you have one question, the phase to neutral sequence voltages of before chapter. So there we have found that VAN1 equal to X angle 30 minus theta minus 30 degrees.
Okay. What's the doubt in that?
So when we calculate line voltage VAB1, VAN minus VBN1. So there would, if we take the example like 1 alpha step, so we would get 1 minus alpha square.
That root 3, what you get there, that I am moving into base.
Okay, yes, sir, I have got that. But generally, if we take 1 minus alpha square, we got root 3 angle 30, no, sir. So I got that. We have removed here root 3.
I am saying that root 3, I moved into base.
Okay.
Okay, root 3 into V base per phase, rewritten as V base line to line.
Okay. Means we can change according to us. So X in first we have taken V base
because
line.
The problem is said on the respective base values, right?
Yeah. Okay. Yes, sir. Okay. I have got that. Okay. Okay. Thank you.
Okay. Anil Kumar Malhotra.
Sir, in positive sequence RMF, sir. So no EMF induced in the rotor. That point I did not get, sir. When
both are rotating in same direction.
So that is the reason for no EMF induced to them.
That is a DC flux. Moreover, rotor flux is a DC flux.
Sir.
Rotating in the same direction of rotor.
Okay, sir.
Then definitely rotor will not experience any rate of change in DC flux, right?
Yes, sir.
So obviously you don't have any EMF induced.
Okay, sir.
Okay?
Okay, sir. Thank you, sir.
Yeah. Any other doubts? Please raise your hands. Anyone have a doubt? So I'll wait for 1 minute. If you have any doubt, you can ask me quickly. Karthik.
Hello, sir.
Tell me, Karthik.
Sir, మీరు క్వశ్చన్ చెప్పారు కదా సార్, డెల్టా స్టార్ జీరో సీక్వెన్స్ కరెంట్స్ అని చెప్పేసి విచ్ ఆఫ్ ద ఫాలోయింగ్ రిప్రజెంట్స్ జీరో సీక్వెన్స్. ఒకసారి ఆ స్లైడ్ ఓపెన్ చేస్తారు.
డెల్టా స్టార్
అదే సార్, జీరో సీక్వెన్స్ కరెంట్స్ ఇన్ విచ్ ఆఫ్ ద ఫాలోయింగ్ రిప్రజెంట్ సర్క్యూట్స్ డెల్టా జీరో సీక్వెన్స్ కరెంట్స్ ఇన్ డెల్టా స్టార్ కాన్ఫిగరేషన్ అని చెప్పేసి ఒకటి చెప్పారు కదా సార్. ఇదే సార్. సార్ మనకి అక్కడ స్టార్ డెల్టా ఇచ్చినప్పుడు లాస్ట్ డెల్టా ఇచ్చారు కదా సార్, అదేంటంటే షంట్ బ్రాంచ్ అనేది ఉంటది కదా మనకి ఇక్కడ.
షంట్ బ్రాంచ్ ఉన్నా లేకపోయినా పెద్ద ఉపయోగం లేదు కదా ప్రైమరీ ఆలో చేయనప్పుడు.
ఓకే సార్, అంటే స్టార్ డెల్టా ఇచ్చినప్పుడు అయితే మనకి
ఈక్వివలెంట్ సర్క్యూట్ సాటిస్ఫై అయిందా లేదా?
అయిపోయింది సార్,
దట్స్ ఇట్.
అదైతే మాత్రం అయింది సార్.
ఒరిజినల్ గా మనకు తెలిసినంత వరకు ఇది సర్క్యూట్.
అవును సార్, అంటే ఫస్ట్
సర్క్యూట్ ప్రాపర్టీ ఏంటి? జస్ట్ ఓపెన్ కదా.
అవును సార్.
ఇది కూడా ఈక్వివలెంట్ సర్క్యూట్ స్టార్ డెల్టా కి.
ఓకే సార్, అంటే అక్కడ డెల్టా ఆ సెంట్ బ్రాంచ్ ఉన్నా లేకపోయినా మనకి పెద్దగా ప్రాబ్లం లేదంటున్నారు.
సర్క్యూట్ అనాలిసిస్ లో ఎటువంటి తేడా లేదు.
ఓకే సార్.
ఓకేనా?
ఓకే సార్. ఓకే సార్, థ్యాంక్ యూ సార్.
ఓకే. వెంకటేష్.
హలో సార్.
వెంకటేష్
సార్, అదే క్వశ్చన్ లో ఫస్ట్ ఆప్షన్ ఎందుకు కాదని ఒకసారి ఎక్స్ప్లెయిన్ చేస్తారు సార్? ఆ ఫస్ట్ ఆప్షన్
ట్రాన్స్ఫార్మర్ కదా, అది ఈక్వివలెంట్ సర్క్యూట్.
ఇదే సార్, ఫస్ట్ ఆప్షన్ ఎందుకు కాదు అని.
If you keep one current source here on primary side,
yes sir,
there is a possibility of current flow provided that equipment above this transformer is providing closed path.
Okay sir. అంటే ఇప్పుడు సెకండరీ అంటే ఓపెన్ లోనే ఉంది కదా సార్. అంటే ప్రైమరీ పెట్టినప్పుడు
We
ఓపెన్
don't
లో
know what
సార్
equipment is
కరెంట్
connected on the
0.
other side, right? For example, this side you have a closed
Okay.
path by some other equipment.
Sir.
Then transformer will allow, right?
Okay. Yes, sir. Yes, sir. Okay, sir.
Understood,
Got it,
Venkatesh?
sir. Yes, sir. Got it, sir.
Okay.
Okay, thank you, sir.
Yeah. Sagar.
Sir, what is one by four phase? Sir, you said that third phase
means in phase.
In phase, sir. The third harmonic also will be in phase, sir.
In phase only.
So such that there will be
angle of phase A current, phase B current, phase C current will be equal.
Okay, sir. Thank you, sir.
Karthik, do you have any doubt, Karthik?
No, sir.
Okay. Anil Kumar, do you have any doubt?
Yes, sir.
Tell me.
Sir, in this question, sir, first we can draw the properties of given zero phase sequence network.
Okay.
Then we can connect the current source and we can find the closed path.
Property
yes, sir, that is a procedure to follow, sir. Okay, sir. That's only I'm asking, sir, because I am confused that directly seeing these questions.
No.
Okay, sir.
Okay.
Thank you, sir.
Okay. Any other doubts? Manikanta.
Good evening, sir.
Good evening.
Sir, I have doubt in per unit impedance.
Tell me.
Sir, if Thevenin's impedance is find general terminals ನಾವು ಸಮ್ చెప్తారు కదా సార్. దాంట్లో ఇప్పుడు Z per unit equal to Z base is equal to V base per phase by S base per phase అన్నారు కదా సార్. టెర్మినల్ దగ్గర ఏ డెల్టా ఇచ్చినా కానీ స్టార్ ఇచ్చినా కానీ పర్ ఫేజ్ వోల్టేజ్ లైన్ టు లైన్ వోల్టేజ్ బై √3 అని చెప్పారు కదా సార్. హౌ దట్ కండిషన్ సాటిస్ఫై సార్ నార్మల్లీ?
Why can't it be?
అదే అర్థం కావట్లేదు సార్, ఆ పాయింట్ ఎలా సాటిస్ఫై అయ్యిద్దని.
Wherever if you are finding at the terminal, always line to line voltage equals to √3 times of the base per phase voltage, right?
అప్పుడు మరి
I am asking you to measure a terminal voltage at some point.
Yes, sir.
Will you measure that voltage with respect to other point or ground?
With respect to ground.
With respect to ground, if you are measuring, it will become line to line by √3 only.
అలాంటప్పుడు మరి జనరల్ టెర్మినల్స్ దగ్గర అయినా కానీ ట్రాన్స్ఫార్మర్ ఎల్వి సైడ్ అయినా కానీ సేమ్ ఆన్సర్ వచ్చేది కదా.
రెండు ఒకటే కదా, రెండు ఒకే టెర్మినల్ కదా, మళ్ళీ రెండు ఎందుకు అక్కడ, ఒకటే టెర్మినల్.
ఓకే సార్. అనదర్ డౌట్ సార్. Today's problem on three phase unbalanced system, we can find a positive sequence and negative sequence. Positive sequence line voltage will be given VA_B1 equal to X at an angle θ1. Sir, I have found నేను కొన్ని వాల్యూస్ పెట్టాను సార్ అక్కడ. VA1 equal to 0.9. Then VA_B1 equal to VA1 minus VB1.
Okay.
VB1 equal to alpha square into VA1.
Okay.
0.9 minus 1 at an angle 240 into 0.9 at an angle 0. In that నేను అలా దాన్ని సాల్వ్ చేసుకుంటూ వస్తే యాంగిల్ 30 degrees వచ్చింది కానీ మ్యాగ్నిట్యూడ్ 1 రాలేదు సార్.
ఎంత వచ్చింది మ్యాగ్నిట్యూడ్?
1.3 1.55 వచ్చింది సార్.
0.9 రాలేదా?
0.9 రాలేదు సార్.
0.9 into √3 వచ్చిందా?
0.9 into √3 అది నేను చెక్ చేయలేదు సార్ కండిషన్.
చెక్ చేయి.
Yes sir. 0.9. Yes sir.
ఆ √3 ని బేస్ లోకి తీసుకో.
ఆ √3 ని బేస్ లోకి తీసుకుపోతే
√3 into V base per phase అవుతుందా?
Yes sir. √3 into V base per phase.
అది V base line to line.
V phase line to line. Okay.
Per unit value same, but base value was modified according to line to line voltage calculation.
Okay sir.
Okay Manikanta?
Yes sir.
Venkanna.
Sir, good evening, sir.
Good evening.
Sir, I don't have any doubts regarding the subject, sir. Sir, morning call చేసాం సార్ ఇన్స్టిట్యూట్ కి ఆఫ్లైన్ క్లాసెస్ ఎప్పుడు స్టార్ట్ అవుతాయి అని అడిగితే
You asked them. You asked the management people also. I don't know about
యాక్చువల్గా ఫ్యాకల్టీ ఇన్ఫార్మ్ చేస్తారని చెప్పారు సార్. సో దట్స్ వై ఐఎమ్ ఆస్కింగ్.
Okay. They didn't said anything to me. If any information is there, I will tell you tomorrow.
Okay. Thank you, sir.
Okay. Any doubts? Can I close the session? Thank you.